Before we descend into the darkness, I want to ask a favour. If you enjoy this story, please use your hype points on this video. It helps the channel more than you possibly know. If you're listening on Spotify, leaving a review makes a massive difference. And if you'd like, comment what time it is and where in the world you're listening from. We absolutely love seeing where everyone is tuning in. And of course, if you enjoy the content, consider subscribing. Now let's begin. There is something deeply reassuring about numbers. When we encounter data about the world, whether it's success rates, test scores, or recovery percentages, we instinctively look for the bottom line, the overall summary that tells us what really happened. If you show someone a table filled with different groups and different outcomes, their eyes will drift toward the total at the end, the grand average that seems to capture everything in one honest measure. This impulse makes perfect sense after all. If you want to know how well a treatment works, or which school performs better, or whether one approach succeeds more often than another, shouldn't you just look at all the cases combined? The word overall carries a certain authority, a promise that you're seeing the complete picture rather than cherry-picking convenient pieces. It feels like the most reliable truth, the number that can't be accused of bias or selective reporting because it includes absolutely everything. But there exists a quiet, unsettling moment in statistics where this intuition completely fails. It's a moment when you gather all your data, calculate that reassuring overall average, and discover that it points in the exact opposite direction of what every single subgroup clearly shows. This isn't a rare computational mistake or a sign that someone manipulated the numbers. It's a genuine mathematical phenomenon called Simpson's paradox, and it represents one of the most counterintuitive aspects of how aggregated data can behave. The paradox doesn't require complicated formulas or advanced mathematics to appear. It simply requires the right kind of structure in your data, different group sizes, different baseline conditions, and a hidden variable quietly influencing how observations get distributed. When these elements combine in particular ways, the overall trend can reverse completely, showing improvement where every subgroup shows decline, or showing harm where every subgroup shows benefit. The shock of Simpson's paradox lies not in its complexity, but in its directness. It demonstrates that combining data doesn't always clarify reality. Sometimes it flips reality into something that contradicts what's actually happening in every observable corner of your dataset. Let's state the core pattern plainly, because the paradox is most striking when you see it in its simplest form. Imagine you're examining the relationship between two variables. Perhaps you're comparing two medical treatments, or two teaching methods, or two business strategies. You divide your data into natural subgroups, perhaps by age, or severity of condition, or initial skill level. Within each subgroup, you see the same clear trend. Treatment A performs better than treatment B in the first group. Treatment A performs better than treatment B in the second group. If you have a third group, treatment A wins there too. Every single comparison, when you control for the subgroup, points in the same direction. The evidence seems overwhelming and consistent. Now you combine all the groups together to look at the overall results. You calculate the total success rate for treatment A across everyone and the total success rate for treatment B across everyone. And suddenly, impossibly, the trend reverses. Treatment B has a higher overall success rate than treatment A. The combined data says precisely the opposite of what every subgroup demonstrated. This isn't a subtle shift or a case where one group differs from the others. All groups agreed on one direction. Every single comparison pointed the same way. Yet the combined average points in the reverse direction. Your first instinct might be to check for a calculation error, to assume someone made a mistake in adding up the numbers. But the arithmetic is correct. The paradox is real, and it's not even particularly rare. The shock of Simpson's paradox comes from how directly it violates our intuition about aggregation, We expect that when we combine evidence from multiple sources, we're building a stronger, more complete picture. We assume that averaging across groups should give us something like a consensus, a middle ground that reflects the general pattern. But Simpson's paradox shows that combining groups isn't always like stacking similar building blocks into a taller tower. Sometimes it's more like mixing liquids of different densities. The result doesn't simply reflect the properties of each component, but rather how much of each component you included and how their different properties interact when combined. The overall average isn't a pure, unbiased summary of the underlying relationships. It's a weighted mixture, and if the weights are uneven in particular ways, that mixture can produce a complete reversal of the pattern you saw in every individual piece. To understand why this happens, we need to think carefully about what an overall average actually represents. When you calculate an average across different groups, you're not treating each group equally. You're giving more influence to the groups with more observations. This is mathematically unavoidable. If Group 1 contains 90 observations and Group 2 contains 10 observations, the overall average will be dominated by whatever happened in Group 1. That's just arithmetic. The bigger group pulls the combined average toward its own value. This weighting isn't necessarily a problem. In fact, it's often exactly what we want, especially if the groups represent how things naturally occur in the real world. If you're measuring the average height of adults and 90% of your sample is between 20 and 60 years old, while only 10% is over 80, the overall average will mostly reflect the heights of younger and middle-aged adults, which makes sense because that's what most adults are. But this weighting becomes deeply problematic when the groups differ not just in size but in their baseline characteristics, when the groups aren't just different quantities of the same thing, but fundamentally different contexts. Simpson's paradox emerges when groups have different baseline levels of the outcome you're measuring, and when those groups are unevenly distributed between the conditions you're comparing. The overall average then becomes a peculiar mixture. It's not measuring the pure effect of your comparison, but rather the effect mixed together with the distribution of observations across contexts. The larger groups, or the groups where observations cluster more heavily, will dominate the overall statistic, and if these groups happen to have very different baseline outcomes, the overall trend can reflect that distribution pattern more than it reflects the actual relationship you're trying to measure. Let's think about this mechanism with a simple abstract example. Imagine you're comparing two things, call them option A and option B, and you're measuring success rates. You have two groups of cases, easy cases and hard cases. Within easy cases, option A succeeds 85% of the time, and option B succeeds 80% of the time. Option A is better. Within hard cases, option A succeeds 50% of the time, and option B succeeds 40% of the time. Option A is better there too. Both comparisons point in the same direction. Option A outperforms option B in both contexts. Now here's where the distribution matters. Suppose option A is used mostly for hard cases. Perhaps it's a more intensive or expensive approach that people reserve for difficult situations. Let's say option A handles 90 hard cases and only 10 easy cases. Meanwhile, option B is used mostly for easy cases. Perhaps it's the standard first-line approach. Option B handles 90 easy cases and only 10 hard cases. Now calculate the overall success rates. For option A, you have 90 hard cases with a 50% success rate, giving you 45 successes, plus 10 easy cases with an 85% success rate, giving you 8.5 successes, for a total of 53.5 successes out of 100 cases, a 53.5% overall success rate. For option B, you have 90 easy cases with an 80% success rate, giving you 72 successes, plus 10 hard cases with a 40% success rate, giving you 4 successes, for a total of 76 successes out of 100 cases, a 76% overall success rate. The reversal is complete. Option A wins in easy cases. Option A wins in hard cases, but option B wins overall. The reason is entirely about distribution. Option A faced mostly hard cases, which naturally have lower success rates regardless of which option you use. Option B faced mostly easy cases, which naturally have higher success rates. The overall averages are dominated by these baseline difficulty levels rather than by the relative effectiveness of the options. You're not seeing which option is better, you're seeing which option happened to be used more often in easier situations. The overall statistic has become confounded by case mix, and that confounding is strong enough to completely reverse the direction of the relationship you observed in every controlled comparison. This brings us to the heart of what's really happening in Simpson's paradox: the presence of a hidden variable that changes how observations get distributed across your comparison groups. The paradox doesn't appear randomly, it requires a specific structure where some third factor, something beyond just the two variables you're comparing, influences both which group a case belongs to and what the baseline outcome is likely to be. This third factor is often called a confounding variable, and its role in Simpson's paradox is to create an unequal distribution that masks the true relationship when you combine groups. Think about what constitutes a confounding variable in this context. It's something that affects group membership. It determines which cases end up in which subgroup, and it also affects the outcome you're measuring. In our treatment example, the confounding variable was case difficulty. Difficulty affected which treatment got chosen, with harder cases more likely to receive treatment A, and difficulty also affected success rates, with harder cases naturally having lower success regardless of treatment. When you combined all cases together without accounting for difficulty, you were comparing unlike with unlike. You were comparing treatment A's performance in a mostly difficult patient population against treatment B's performance in a mostly easy patient population. The overall difference in success rates reflected the difference in patient populations more than it reflected the difference in treatment effectiveness. This pattern appears over and over in real-world data, often in situations where people don't immediately recognize the confounding variable at work. Consider college admission rates, a classic example of Simpson's paradox. You might find that when you look at overall admission rates, School A admits a lower percentage of applicants than School B. But when you break down the data by department, you discover that School A has higher admission rates than School B in every single department. How is this possible? The resolution lies in application patterns. Perhaps School A has more of its applications concentrated in highly selective departments, engineering, medicine, law, where admission rates are naturally low for everyone. School B might have more applications concentrated in less selective departments, where admission rates are naturally higher. The overall admission rate at School A is pulled down by the concentration of applications in tough departments, while School B's overall rate is pulled up by the concentration in easier departments. Within any given department, School A is actually more welcoming, but across all departments combined, School B appears more accessible simply because of where applicants chose to apply. The hidden variable here is department selectivity. It affects where applications concentrate. Students self-select into different departments based on their interests and qualifications. And it affects admission rates. Some departments are naturally more selective than others, regardless of which school they're at. When you calculate overall admission rates, you're mixing together applications from highly selective and less selective departments in different proportions at each school. The overall rates tell you more about the mix of departments where students applied than about how welcoming each school actually is to comparable applicants. Or consider a medical example that feels particularly urgent and real. Suppose you're comparing mortality rates between two hospitals. Hospital Alpha has a higher overall mortality rate than Hospital Beta. More of their patients die. This seems like damning evidence that Hospital Beta provides better care. But then you break down the data by patient condition severity. You look at low-risk patients, those who come in with minor issues or routine procedures. Hospital alpha has a lower mortality rate than hospital beta for these patients. Then you look at high-risk patients, those who arrive with serious conditions or undergo complex surgeries. Hospital alpha has a lower mortality rate than hospital beta for these patients too. Hospital alpha achieves better survival rates for both low-risk and high-risk patients, yet has a worse overall mortality rate. The paradox appears because of patient mix. Perhaps hospital alpha is a major trauma centre or a specialised facility that receives a much higher proportion of high-risk cases. Even though they save a higher percentage of both low-risk and high-risk patients than hospital beta does, their overall mortality rate is driven up by the fact that most of their patients are in the high-risk category, where mortality is inevitable for some percentage regardless of care quality. The hidden variable is patient risk level. It affects which hospital patients go to. Sicker patients get referred to specialised centres. Healthier patients might choose community hospitals. And it affects mortality. Sicker patients are more likely to die regardless of where they're treated. The overall mortality rates are confounded by case mix, and unless you account for that case mix, you might conclude the opposite of the truth about care quality. The hospital that actually saves more lives per comparable patient can appear worse when you ignore the fact that they're treating a fundamentally different and more challenging patient population. These examples share a common structure. There's a comparison you want to make between treatments, between schools, between hospitals. There's an outcome you're measuring: success rates, admission rates, survival rates. And there's a third variable that creates structure in your data: difficulty level, department selectivity, patient risk, that influences both which observations end up in which group and what the baseline outcome tends to be. When this third variable distributes observations unevenly across the groups you're comparing, the overall average becomes a weighted mixture of different baseline conditions, rather than a pure measure of the comparison you care about. The bigger the imbalance in distribution, and the bigger the difference in baseline outcomes between subgroups, the more likely you are to see Simpson's paradox appear. Let's walk through another example slowly, letting the reversal unfold step by step so you can watch the mechanism at work. Imagine a company is evaluating two training programs for its employees. Program X and Program Y both aim to improve job performance, measured by some standardized assessment. The company has two types of employees: new hires who are still learning the basics, and experienced workers who are refining advanced skills. The company decides to look at performance scores after training to see which program works better. They start by examining new hires. Among new hires who took Program X, the average post-training score is 65 out of 100. Among new hires who took Program Y, the average score is 60 out of 100. Program X appears superior for new hires, producing scores that are 5 points higher on average. Then they look at experienced workers. Among experienced workers who took Program X, the average score is 88 out of 100. Among experienced workers who took Program Y, the average score is 85 out of 100. Again, Program X produces better results, this time by 3 points. Every comparison favours Program X. It works better for new hires, and it works better for experienced workers. Confident in these findings, the company calculates the overall average scores. They're surprised to discover that across all employees combined, Program Y has a higher average score than Program X. How did this happen? The answer lies in who took which program. Let's say Program X is a more intensive, time-consuming program that requires significant time away from regular work. Because of this, the company tended to use Program X primarily for new hires, people who weren't yet fully productive anyway. So taking them away from work for training didn't represent a major opportunity cost. Out of 100 people who took Program X, 90 were new hires and only 10 were experienced workers. Meanwhile, Program Y is a lighter, more flexible program that people can complete while still doing their regular jobs. The company used Program Y primarily for experienced workers who couldn't spare the time for intensive training. Out of 100 people who took Program Y, 90 were experienced workers and only 10 were new hires. Now let's calculate the overall averages carefully. For Program X, 90 new hires scoring an average of 65 points contribute 5,850 total points. 10 experienced workers scoring an average of 88 points contribute 880 total points. Combined, that's 6,730 points across 100 people, for an average of 67.3 points. For Program Y, 10 new hires scoring an average of 60 points contribute 600 total points. 90 experienced workers scoring an average of 85 points contribute 7,650 total points. Combined, that's 8,250 points across 100 people, for an average of 82.5 points. Program Y's overall average is dramatically higher, 82.5 versus 67.3. Yet Program X outperformed Program Y in both subgroups. The resolution is transparent once. You see the distribution. Program X's overall average is pulled down by the fact that 90% of its participants were new hires who naturally score lower regardless of training program because they're still learning basic skills. Program Y's overall average is pulled up by the fact that 90% of its participants were experienced workers who naturally score higher because they already have strong foundational skills. The overall averages are dominated by employee experience level rather than by program effectiveness. If you only looked at the overall scores, you'd conclude that Program Y is the superior training program and should be rolled out to everyone. But if you actually assigned new hires to Program Y and experienced workers to Program X, you'd be giving each group the program that performed worse for people like them. The overall statistic pointed you toward exactly the wrong decision. This example illustrates why Simpson's paradox matters beyond being a statistical curiosity. It's not a rare edge case that only appears in carefully constructed textbook examples. It's a warning about a fundamental interpretive challenge that appears whenever you're combining data from groups with different characteristics and different distributions. The paradox emerges in medical studies, in educational assessments, in business analytics, in social science research, in legal cases, in policy evaluations, anywhere that data combines groups with different base rates, different starting conditions, different selection patterns, or different exposure levels. And the danger is that the overall trend, the number that feels most authoritative and complete, can actively mislead you about what's actually happening. The prevalence of Simpson's paradox in real decisions stems from a few common patterns in how data gets collected and analysed. First, people often self-select into groups based on factors that also affect outcomes. Students choose which departments to apply to based partly on their interests and qualifications, and those same factors affect admission rates. Patients end up at different hospitals based partly on how sick they are, and sickness level affects survival. This self-selection creates the uneven distribution across groups that enables the paradox. Second, people often make comparisons using aggregate data without carefully considering what subgroups might exist within that data. It's easier and more intuitive to compare overall success rates than to break everything down by relevant factors and compare within each factor level. But that convenience can come at the cost of accuracy. Third, the factors that create structure in your data, the confounding variables, aren't always obvious or immediately visible. You might not have data on patient risk levels, or case difficulty, or prior experience, or the dozens of other factors that could be creating unequal distributions and different baseline outcomes across groups. This brings us to a crucial shift in how we should think about Simpson's paradox. The question isn't really which trend is true, the subgroup trends, or the overall trend, both trends are mathematically accurate. The subgroup trends are true. Within each subgroup, the relationship goes in that direction. The overall trend is also true. When you combine all observations together, the aggregate relationship goes in that direction. The paradox doesn't indicate that someone calculated incorrectly or that the data is lying to you. It indicates that you're seeing two different things, two different questions being answered by two different statistics. The better question is, overall for whom? Under what mix? When you calculate an overall average, you're calculating the average outcome for the specific mixture of groups that happen to exist in your data. If 90% of people in your dataset received a treatment under difficult conditions and 10% received it under easy conditions, your overall average tells you what happens for that particular 90-10 mix. It doesn't tell you what would happen if the mix were different. It doesn't tell you what would happen for a specific individual whose circumstances you know. And it doesn't necessarily tell you which option is inherently better when compared under equivalent conditions. This reframing helps clarify when each type of statistic is meaningful. The subgroup comparisons tell you about relative effectiveness within comparable contexts. They control for the confounding variable by holding it constant. They compare like with like. If you're trying to make a decision for someone whose circumstances you know, the subgroup comparison is usually what you want. If you're a new hire trying to choose between training programs, you should look at how each program performed for other new hires, not at how they performed overall, across a mix of new and experienced workers that doesn't reflect your situation. If you're a patient with a known risk level trying to choose between hospitals, you should look at how each hospital performs for patients with your risk level, not at overall mortality rates that mix together all risk levels in proportions that might not match your case. The overall statistic tells you about what happens under the real-world distribution as it exists. If you're trying to predict aggregate outcomes for a population that will naturally sort itself into groups in particular proportions, the overall statistic captures that. If you're a policymaker trying to understand what will happen if you implement a program across an entire population that will distribute itself across difficulty levels in certain ways, the overall rate might be informative. But even then, you need to understand what that overall rate represents. It's not a pure measure of program effectiveness, but rather a measure of effectiveness mixed with population distribution. If the distribution changes, the overall rate will change even if the program's effectiveness within each subgroup stays constant. The paradox teaches that truth depends on the question you're actually trying to answer. Are you trying to measure which option is more effective under equivalent conditions? Then you want the subgroup comparisons because they isolate the effect by controlling for confounding factors. Are you trying to predict what will happen in practice given how things actually distribute themselves? Then you need to think carefully about whether your current overall statistic reflects the distribution that will actually occur, or whether it reflects a historical distribution that might not continue. Simpson's paradox appears when we confuse these questions, when we use an overall statistic to answer a question about comparative effectiveness, or when we assume that overall rates will stay constant even as the underlying distribution shifts. Consider what happens if you try to apply an overall statistic without understanding its dependence on distribution. Suppose our company from earlier decides that since Program Y has a higher overall average score, they'll switch everyone to Program Y. All new hires will now take Program Y instead of Program X, and all experienced workers will continue taking Program Y as they already were. What happens to the overall average? It drops. New hires who previously would have scored 65 under Program X now score 60 under Program Y. The company's overall average was 82.5 when 90% of trainees were experienced workers taking Program Y and 10% were new hires taking Program Y. Now that everyone takes Program Y, with let's say equal numbers of new and experienced workers, the overall average becomes the midpoint of 60 and 85, which is 72.5. The overall average dropped by 10 points, even though the company switched everyone to the program with better overall performance. The disconnect happened because the original overall average didn't measure program quality. It measured the outcome of having most trainees be experienced workers. Once that distribution changed, the overall average changed too, revealing that it was never a stable measure of program effectiveness. This helps explain why Simpson's paradox can be so dangerous in practice. People make decisions based on overall statistics, assuming those statistics reflect some stable underlying truth. But when the statistic is confounded by distribution, and when the decision changes that distribution, the expected outcome can fail to materialize. You thought you were choosing the better option, but you were actually choosing the option that happened to be used more often by people with naturally better outcomes for reasons unrelated to the option's effectiveness. So how do you protect yourself from being fooled by Simpson's paradox? The answer lies not in always preferring subgroup trends over overall trends, or vice versa, but in understanding what created the structure in your data and what question you're actually trying to answer. This requires a kind of gentle, persistent skepticism about aggregate statistics, not a rejection of them, but a habit of looking beneath them to see what they're made of. Start by asking what the relevant subgroups might be. Whenever you're comparing two things and looking at an overall difference, consider whether there are natural categories within your data that might have different baseline outcomes. If you're comparing success rates, think about whether there are easier and harder cases. If you're comparing test scores, think about whether there are students with different starting skill levels. If you're comparing medical outcomes, think about whether there are patients with different severity levels. The goal isn't to subdivide endlessly, but to identify factors that both affect the outcome you're measuring and might be distributed differently across the groups you're comparing. Next, ask whether group sizes are uneven. If your two comparison groups have equal numbers of observations in each subgroup, Simpson's paradox becomes much less likely, though still possible in more complex scenarios. But if one comparison group is concentrated in a particular subgroup, while the other is concentrated elsewhere, that's a warning sign. Uneven distribution is the structural requirement for the paradox to appear. The more extreme the imbalance, the more the overall statistic will be dominated by whichever subgroup is largest, and the more likely it is that the overall trend could diverge from the within subgroup trends. Then ask whether there's a third variable that could be creating both the group membership pattern and the baseline outcome differences. This is where you look for confounding. What determines which observations end up in which comparison group? Is it random assignment, or do observations sort themselves based on some factor that also affects the outcome? If treatments are chosen based on patient severity, if schools attract applications based on department prestige, if programs are assigned based on employee experience level, then you have potential confounding. The third variable is creating an unequal distribution across the groups you're comparing, and that distribution might be masking or reversing the true relationship. Ask whether you're comparing like with like. This is really the heart of the issue. When you calculate an overall average across groups, you're implicitly treating all observations as equivalent, as though they all came from the same context. But if the groups have fundamentally different characteristics, different difficulty levels, different risk profiles, different starting points, then combining them isn't giving you a fair comparison. It's giving you a comparison that's confounded by whichever group contributed more observations. The subgroup comparisons attempt to compare like with like by holding the confounding variable constant. Finally, ask what you're trying to learn. This might be the most important question. Are you trying to understand which option is inherently more effective, more successful, or better when applied to equivalent situations? Then you probably want controlled comparisons within subgroups, because those isolate the effect you care about. Are you trying to predict what will happen in practice as things naturally occur with people or cases distributing themselves, however they actually do, then you need to think carefully about whether your overall statistic reflects the relevant real-world distribution and whether that distribution is stable or might change. Understanding what the overall number actually represents is how you avoid being fooled by Simpson's paradox. You don't solve the paradox by picking one trend and declaring it the winner. You solve it by recognizing that aggregation is not neutral. It's a choice about how to weight different pieces of evidence, and that choice matters enormously when the pieces have different characteristics. The overall statistic is not more objective or more complete than the subgroup statistics. It's simply answering a different question, and if the distribution is uneven in particular ways, it might be answering a question you don't actually care about. There's something humbling about Simpson's paradox that goes beyond the specific mathematical mechanism. It challenges our basic intuition that more data and broader aggregation lead to clearer truth. We're taught to be skeptical of small samples and narrow views, to value comprehensive datasets that include everyone. And this is generally good advice. Small samples are indeed more vulnerable to random noise and less likely to capture the full picture. But Simpson's paradox shows that comprehensiveness can mislead when comprehensiveness means combining things that shouldn't be combined, mixing contexts that are fundamentally different. The broadest view isn't always the clearest view. Sometimes clarity requires looking more narrowly at carefully defined subgroups where comparisons are actually meaningful. The paradox also reveals something about the nature of statistical truth. We often talk about statistics as though they're simply reflecting objective reality, as though if we measure carefully enough, we'll discover what's really true. But statistics are always measuring something specific, answering particular questions based on how we've structured the analysis. Simpson's paradox shows that the same data can truthfully tell two opposite stories depending on whether you aggregate or disaggregate, and both stories are mathematically correct. The reversal isn't an error or an illusion, it's a genuine feature of how different levels of aggregation can yield different relationships. This doesn't mean truth is arbitrary or that all interpretations are equally valid. It means that statistical truth is always conditional on the question being asked and the structure being analysed. The relationship between two variables isn't a single fixed thing. It can genuinely differ depending on whether you're looking within homogeneous subgroups or across heterogeneous mixtures. This connects to a broader insight about how we should interpret quantitative evidence. Numbers feel precise and objective, but every number is embedded in context, in decisions about what to measure, how to group observations, which variables to control for, what level of aggregation to use. Simpson's paradox is an extreme example where these choices lead to opposite conclusions, but the underlying lesson applies more generally. Every average is an average of something, aggregated in some particular way, and the structure of that aggregation shapes what the average means. When you see an overall statistic, you're not seeing a pure, unmediated truth about the world. You're seeing one particular summary of the data, created by combining observations in a specific way, and that summary might or might not be answering the question you care about. The gentle irony of Simpson's paradox is that it appears precisely when you try to be most comprehensive and inclusive. The reversal doesn't happen because you ignored some data or cherry-picked favourable comparisons. It happens because you included all the data and combined it into one grand overall statistic. The paradox emerges from totality, from the attempt to capture everything in a single number. This isn't an argument against comprehensiveness, but it is a reminder that comprehensiveness without structure can obscure rather than illuminate. The goal isn't to avoid combining data. Often you need combined statistics to understand aggregate outcomes. The goal is to understand what your combined statistic actually represents, what it's weighted by, what it's mixing together, and whether that mixture corresponds to the question you're trying to answer. There's also a practical lesson about communication and interpretation. When you present an overall statistic, a success rate, an average outcome, a comparative measure, you're implicitly claiming that this number represents a meaningful summary, that it tells people something useful about the comparison you're making. But Simpson's paradox shows that an overall statistic can be actively misleading even when it's correctly calculated. If the statistic is dominated by one subgroup, if it's confounded by a third variable, if it combines unlike with unlike, then presenting it without explanation can lead people to exactly the wrong conclusion. This places a burden on anyone analysing or presenting data to look beneath the overall numbers, to check for subgroup patterns, to consider potential confounding, and to help others understand what the aggregate statistics do and don't tell you. At the same time, there's a burden on people interpreting data, on all of us when we encounter statistics in news reports, research papers, policy documents, or business analyses to maintain a healthy curiosity about where numbers come from. When someone tells you that option A has better overall outcomes than option B, it's worth asking, better for whom? Under what conditions? In what mixture of circumstances? Are the groups being compared actually equivalent, or is one group handling harder cases, or facing more challenging conditions, or drawing from a different population? These questions aren't about being needlessly skeptical or distrusting all statistics. They're about recognizing that statistics answer specific questions, and the question being answered might not be the question you need answered. Simpson's paradox appears in enough real-world contexts that it's worth being aware of its signature. Every subgroup shows one trend, but the overall data shows the opposite trend. When you encounter this pattern, it's almost always because of unequal distribution combined with different baseline outcomes across subgroups. The larger groups, or the groups where observations cluster more heavily in one comparison group versus the other, dominate the overall average. The overall statistic ends up measuring the mix of who ended up where, rather than measuring the pure effect of your comparison. And if you act on the overall statistic without understanding this, you can make decisions that actively contradict what works in every actual context. But here's the comforting part. Once you understand the mechanism, Simpson's paradox stops being paradoxical. The reversal stops feeling like magic, or like the data is somehow broken. It starts feeling like a natural consequence of weighted averages when weights are uneven and baselines differ. You can see it coming when you notice the structural elements. Different group sizes, different baseline outcomes, potential confounding variables. You can check for it by breaking your overall comparison into subgroups and seeing whether the pattern holds or reverses. And you can avoid being misled by it by thinking carefully about what question you're trying to answer and whether your overall statistic is actually answering that question or confounding it with distribution effects. The paradox also becomes less threatening when you realize that you don't need to resolve it by declaring one trend right and the other wrong. Both trends can be accurate descriptions of different things. The subgroup trends describe what happens within comparable contexts. The overall trend describes what happens when you mix those contexts in particular proportions. Neither is a lie, neither is a mistake, they're just answering different questions. Your job is to figure out which question matters for your purpose and interpret the appropriate statistic accordingly, while understanding what it represents and what it doesn't. There's something almost meditative about sitting with Simpson's paradox long enough to really understand it. At first it feels impossible. How can all the subgroups point one way and the total point the other way? It seems to violate basic logic. But as you work through the arithmetic, as you watch how weighted averages operate, as you see how different group sizes and different baselines interact, the impossibility dissolves into inevitability. Of course this happens. Of course, when you have uneven distributions and different baseline outcomes, the overall average can reverse. It's not mysterious once you see the mechanism. It's just math, working exactly as math should. revealing that aggregation is not neutral and that structure matters. This understanding brings with it a kind of calm clarity about how to think about data. You don't need to be afraid of Simpson's paradox, or to assume that any statistic might reverse if you just found the right subgroups. The paradox requires specific conditions, uneven distribution, different baselines, confounding variables. Most of the time, when you aggregate data, you get something that reasonably reflects the average of what happened. But you develop an awareness, a habit of asking about structure, about distribution, about what's being mixed together. You look at overall statistics with both respect for what they capture and caution about what they might obscure. The paradox also offers a gentle reminder about intellectual humility. We live in a world that increasingly runs on data, on metrics, on quantified comparisons and statistical summaries. And this is in many ways valuable. Data can reveal patterns we wouldn't otherwise see, can help us make more informed decisions, can check our biases and intuitions against empirical evidence. But Simpson's paradox shows that data doesn't interpret itself. The same dataset can support opposite conclusions depending on how you analyze it. The numbers don't tell you which analysis is appropriate. You need judgment, context, understanding of the domain, and careful thought about what you're trying to learn. The paradox appears at the intersection of mathematics and meaning, where technically correct calculations can lead to substantively wrong interpretations if you don't understand the context that generated the data. In some ways, Simpson's paradox is a lesson in slowing down. Our instinct with data is often to look for the bottom line, the simple summary, the clear answer. We want to know which is better. What's the overall result? What does the data say? And there's nothing wrong with wanting clear answers. But the paradox teaches that clarity sometimes requires stepping back from the immediate overall number and asking what created it, what it's made of, whether it's mixing things that should be separated. This slower, more careful approach to interpretation, looking at subgroups, thinking about distribution, considering confounding, is what protects you from being misled. It's also worth noting that Simpson's paradox can work in both directions. We focus mostly on examples where subgroup trends all point one way and the overall trend reverses, but the paradox can also make something look good overall, even though it's worse in every subgroup. The same mechanism operates. Uneven distribution across groups with different baselines creates an overall statistic that's dominated by mix rather than by comparative effect. Whether this makes the overall trend reverse from negative to positive or from positive to negative depends on the specifics of which groups are larger and which baselines are higher. But the underlying issue is the same. The overall trend can mislead in either direction. There's also a version of Simpson's paradox that can appear with more than two groups, or with continuous rather than categorical subgroups, or in more complex statistical models. The basic insight remains when you aggregate across contexts that differ in both their prevalence and their baseline outcomes, the aggregate can show a relationship that differs from or reverses the relationship within contexts. The mathematical sophistication can increase, but the conceptual core stays the same. Aggregation combines data in ways that weight some observations more heavily than others, and if those weights correlate with baseline outcomes, the aggregate relationship can misrepresent the within-context relationships. Understanding Simpson's paradox also helps clarify what it means to control for a variable in statistical analysis. When researchers say they controlled for a factor, age, severity, experience level, whatever, they're often doing something analogous to looking at subgroups. They're trying to compare outcomes while holding that factor constant, rather than letting it confound the comparison. Simpson's paradox illustrates why this matters. Without controlling for confounding variables, your comparison might be dominated by who ended up in which group, rather than by the actual effect of your treatment or intervention. Controlling for those variables, either by analysing subgroups separately or by including them in a statistical model, attempts to isolate the relationship you care about from the distribution effects that can obscure or reverse it. But even controlling for variables requires judgment. Which variables should you control for? If you control for too few, you leave in confounding. If you control for too many, you might control away the very relationship you're trying to measure, or introduce new biases. Simpson's paradox doesn't give you a formula for which variables to control. It just demonstrates that whether you aggregate or disaggregate, and along which dimensions, fundamentally shapes what relationships you'll observe. The decision about what constitutes a meaningful comparison, about which subgroups matter, about what should be controlled and what should be examined. Separately, these are judgment calls that depend on understanding the subject matter, not just the mathematics. There's a philosophical dimension here too, about the nature of causation and effectiveness. When we ask whether treatment A is better than treatment B, we're often asking a causal question. Does choosing treatment A cause better outcomes than choosing treatment B? But Simpson's paradox shows that this question doesn't have a single answer, independent of context. Treatment A might cause better outcomes for easy cases and for hard cases, but if you apply it to a population that's mostly hard cases, while applying treatment B to a population that's mostly easy cases, treatment B will show better overall outcomes. The causal effect depends on context, on who receives the treatment and what their baseline characteristics are. This doesn't mean causation is hopelessly relative, or that we can't make meaningful causal claims. It means that causal effects can vary across contexts, and overall averages of causal effects depend on the distribution of contexts, just as overall averages of any quantity do. This insight connects to debates in fields like medicine and public health about the difference between efficacy and effectiveness. Efficacy typically refers to how well something works under ideal controlled conditions, like the subgroup comparisons in Simpson's paradox, where you're comparing like with like. Effectiveness refers to how well something works in actual practice, where people aren't randomly assigned and contexts vary. Simpson's paradox shows that effectiveness statistics can be misleading if the real-world distribution includes confounding. A treatment might show worse overall effectiveness than an alternative, even though it has better efficacy in every context, simply because it gets used more often in harder contexts. As you sit with all of this, letting the implications settle, there's a sense in which Simpson's paradox is both deeply important and quietly reassuring. It's important because it reveals a genuine way that statistical evidence can mislead, a way that overall numbers can point in precisely the wrong direction. This matters for medical decisions, policy choices, business strategies, legal arguments, and anywhere else that data drives conclusions. Missing Simpson's paradox can lead to actively harmful decisions, choosing treatments that perform worse, implementing policies that backfire, trusting institutions that actually underperform, all because an overall statistic confounded effectiveness with distribution. But it's also reassuring because the paradox is understandable. It's not a weird quantum phenomenon or an irreducible mystery. It's just weighted averages behaving exactly as weighted averages should, combined with distributions that happen to be uneven in particular ways. Once you see the mechanism, you can check for it, you can look at subgroups, you can think about distribution. You can ask what's being mixed together and whether the mix matches what you care about. The paradox gives you something specific to watch for, that signature pattern of within-group consistency but overall reversal. When you see it, you know there's confounding from distribution, and you can adjust your interpretation accordingly. Perhaps the deepest lesson of Simpson's paradox is about the relationship between simplicity and truth. We value simplicity in explanations and summaries. We want the one number that tells us what we need to know, the clear bottom line, the straightforward answer. And often, simplicity serves us well. It makes information manageable and communicable. But Simpson's paradox shows that sometimes the simple summary, the overall average, the comprehensive total, doesn't capture what's actually happening. Sometimes truth requires accepting complexity, requires looking at multiple subgroups, rather than one overall number, requires acknowledging that different contexts might need different answers. This isn't an argument for making everything complicated or for never using aggregate statistics. It's an argument for being willing to dig deeper when the overall statistic might be hiding important structure, for being comfortable with the idea that sometimes the right answer isn't a single number, but a set of conditional statements about what happens in different contexts. The paradox also reminds us that context is not optional decoration added to statistics. It's fundamental to what statistics mean. The same success rate means something different if it came from easy cases versus hard cases. The same admission rate means something different if it came from selective departments versus open enrollment programs. The same mortality rate means something different if it came from low risk versus high risk patients. Context isn't separate from the number. It's part of what makes the number meaningful or misleading. Simpson's paradox appears when we strip away context by aggregating, when we combine numbers from different contexts and lose track of where they came from. Preserving context through subgroup analysis or appropriate controls, or simply through careful description of what the overall number represents, is how we avoid the reversal. There's a quieter implication too about how we should approach disagreements about data. Sometimes people argue about statistics because they're looking at different levels of aggregation. One person points to overall rates and draws one conclusion. Another person points to subgroup comparisons and draws the opposite conclusion. Without understanding Simpson's paradox, this looks like one person must be wrong or manipulating the data. But both might be accurately describing real patterns in the same dataset, just at different levels of aggregation. The disagreement isn't about facts, but about which level of aggregation answers the relevant question. Recognizing this can make these disagreements more productive. Instead of arguing about whose number is right, you can clarify what question you're trying to answer, whether the overall distribution matches the context you care about, and whether there's confounding that makes one level of analysis more appropriate than another. Simpson's paradox also has something to teach about fairness and evaluation. When we evaluate people, programs, or institutions based on outcomes, we're often calculating overall statistics, overall success rates, overall performance metrics, overall achievement levels. But if different entities face different distributions of difficulty, different starting populations, different baseline challenges, those overall statistics might be deeply unfair. They might punish the entity that took on harder cases, or reward the entity that cherry-picked easier circumstances. Fair evaluation requires either comparing entities that face equivalent populations, or adjusting for population differences, or at minimum, acknowledging that overall outcome differences might reflect population differences rather than performance differences. Simpson's paradox makes this vivid. It shows that you can literally be the best performer in every context and still have the worst overall statistics if you face a worse distribution of contexts. As we come toward the end of thinking about this paradox, it's worth stepping back and seeing it as part of a larger pattern in how we understand quantitative evidence. Simpson's paradox is one of several ways that statistical relationships can surprise us, can violate our intuitions, can show patterns that feel impossible until you understand the mechanism. There are other paradoxes and surprising results in statistics: regression to the mean, the base rate fallacy, Bergson's paradox, and many others. What they share is that they reveal the gap between mathematical truth and intuitive interpretation, between what the numbers say and what we think they mean. This gap exists because our intuitions evolved in simpler contexts, dealing with smaller amounts of information, where averages really did represent something like the typical case, and where combining evidence really did give you a clearer picture. But in a world of large datasets, complex systems, and heterogeneous populations, our simple intuitions can fail. We need to supplement intuition with careful thinking about statistical structure, about what creates patterns in data, about how aggregation and weighting work. This doesn't mean abandoning intuition. It remains valuable as a starting point and a check on whether our formal analyses make sense. But it means being willing to override intuition when the structure of the situation demands it, when the mathematics clearly shows that the intuitive answer is wrong. Simpson's paradox is a perfect example. Every instinct says that if treatment A is better in every subgroup, it must be better overall. But the mathematics shows this isn't necessarily true, and once you understand why, you can adjust your intuition to account for the role of distribution and weighting. The journey through Simpson's paradox, from initial confusion through understanding to eventual insight, mirrors a broader journey in statistical literacy. At first, statistics feels like it should be straightforward. You collect numbers, you calculate averages, you see what the data says. But as you go deeper, you discover layer after layer of subtlety. You learn about sampling variability and why small samples can mislead. You learn about confounding and why correlation doesn't prove causation. You learn about selection bias and why who's included in your data matters enormously. You learn about Simpson's paradox and why the level of aggregation shapes the relationships you observe. Each layer adds complexity, but also adds clarity. You develop a more nuanced understanding of what data can and can't tell you, of what different statistics mean, of how to interpret quantitative evidence responsibly. Simpson's paradox sits at an interesting position in this landscape. It's not about random variation or uncertainty. The reversal can appear even with infinite sample sizes and perfect measurements. It's not about causation versus correlation. The paradox can affect both. It's specifically about aggregation and distribution, about how combining data from different contexts creates weighted averages that might not represent any of the underlying contexts. This makes it particularly relevant in our current era of big data and comprehensive metrics, where the temptation is always to aggregate everything, to combine all available information into single summary statistics. Simpson's paradox warns that more data, combined thoughtlessly, can obscure truth rather than reveal it. And yet, despite all these warnings and complications, there's something ultimately optimistic about understanding Simpson's paradox. It shows that statistical confusion, even statistical reversals, can be understood and explained. It demonstrates that what looks paradoxical becomes clear once you understand the underlying mechanism. It proves that careful thinking about data structure can prevent misinterpretation. The paradox isn't a reason to distrust statistics. It's a reason to think more carefully about statistics, to look beneath overall numbers, to ask about distribution and context, to match the level of analysis to the question you're actually trying to answer. There's also something satisfying about the paradox's resolution. The mystery disappears completely once you see how weighted averages work, once you trace through the arithmetic of combining groups with different sizes and different baselines. You can literally watch the reversal happen step by step, seeing exactly how the larger group dominates the overall average and pulls it away from the pattern you saw in each subgroup. There's no magic, no contradiction, no violation of logic, just mathematics operating exactly as it should, revealing that our intuition about what overall means was too simple. The overall average isn't somehow above or beyond the subgroup averages, isn't a purer truth that transcends the details. It's a specific calculation with specific properties, and those properties include being heavily weighted toward larger groups and being sensitive to baseline differences across groups. As you let all of this settle, as you imagine encountering statistics in your own life, or work with this understanding in mind, there's a new kind of attentiveness that Simpson's paradox cultivates. When you see an overall comparison, you find yourself wondering what subgroups might exist within this data. Are they distributed evenly across the comparison groups or unevenly? Might the overall difference reflect who ended up where, rather than which option is actually better? This isn't paranoia or excessive skepticism, it's appropriate caution, a recognition that aggregation is a choice with consequences. Sometimes that choice is exactly right, and the overall statistic tells you what you need to know. But sometimes the choice obscures what matters, and you need to look more carefully at the structure beneath the summary. The paradox also encourages a particular kind of intellectual honesty in how we present and interpret data. If you've calculated an overall statistic and discovered that it reverses when you look at subgroups, you have a responsibility to explain this. You can't just present the overall number that supports your preferred conclusion and ignore the subgroup patterns that contradict it, any more than you can ignore the overall pattern and cherry-pick favourable subgroups. The honest approach is to present both, to explain the reversal, to discuss what creates it, and to help people understand which comparison is more relevant for the decisions they face. This transparency is harder than just presenting a single number, but it's what responsible data analysis requires when Simpson's paradox appears. In the end, Simpson's paradox is a story about humility, about recognizing that our intuitions about aggregation can fail, that simple summaries can mislead, that more comprehensive statistics aren't always better statistics. It's a reminder that every number is embedded in structure, that every average reflects choices about what to include and how to weight it, that truth depends on asking the right question and analysing at the appropriate level. The world is layered, not flat. Context matters. Distribution shapes outcomes. And sometimes to see clearly, you need to resist the temptation to collapse everything into a single overall statistic and instead maintain the distinctions that make comparisons meaningful. But it's also a story about understanding, about how what seems impossible becomes inevitable once you see the mechanism, about how careful thinking can resolve confusion, about how mathematical literacy can protect you from being misled. Simpson's paradox isn't a reason to despair about our ability to learn from data. It's an invitation to learn more carefully, to look more deeply, to think more clearly about what our statistics actually mean. The reversal stops feeling like a paradox and starts feeling like a natural consequence of how weighted averages behave when weights are uneven and contexts differ. This understanding doesn't eliminate the challenge of interpreting data well. That remains hard work requiring judgment and care, but it gives you tools for that work, specific things to check for, specific questions to ask, specific ways that aggregation can mislead and how to protect against them. The final comfort in understanding Simpson's paradox is the clarity it brings to situations that might otherwise feel hopelessly confusing. When you encounter contradictory statistics, when overall trends disagree with subgroup trends, when different analyses of the same data reach opposite conclusions, Simpson's paradox gives you a framework for understanding what's happening. You can check whether it's a distribution issue, whether different levels of aggregation are answering different questions, whether confounding is creating the contradiction. This doesn't automatically resolve every disagreement or make every decision easy, but it replaces confusion with comprehension. You understand why the reversal happens. You know what to look for. You can figure out which statistic answers your actual question. The paradox that once seemed impossible now seems natural. The reversal that once seemed paradoxical now seems like an expected consequence of combining data with particular structural properties. And so, we arrive at a quiet understanding. Numbers don't speak for themselves. Aggregates aren't automatically trustworthy. And overall doesn't always mean most accurate. Simpson's paradox teaches that clarity requires looking beneath the surface of summary statistics, understanding the distribution and structure that creates them, and matching the level of analysis to the question you need answered. The reversal between subgroup trends and overall trends isn't a failure of mathematics or a flaw in the data. It's a natural consequence of how weighted averages work when applied to heterogeneous groups with uneven distributions. Once you see this, really see it, and understand it, you're less likely to be fooled by misleading aggregates. You develop an instinct for asking about subgroups, for thinking about distribution, for questioning whether the overall number is actually answering your question or confounding it with something else. This understanding doesn't make data interpretation easy, but it makes it clearer. It gives you something specific to watch for, a known pattern of how things can go wrong, and tools for checking whether that pattern is present in data you encounter. Simpson's paradox moves from being a confusing impossibility to being an expected structural feature of certain kinds of data, something you can recognize and account for, something that no longer has the power to mislead you because you understand exactly how the reversal works and what it means. That's the gentle landing. The paradox resolved not by solving an equation but by understanding a principle, by seeing through the surface contradiction to the clear mechanism beneath, by developing the patience to look at structure rather than just accepting the first overall number you're given. The lesson settles quietly. Respect the context, understand the distribution, ask the right question, and the paradox dissolves into simple, clear insight about how weighted averages behave in a layered world. Before we descend into the darkness, I want to ask a favour. If you enjoy this story, please use your hype points on this video. It helps the channel more than you possibly know. If you're listening on Spotify, leaving a review makes a massive difference. And if you'd like, comment what time it is and where in the world you're listening from. We absolutely love seeing where everyone is tuning in. And of course, if you enjoy the content, consider subscribing. Now let's begin. There are two boxes sitting in front of you. One is transparent, made of clear plastic or glass, and you can see exactly what it contains. A modest sum of money, perhaps $1,000, neatly stacked and visible. The other box is opaque, solid and closed, impossible to see through. You have no idea what might be inside it, if anything at all. You are presented with a simple choice. You can take only the opaque box, walking away with whatever it contains, or you can take both boxes, claiming both the visible money and whatever might be hidden in the sealed container. On the surface, this seems like a straightforward decision, the kind of choice that should have an obvious answer. After all, more is better than less, and taking both boxes would seem to guarantee you at least a visible amount, plus potentially more. But this scenario, known as Newcomb's paradox, is anything but straightforward, and the more carefully you think about it, the more deeply puzzling it becomes. The setup is deliberately clean and minimal. There are no trick doors, no sleight of hand, no hidden complications in the physical arrangement. The transparent box sits there with its contents on full display. The opaque box sits beside it, sealed but not locked, ready to be opened. The choice is yours to make freely, with no time pressure, no one forcing your hand. You can walk up, examine both boxes as long as you like, and then decide. Take one or take both. That's all there is to the mechanical aspect of the problem. The simplicity is important because it means the paradox doesn't arise from confusion about what's happening physically. The boxes are just boxes. The money is just money. The action of taking one or both boxes is as simple as reaching out your hand. Everything about the physical setup is completely ordinary. But there is one element that transforms this simple choice into something profound, something that has puzzled philosophers, mathematicians, and decision theorists for decades. Before you arrived at this decision point, Before you even knew about these boxes, someone made a prediction about what you would choose. This predictor, whether it's a person, a computer, or some other entity, studied you carefully. Perhaps it examined your past decisions, your personality, your stated principles about rationality and choice. Perhaps it ran psychological tests, or scanned your brain, or simply observed you in similar situations. The method doesn't matter as much as the result. This predictor has demonstrated, time and time again, an extraordinary ability to forecast what people will choose in exactly this scenario. Let's say it has been correct in 99 out of every 100 previous cases, or perhaps even more often than that. Its track record is not perfect, but it is extremely, remarkably good. Here is where the scenario takes its crucial turn. The predictor made its forecast about your choice before you arrived, and based on that forecast, it filled the boxes accordingly. If the predictor determined that you would take only the opaque box, choosing to one box as the terminology goes, then it placed a large sum of money inside that box. Let's say it placed $1 million there, a life-changing amount that dwarfs the $1,000 visible in the transparent box. If, however, the predictor determined that you would take both boxes, that you would two-box, then it left the opaque box completely empty. It placed nothing inside at all. The predictor made this decision and sealed the boxes before you arrived. By the time you're standing there making your choice, the contents are already determined. The money is either sitting in the opaque box right now, or it isn't. Your future action cannot reach backward in time to change what the predictor already did. The past is fixed, settled, done. And yet somehow, what you are about to choose now determined what the predictor did then. Not in any mystical or magical sense, but in the straightforward sense that the predictor's job was to forecast your choice, and it filled the boxes based on that forecast. If you are the sort of person who will take only one box, then the predictor, being highly accurate, very likely predicted that and put the $1 million in for you. If you are the sort of person who will take both boxes, then the predictor, being highly accurate, very likely predicted that and left the opaque box empty. The contents of the boxes right now, before you make your choice, depend on what the predictor thought you would do, and the predictor based its judgment on who you are and how you make decisions. So in a strange indirect way, what you will choose has already shaped what is in front of you, even though the choosing hasn't happened yet, and the box filling happened in the past. This is the heart of the paradox, the reason it feels so deeply strange. The contents are fixed now, unchangeable by anything you do next. You cannot causally influence what happened before you arrived. That would violate our basic understanding of how time and causality work. Actions now affect the future, not the past. And yet, the predictor's accuracy means there is an extremely strong correlation between what you choose and what you get. One boxers walk away wealthy almost every time. Two boxers walk away with only the small visible amount. Or in the version where the visible amount is zero, they walk away with nothing at all. The statistics are clear. The pattern is undeniable. The predictor's accuracy makes your choice highly predictive of your outcome, even though your choice comes after the boxes were filled. This creates a genuine tension between two ways of thinking about rational choice, two different intuitions about what you should do, and both of them feel compelling. Each approach uses perfectly valid reasoning. Each one seems to lead inevitably to its conclusion. And yet they recommend opposite actions. That is what makes this a paradox in the technical sense, not just a puzzle with a tricky answer, but a situation where two valid modes of reasoning collide and cannot both be right. Yet neither one seems to contain an obvious error. Let's start with the reasoning that says you should take both boxes. This is often called causal decision theory, or the dominance approach, and it follows a particular kind of logic that many people find immediately convincing. The reasoning goes like this. Right now, at this very moment, the opaque box either contains $1 million or it contains nothing. That fact is already settled. The predictor made its choice, sealed the boxes, and walked away. Nothing you do now can change what is inside that box. Your action, whatever it is, will unfold after the contents have been determined. There is no causal pathway running backward in time from your hand reaching toward the boxes to the earlier moment when the predictor filled them. Causation flows forward, not backward. Therefore, the contents are fixed, independent of your current choice. Given that the contents are fixed, let's consider the two possibilities. First possibility, the opaque box contains the $1 million. If that's the case, then you have a choice between taking only that box, which gives you $1 million, or taking both boxes, which gives you $1 million plus the 1,000 in the transparent box. Taking both is clearly better. You get everything you would have gotten by one boxing, plus an additional 1,000. Second possibility, the opaque box is empty. If that's the case, then you have a choice between taking only that box, which gives you nothing, or taking both boxes, which gives you the 1,000 in the transparent box. Again, taking both is clearly better. You get something instead of nothing. So regardless of which possibility is actually true, regardless of what the predictor did, taking both boxes gives you a better outcome than taking only one. This is called a dominance argument. One action dominates another if it gives you at least as good an outcome in every possible state of the world, and a strictly better outcome in at least one state. Here, two boxing dominates one boxing. In the world where the opaque box is full, two boxing gets you more. In the world where the opaque box is empty, two boxing gets you more. There is no possible state of affairs where one boxing comes out ahead. The transparent box is sitting right there, money visible, yours for the taking. Why would you ever leave free money on the table? The box isn't booby-trapped. Taking it doesn't cause the other box to empty. The contents were determined before you arrived. Leaving that guaranteed money behind seems irrational, a needless sacrifice that gains you nothing. This reasoning feels solid. It respects causality. It treats the world as it is at the moment of decision. It doesn't get distracted by correlation or statistical patterns. It focuses on the straightforward fact that at decision time, taking both boxes cannot be worse than taking one, and will definitely be better if the opaque box happens to be full. Many people hear this argument and find it completely convincing. It seems to capture something fundamental about rational choice. When faced with options, choose the one that gives you the best outcome, no matter what state the world is in. That's what two boxing does. It's the safe, rational, obviously correct choice according to this way of thinking. But now consider the other side, the reasoning that says you should take only the opaque box. This approach, often associated with evidential decision theory or causal decision theory's rivals, focuses on a different aspect of the situation. It says yes, the contents are already determined, but that doesn't mean the correlation between your choice and those contents is irrelevant. In fact, that correlation is the most important thing to pay attention to. Look at what actually happens to people in this scenario. People who choose one box walk away with $1 million almost every time. People who choose both boxes walk away with just $1,000 or with nothing almost every time. That's not a coincidence. That's the predictor doing its job with extraordinary accuracy. The predictor is so good at its task that your type of choice, the kind of decision maker you are, is highly predictive of what's in the boxes right now. If you are the sort of person who reasons in a two-boxing way, who focuses on dominance and the fixed contents, then the predictor very likely saw that about you and left the opaque box empty. If you are the sort of person who reasons in a one-boxing way, who recognizes the correlation and acts on it, then the predictor very likely saw that about you and filled the opaque box with the million. Your decision process, your way of thinking about the problem, is part of the information the predictor used. The predictor didn't just flip a coin. It studied you. It modeled you. It figured out what kind of reasoner you are. So when you choose both boxes, you are not just making a choice about boxes, you are revealing something about yourself, something the predictor almost certainly already knew. You are revealing that you are a two-boxer, someone who follows dominance reasoning. And if the predictor knew that, it left the opaque box empty. Conversely, if you choose only the opaque box, you are revealing that you are a one-boxer, someone who follows evidential or correlation-based reasoning. And if the predictor knew that, it filled the box. The predictor's accuracy means that your choice is strong evidence about what's in the boxes, even though your choice happens after the filling. The correlation runs through what kind of person you are, not through any backward causation. From this perspective, the rational thing to do is to maximize your expected value given the predictor's accuracy. If the predictor is right 99% of the time, then one boxing gives you about a 99% chance of getting $1 million and a 1% chance of getting nothing. That's an expected value of $990,000. Two boxing gives you about a 99% chance of getting $1,000, which happens when the box is empty, plus the visible 1,000, and a 1% chance of getting $1,001,000, which happens in the rare case that the predictor was wrong, and you got lucky. That's an expected value of about $11,000. 990,000 is much, much larger than 11,000. One boxing is the clear winner in expected value terms. It's not even close. People who follow this reasoning point out that the dominance argument, while logically valid in the abstract, is missing something crucial about this particular scenario. Yes, taking both boxes would be better than taking one box if the contents were truly independent of your choice, but they aren't independent. They're highly correlated with your choice through the predictor's accuracy. Ignoring that correlation because it runs through something other than direct causation is a mistake. It's like ignoring the fact that smoking correlates with cancer just because you can't draw a simple causal arrow from this particular cigarette to your future diagnosis. The correlation matters. The predictor's accuracy matters. And if you ignore it, you will very likely walk away with much less money than you could have had. This reasoning also feels solid. It respects evidence. It pays attention to patterns and outcomes. It doesn't get caught up in abstract principles that lose sight of what actually happens. It focuses on the fact that, empirically, one boxers get rich and two boxers don't. Following a strategy that consistently leads to worse outcomes in the name of an abstract principle seems irrational, a stubborn refusal to adapt to the actual structure of the problem. Many people hear this argument and find it completely convincing. It seems to capture something fundamental about rational choice. When faced with options, choose the policy or strategy that reliably leads to the best outcomes. That's what one boxing does. It's the smart, adaptive, obviously correct choice, according to this way of thinking. And there we have the paradox in full. Two different chains of reasoning, each seemingly valid, each leading to opposite conclusions. The two boxing argument says the contents are fixed, causation doesn't run backward, and taking both boxes dominates taking one. The one boxing argument says the correlation is decisive, your choice is evidence about the contents, and one boxing maximizes expected value. Both arguments are internally consistent. Neither one contains an obvious logical flaw. They simply start from different premises about what matters for rational decision-making, and those different premises lead to different recommendations. This isn't just an academic disagreement about probability or game theory. It cuts to the heart of what we mean when we say a choice is rational. The two boxing view identifies rationality with following certain principles, like dominance, that are about the structure of outcomes at the moment of choice. The one boxing view identifies rationality with achieving good results in expectation, paying attention to all the information available, including correlations that run through the predictor. These are two different conceptions of what rationality is for, two different pictures of what a decision procedure should accomplish. The dominance principle has deep roots in how we think about choice. It says that if one option is better than another in every possible state of the world, then you should choose that better option. This seems almost tautological, a simple application of the idea that more is better than less. How could it be rational to choose something that is guaranteed to be worse than an alternative? The transparent box is right there. Its contents are guaranteed. Taking it cannot make the opaque box's contents change from what they already are. So why not take it? The only reason to refuse the transparent box would be if taking it somehow made the opaque box worse, but that's impossible given the timeline. The filling happened first, your choice happened second. Second things don't cause first things. But the evidential view points out that rationality isn't just about what happens in this one decision moment. It's about having a decision procedure, a way of reasoning that reliably gets you good outcomes across many situations. If you are in a world where predictors exist and are accurate, then being a two-boxer is a bad way to be. Two-boxers systematically get worse outcomes in Newcomb-like situations. They end up poorer, on average, than one-boxers. So even though at the moment of decision with the boxes already filled, two-boxing seems to dominate, it's the wrong kind of decision procedure to have. It's like being the kind of person who touches hot stoves. At the moment your finger is near the stove, you might reason that the burn has either already started or it hasn't, and touching the stove will give you information. But being the kind of person who touches hot stoves is still a bad way to be. You want to be the kind of person who avoids hot stoves. And similarly, you want to be the kind of person who one-boxes. The paradox becomes even sharper when we consider how prediction accuracy affects the situation. Suppose the predictor is only right 60% of the time, only slightly better than chance. In that case, the dominance argument looks much stronger. The correlation between your choice and the contents is weak enough that you might reasonably ignore it and just focus on taking both boxes to guarantee the visible money. The expected value calculation still favours one-boxing if we run the numbers, but not by as dramatic a margin, and many people would feel that the guaranteed extra 1,000 is worth taking. Now suppose the predictor is right 99.9% of the time, almost perfect. The correlation is now overwhelming. One-boxers get the million in 999 out of 1,000 cases. Two-boxers get only the 1,000, or nothing, in 999 out of 1,000 cases. The expected value difference is enormous. Nearly $1 million for one-boxing versus about 1,000 for two-boxing. At this level of accuracy, the dominance argument starts to feel like missing the forest for the trees. Yes, technically, at the moment of decision, the contents are fixed, and you could argue for taking both. But you'll almost certainly regret it, because you'll almost certainly be a two-boxer facing an empty, opaque box. The paradox lives in this space where prediction accuracy is very high but not quite perfect. If the predictor were literally perfect, always right, never wrong, then even dominant-style reasoning might have to concede. With a perfect predictor, being a two-boxer means you will definitely face an empty, opaque box, and being a one-boxer means you will definitely face a full one. The correlation becomes absolute, and the idea that the contents are independent of your choice becomes harder to maintain. You might start to think of the predictor as so accurate that it's effectively setting up a different problem for each type of reasoner, and in that problem, one-boxing clearly wins. But if the predictor is literally perfect, we have to ask how that's possible. How can any predictor know with absolute certainty what you will freely choose before you choose it? This starts to bump up against questions about determinism and free will. If the predictor can be certain, does that mean your choice is determined, not genuinely free? And if it's determined, does the whole notion of rational choice collapse? We'll come back to these questions, but for now, the important point is that Newcomb's paradox is at its most paradoxical when the predictor is extremely good, but not necessarily perfect. Good enough that the correlation is too strong to ignore, but not so perfect that we're forced into uncomfortable metaphysical territory about whether choice is even possible. This leads to a deeper realization. The disagreement between one-boxing and two-boxing isn't really about the scenario itself. It's about what kind of decision theory you're using, what framework you're applying to evaluate choices. Decision theory is the formal study of how to make rational choices, and it turns out there are multiple competing theories, each with its own principles and recommendations. Newcomb's paradox is a case where these theories diverge sharply, where they tell you to do opposite things, and that divergence reveals that they are based on fundamentally different ideas about what rational choice means. Causal decision theory, the framework that supports two-boxing, says that rational agents should evaluate actions based on their causal effects. When you choose an action, you should think about what that action will cause to happen, and choose the action that causes the best outcome. In Newcomb's problem, taking both boxes doesn't cause anything bad to happen. The opaque box's contents are already determined, so your choice can't cause them to change. Taking the transparent box causes you to have more money than you would have had without taking it. Therefore, causally speaking, taking both boxes is better. This theory explicitly sets aside correlations that don't represent causal influence. The fact that two boxes tend to find empty boxes is a correlation, yes, but it's not a causal effect of the choice to take both boxes. The causation runs the other way. The predictor's judgment causes both the box filling and, in some sense, the choice itself by modelling what you will do, but your choice doesn't cause the box filling, so you should ignore that correlation when deciding. Evidential decision theory, one of the frameworks that supports one-boxing, says that rational agents should evaluate actions based on what they indicate about the state of the world. When you choose an action, you should think about what that action is evidence for, what it tells you about which possible world you're in, and choose the action that is evidence for being in the best world. In Newcomb's problem, choosing only the opaque box is strong evidence that you're in the world where the predictor filled it with $1 million. Choosing both boxes is strong evidence that you're in the world where the predictor left the opaque box empty. So evidentially speaking, one-boxing is better. This theory explicitly includes correlations even when they don't represent direct causal influence. The fact that one-boxers tend to find full boxes is evidence about what your choice indicates, and you should act on that evidence. There are other decision theories too, variations and hybrids, that try to handle different problems. Functional decision theory, for instance, tries to evaluate actions as instances of a decision, algorithm, or policy, asking what would happen if everyone using your type of reasoning chose this way. In Newcomb's problem, it also recommends one-boxing, because the policy of one-boxing reliably produces better outcomes when facing accurate predictors. Updateless decision theory takes a similar approach, but frames it in terms of committing to policies before you have certain information. These theories are attempts to capture intuitions that causal decision theory might miss while still maintaining rigorous formal frameworks. But the key insight is that these are different theories. They're not just different names for the same thing. They encode different values about what rationality requires. Causal decision theory values making choices that cause good outcomes, focusing on the forward-looking, future-directed effects of your actions. Evidential decision theory values making choices that are correlated with good outcomes, focusing on what your actions reveal about the situation you're in. Both of these seem like reasonable things to value. Both of them are, in some sense, trying to capture what it means to choose well, and yet they conflict in Newcomb's problem. This reveals something profound about rational choice. It's not a simple, obvious notion with one clear answer. Different formalizations of rationality can give different recommendations. The project of decision theory is ongoing precisely because these hard cases exist, situations where our intuitions pull in different directions and where different formal frameworks diverge. Newcomb's paradox doesn't just present a puzzle to solve. It presents a choice between different conceptions of what rationality is, and there's no higher authority to appeal to, no super rationality. That tells us which conception is the right one. We have to decide what we value in a decision procedure, what we want rationality to accomplish. And that choice itself isn't obviously rational or irrational. It's more like a foundational commitment, a stance we take about how to engage with decisions. Some philosophers have tried to find ways to make the paradox less sharp, to find considerations that might favour one side without requiring such deep commitments. One argument says that even causal decision theorists should one-box if they accept that the predictor is accurate enough. The idea is that your reasoning process itself might be part of the causal chain. If the predictor studied your brain or your past decisions, then your current neural states or decision patterns are causing your choice, and those same states were accessible to the predictor. So there is a kind of common cause. Your decision-making apparatus causes both your current choice and the predictor's past prediction. In that case, choosing both boxes is evidence that your decision-making apparatus is in a state that caused the predictor to leave the opaque box empty, and you should avoid being in that state. But this argument is tricky because it requires accepting that your decision-making apparatus, rather than your choice itself, is the causally relevant thing. It's not that choosing both boxes causes the opaque box to be empty. It's that being the kind of decision-making system that will choose both boxes causes the predictor to leave it empty. This is a subtle shift, and not all causal decision theorists accept it. Some insist that, at the moment of decision, the state of your brain is what it is. The boxes are already filled, and the question is just what action to take given all that. Your action still can't reach back to change the past, even if your brain states can be seen as causing both the past prediction and the current action. Another consideration that sometimes comes up is that in realistic scenarios, you might not be certain about the predictor's accuracy. Maybe you've heard it's very good, but you haven't personally verified the statistics. Maybe there's some chance the whole thing is a trick, and the boxes are being manipulated in some other way. If you're uncertain about the predictor's accuracy, then you have to weigh the possibility that it's highly accurate, in which case one boxing is better, against the possibility that it's not very accurate or is working differently than claimed, in which case two boxing might be better. Your choice would then depend on your credence in the predictor's accuracy and how you weigh the different possible situations. But this doesn't resolve the paradox so much as change the problem. If you're highly confident the predictor is accurate, you're back to the original paradox. And even if you're not certain, you still face a choice between decision theories. Do you use causal reasoning, where you focus on what your current action causes, or evidential reasoning, where you focus on what your current action is evidence for? The uncertainty about the predictor just adds another layer. It doesn't eliminate the core tension. There's also the question of whether you can genuinely choose freely if a predictor can forecast your choice with high accuracy. This is where Newcomb's paradox starts to touch on deep questions about free will and determinism. If the predictor can know what you will choose before you choose it, does that mean your choice is predetermined? Is it still meaningful to talk about what you should do if what you will do is already set? These are ancient questions, debated by philosophers for millennia, and Newcomb's paradox doesn't settle them. But it does illuminate them in an interesting way. The paradox doesn't require that your choice is predetermined in any strong metaphysical sense. It only requires that your choice is predictable, given enough information about you. The predictor doesn't need to consult the fundamental laws of physics and calculate the exact trajectory of every particle in your brain. It just needs to know you well enough, to have a good enough model of how you think, to forecast what you'll do with high accuracy. This kind of predictability is compatible with most notions of free will. You can freely choose, in the sense that the choice is yours, it flows from your values and reasoning. Nothing is forcing you against your will, and yet the choice can still be predictable. If someone knows your values, your reasoning patterns, your past behaviour, they can often predict what you'll do. Not with perfect certainty, but with reasonable confidence. We do this all the time in ordinary life. You can predict that your friend will order coffee, not tea, because you know their preferences. That doesn't mean your friend isn't freely choosing the coffee. It just means their choice is predictable, given what you know about them. Newcomb's predictor is just an extreme version of this ordinary predictability. It's very, very good at modelling people, good enough that its predictions are right 99 times out of 100 or better. But it's still fundamentally doing what we do when we predict each other's behaviour, taking information about someone and using it to forecast their choices. The forecast doesn't make the choice any less real or less free in the relevant sense. It just makes the choice less surprising. Still, there's something psychologically uncomfortable about being predicted so accurately. It can feel like your choice doesn't really matter, like the outcome was determined before you even started thinking about it. This discomfort is part of what makes the paradox so engaging. It puts you in a position where you have to confront the relationship between your decision-making and the world around you. Your reasoning process, which feels internal and private, has been observed, modelled, anticipated. The world has been shaped in response to what you were going to do before you did it. That can feel unsettling, even if it doesn't actually threaten free will in any technical sense. Some people respond to this discomfort by rejecting the scenario as unrealistic. They say no predictor could be that accurate in practice, so the paradox is just a fantasy, not something we need to worry about. But this misses the point of thought experiments. Newcomb's paradox isn't meant to describe a situation you'll actually face. It's meant to isolate certain features of decision-making and push them to an extreme to see what happens. The predictor's high accuracy is a stipulation that creates a clean test case for different decision theories. Whether such a predictor could exist in reality is interesting, but it's separate from the question of what you should do if such a predictor did exist. And actually, while perfect or near-perfect predictors might not exist, we do encounter situations with somewhat similar structure. Anytime someone knows you well enough to predict your behaviour, anytime you're making a choice that will be evaluated by someone who has studied you or your type, you're in a weak version of Newcomb's problem. Job interviews, negotiations, strategic games where your opponent can model your thinking, all of these have elements of the same structure. The other party's decision about how to treat you may depend on what kind of person they think you are, which is revealed by what you choose, even though their decision happens before or simultaneously with your choice. Consider a simpler example that captures some of the flavour. You're asked whether you would betray a friend for money. Before you answer, you're told that people who say they wouldn't betray their friend will be given $1,000 because they're trustworthy, and the questioner wants to reward trustworthiness. People who say they would betray their friend will be given nothing because they're untrustworthy. What do you say? If you say you wouldn't betray your friend, you're more likely to get the money because trustworthy people are being rewarded. But if you're only saying it to get the money, are you actually trustworthy? The questioner is trying to predict your real character, and your answer is evidence about that character. This isn't exactly the same as Newcomb's paradox, but it has a similar feel. Your choice is both free and also evidence about the kind of person you are, and the outcome depends on that evidence. In game theory, there are situations where players face similar tensions. If you're playing a game against an opponent who can model your thinking, you have to consider not just what action produces the best outcome given the current state, but what action you would want to be known for taking, because your opponent's strategy might depend on what kind of player you are. Being the kind of player who always defects in a prisoner's dilemma gets you short-term gains in any single round, but if your opponent can predict that about you, they'll defect too, and you'll both lose. Being the kind of player who cooperates, if that's predictable, can lead to mutual cooperation and better outcomes for both. This is related to the concept of reputation and commitment in strategic settings. So while Newcomb's exact scenario might be fantastical, the underlying structure, choices where the outcome depends on what your choice reveals about you, where prediction and decision interact, is not entirely alien to real life. The paradox takes this structure and makes it stark, clear, unavoidable, forcing us to think carefully about principles that we might otherwise gloss over in messier, more complicated real-world situations. Let's think more carefully about how different levels of predictor accuracy change the problem. Suppose the predictor is right only 51% of the time, just barely better than a coin flip. In this case, there's almost no correlation between your choice and the contents. You might as well ignore the predictor and focus on the dominance argument. Taking both boxes seems clearly better because the predictor's judgment is nearly worthless as information. The expected value calculations would still technically favour one boxing by a tiny margin if we use evidential reasoning, but that margin would be so small that it would be swamped by any tiny uncertainty or practical consideration. Most people, even committed one boxers, would probably two box in this case. Now suppose the predictor is right 70% of the time. This is better, but still not overwhelming. Two boxers would get $1,000 70% of the time, plus $1,001,030% of the time when the predictor is wrong. One boxers would get $1 million 70% of the time, and nothing 30% of the time. The expected values are starting to diverge more clearly with one boxing ahead, but the dominance reasoning still has some intuitive pull. You might think the correlation is notable, but not decisive. At 90% accuracy, the pattern becomes hard to ignore. 9 out of 10 one boxers get the million. 9 out of 10 two boxers get just the 1,000 or nothing. The expected value difference is large. One boxing looks like the smart bet from a statistical standpoint, but the dominance argument still applies. The contents are still fixed, your choice still can't change them, and taking both still guarantees you don't leave money on the table in the moment. At 99% accuracy, as we've discussed, the correlation is overwhelming. At 99.9%, it's nearly absolute. The higher the accuracy, the sharper the paradox becomes, because the harder it is to dismiss the correlation as mere noise or coincidence. With very high accuracy, saying you should ignore the correlation and focus on dominance starts to sound like refusing to learn from experience, like insisting on a principle that systematically makes you worse off. But here's an interesting twist. The paradox doesn't actually get easier as accuracy increases. In some ways, it gets harder. With moderate accuracy, you might reasonably say the predictor is good, but not good enough to override dominance reasoning. With very high accuracy, you can't say that, but you face a different problem. How is such high accuracy even possible if your choice is genuinely free and not predetermined? The better the predictor is, the more it seems like your choice must be fixed in advance, at least in principle, even if you don't feel like it is. And if it's fixed in advance, then the whole framing of the problem becomes strange. Are you really choosing, or are you just discovering what you are always going to choose? This is where the paradox connects to questions about determinism. Determinism is the view that the present state of the universe, plus the laws of nature, fully determine the future state. If determinism is true, then in principle, a sufficiently knowledgeable predictor could know what you will choose by calculating forward from the present state. The predictor wouldn't need to violate causality or use magic. It would just need to have complete information about the current state and perfect knowledge of the laws. In practice, this might be impossible due to chaos, quantum uncertainty, or sheer computational limits, but in principle, it would be possible. If you accept determinism, then a perfect predictor is at least conceptually possible, and Newcomb's paradox is just a scenario where such a predictor happens to exist. Your choice is determined, but you still make it. The choice is yours in the sense that it flows from your brain states, your values, your reasoning. It's just that those brain states were themselves determined by earlier states, reaching back in a causal chain. The predictor has access to information earlier in that chain and can calculate forward to see what you'll do. But if you reject determinism, if you think there's genuine indeterminacy in the world, whether from quantum randomness or libertarian free will or some other source, then a perfect predictor becomes more problematic. How could it know what you'll choose if your choice isn't fully determined by prior states? It might still be a very good predictor by using statistical patterns, heuristics, psychological models. It could be right 99% of the time without being able to predict you with certainty. But absolute perfection would be out of reach if there's real indeterminacy in your decision. Newcomb's paradox doesn't require us to settle whether determinism is true. The scenario works with a highly accurate but imperfect predictor, and such a predictor is plausible whether or not determinism holds. But thinking about the paradox does make you confront the relationship between prediction and choice, and it makes you think about what your choice is made of. If your choice flows from your character, your values, your reasoning style, then it makes sense that someone who knows those things could predict what you'll choose. And if they can predict it, does that mean it was determined all along? Or just that it was predictable, given who you are? These questions don't have simple answers, and they've been debated in philosophy for centuries without resolution. Compatibilists argue that free will is compatible with determinism, that you can be free as long as your actions flow from your own desires and reasoning, even if those desires and reasoning are themselves caused by earlier factors. Libertarians about free will argue that genuine freedom requires indeterminism, that your choices must not be fully determined by prior states. Hard determinists argue that if determinism is true, we don't have free will in any meaningful sense, and there are other positions, variations, and nuances beyond these. Newcomb's paradox doesn't prove any of these views right or wrong, but it does put pressure on certain assumptions. If you think free will requires that your choices be unpredictable, in principle, then a very accurate predictor seems to threaten free will. But if you think free will just means choosing according to your own reasons and values, then a predictor who knows your reasons and values can predict you without threatening your freedom. The paradox invites you to clarify what you mean by free will and what you think is necessary for it. There's also a social and psychological dimension to the discomfort people feel about being predicted. We like to think of ourselves as somewhat inscrutable, as having an inner life that others can't fully access. Being predicted very accurately can feel like being exposed, like someone has looked inside you and seen your machinery. It can feel reductive, as if you're less complex or less autonomous than you thought. This feeling isn't necessarily rational. Being predictable doesn't mean you're simple or lacking in autonomy, but it's a real part of how people react to scenarios like this. In real life, we sometimes resent people who know us too well, who can predict what we'll do or say. It can feel like they're not taking us seriously, like they've reduced us to a set of patterns. And there's a fear that if someone can predict you, they can manipulate you, using their knowledge of your patterns to get you to do what they want. The Newcomb predictor isn't trying to manipulate you in that sense. It's just filling boxes based on a forecast, but the fact that it can forecast your choice so accurately might still feel like a loss of autonomy, even if technically it isn't. Turning back to the decision theory questions, there have been many attempts to refine or extend the basic theories to handle Newcomb cases better. Some theorists have proposed that in certain situations you should act as if your choice can influence things it's correlated with, even if there's no direct causal link. This is sometimes called ratificationism, or could be seen as a version of super-rationality, the idea that truly rational agents might reason not just about their own actions, but about the pattern or policy they're instantiating. For instance, if you think of yourself not as choosing an isolated action, but as instantiating a decision algorithm, then you might ask, if everyone using my algorithm chose this way, what would happen? In Newcomb's problem, if everyone using your algorithm 1 boxes, they get rich. If everyone using your algorithm 2 boxes, they get only the small amount. So you should 1 box, because you're not just choosing for yourself in this moment, you're choosing which algorithm to run, and the 1 boxing algorithm reliably does better. This kind of reasoning appears in other contexts too. In the twin prisoner's dilemma, you and your twin are both offered the same choice, cooperate or defect. If you cooperate and your twin cooperates, you both get a good outcome. If one defects and the other cooperates, the defector does best and the cooperator does worst. If you both defect, you both do poorly. You're deciding in separate rooms with no communication, but you know your twin will reason the same way you do, because you're twins or psychological duplicates or whatever. Should you cooperate? Standard game theory says defect, because defection dominates cooperation, no matter what the other player does. But if you know your twin will reason identically, then your choice determines what your twin chooses. If you cooperate, your twin cooperates, and you both get a good outcome. If you defect, your twin defects, and you both do poorly. So cooperation seems better. This has a similar flavour to Newcomb's problem. Your choice is correlated with something you care about through a commonality in reasoning, even though your choice doesn't cause the other thing. Some decision theorists take these cases as evidence that we need a framework that goes beyond simple causal or evidential decision theory, something that can capture the idea of logical or algorithmic connections between decisions. Functional decision theory, which we mentioned earlier, is one attempt at this. It evaluates actions not just by their causal effects or their evidential implications, but by what would happen if the algorithm producing the action were instantiated in all relevantly similar situations. In Newcomb's problem, the 1 boxing algorithm is instantiated both in your decision and in the predictor's model of you. The outcome depends on what algorithm is running in both places, so you should 1 box. This is an interesting approach, and it has some attractive features. It gives consistent answers across a range of paradoxical cases, and it captures the intuition that rational agents should care about the outcomes they reliably produce, not just the causal effects of individual actions. But it also has some costs. It requires thinking about decisions in a somewhat abstract way, as instantiations of algorithms rather than just actions taken at moments. And it's not always clear exactly which situations count as relevantly similar for the purpose of evaluating algorithms. Still, it represents a serious attempt to move beyond the causal evidential debate and find a framework that handles these hard cases better. Another line of thought focuses on the notion of counterfactuals, statements about what would happen if things were different. When you're deciding whether to take both boxes, you might ask, what would happen if I took only 1 box instead? The causal decision theorist says the contents of the boxes would be the same as they actually are, because your choice now doesn't cause the past filling, so you'd be leaving money on the table. The evidential decision theorist says, if you're the kind of person who would take only 1 box, then the predictor probably filled it, so you'd probably get the million. The key difference is in how they think about the counterfactual. There are different theories of counterfactuals in philosophy, and they can give different answers about what would happen if you chose differently. Some theories say you should hold fixed the actual past, including the predictor's filling, and just vary your choice. Others say you should consider what would have happened in a whole scenario where you're the kind of person who makes a different choice, which might include the predictor making a different prediction. The choice of counterfactual theory can affect what you think you should do. This might sound like angels on pinheads territory, abstract philosophy with no practical import. But these questions about counterfactuals are actually central to how we reason about decisions in many contexts. When you think about what would happen if you did something different, you're implicitly using some theory of counterfactuals, some rule for imagining the alternative scenario. Different rules can lead to different decisions. Newcomb's paradox makes this vivid by creating a case where the stakes are clear and the different theories clearly diverge. It's worth stepping back and asking why this paradox has gotten so much attention from philosophers and decision theorists. It's not just because it's a fun puzzle, though it is that. It's because it sits at the intersection of multiple deep issues: the nature of rational choice, the relationship between causation and correlation, the meaning of free will, the role of prediction in shaping outcomes. It's a kind of stress test for theories of rationality, a case where different theories give different answers, and we have to think carefully about which answer seems right and why. Moreover, the paradox is clean. There's no hidden complexity, no ambiguity in the setup. The boxes are just boxes, the money is just money. The predictor is stipulated to be accurate to whatever degree we specify. This clarity is valuable because it means we can't resolve the paradox by finding some overlooked detail or reinterpreting the scenario. The tension is genuine, built into the structure of the problem. Any resolution has to come from choosing a decision theory or revising our intuitions, not from finding a trick. Different people have different intuitions about Newcomb's problem, and these intuitions seem to correlate with different philosophical temperaments. Some people immediately see the dominance argument and can't be shaken from it. The idea of leaving money on the table seems absurd to them, a clear violation of rationality. Other people immediately see the pattern of outcomes, the fact that one boxers get rich and two boxers don't, and can't understand why anyone would two box. Both groups feel like their position is obvious, like the other side is missing something simple. This divergence in intuitions is itself interesting. It suggests that people are implicitly using different frameworks for thinking about choice, different background assumptions about what matters. And often these frameworks are not explicitly articulated. People just have a gut feeling about what the right answer is, and they construct arguments to support that feeling. The paradox brings these implicit frameworks to the surface, makes them explicit, and shows that they conflict. There have been surveys of philosophers and decision theorists about what they would do in Newcomb's problem, and the results are mixed. Roughly speaking, opinions are divided, with perhaps a slight majority favouring one boxing, but a substantial minority favouring two boxing. This is unusual for a problem in decision theory. Normally, once a field has examined a problem carefully, a consensus emerges. The fact that experts remain divided about Newcomb's problem, even after decades of analysis, suggests that the paradox is touching on something genuinely unresolved, a point where our theories and intuitions haven't fully converged. Some philosophers argue that the paradox shows decision theory is broken or incomplete, that we need a better framework that doesn't give conflicting answers. Others argue that the paradox shows there are multiple legitimate notions of rationality, different goals or values a decision procedure might aim at, and we shouldn't expect them to always agree. Still others argue that one of the standard theories is right and the other is wrong, and the paradox helps us see which is which. There's no consensus on this meta-level question either. One interesting variant of the problem asks what you should do if you know how the predictor works. Suppose the predictor scans your brain, sees what you're going to choose, and fills the boxes accordingly. You know this is how it works. Does that change anything? You might think it doesn't. The contents are still fixed before you choose, the dominance argument still applies. But you might also think it does, knowing that the prediction is based on your actual neural states at the time of prediction makes the correlation even more direct, harder to dismiss. Or suppose the predictor shows you a recording of your future self, taken from a moment after you've made your choice, and uses that recording to decide how to fill the boxes. This makes the temporal loop even more explicit. The predictor is seeing the future to decide how to set up the past. If you can see your future self in the recording, and your future self took both boxes, does that mean you have to take both boxes because that's what you saw yourself doing? Or can you still choose differently and create a paradox? This variant pushes the scenario into science fiction territory, but it makes vivid the idea that your future choice is determining the present setup. These variants don't resolve the original paradox, but they explore its boundaries, testing which features are essential and which are incidental. The core of the paradox seems to be the combination of predictive accuracy and the temporal ordering. The predictor goes first, your choice comes second, but the predictor's action depends on your choice. As long as those elements are in place, the paradox remains. Let's consider the experience of actually facing this choice, trying to set aside our theoretical commitments and just think about what we would do. You're standing in front of the two boxes. The transparent one is right there, $1,000 visible inside it, real and tangible. The opaque one sits beside it, closed, unknown. You've been told the predictor is very accurate, right 99 times out of 100. You believe this. You've seen the statistics, met the previous participants, verified the track record. What do? If you reach for both boxes, taking the guaranteed 1,000 plus whatever might be in the opaque box, you're following the dominance logic. The contents are already set. You can't change them. Taking the extra 1,000 can't hurt. But as your hand moves toward the transparent box, you might feel a flicker of doubt. The predictor has been watching you, studying you, modelling you. It knows how you think. If you're the kind of person who reaches for both boxes, it probably knew that. And if it knew that, the opaque box is probably empty. You're probably about to take the 1,000 and discover the million was never there for you. Almost everyone who has felt this impulse to take both, who has reasoned this way, has ended up with only the small amount. You're probably going to be one of them. If instead you reach only for the opaque box, leaving the transparent one untouched, you're following the evidential logic. You're being the kind of person the predictor rewards. By leaving the guaranteed 1,000 behind, you're demonstrating that you're a one-boxer, and one-boxers are the ones who get the million. The predictor probably saw this about you too, probably filled the opaque box because it knew you'd make this choice. As you reach for the opaque box, you might feel confident that it contains the million because you're doing what leads to that outcome. But there's also a nagging voice. The 1,000 is right there. You're leaving it behind. If you're wrong about the predictor, if it made a mistake this one time, or if you've misunderstood the scenario, you're giving up a guaranteed 1,000 for nothing. The dominance argument still whispers in your ear. Why not just take both? This internal dialogue, this back and forth between the two arguments, is part of the paradox's grip on people. Neither argument is easy to dismiss once you've really understood it. The dominance reasoning has a kind of logical force, a feeling of inevitability. Of course you should take both boxes. What else could possibly make sense? But the pattern of outcomes reasoning has its own compelling quality, an empirical weight. Look at what actually happens to people. How can you ignore that? Some people report that their intuition flips back and forth as they think about the problem. They'll be convinced they should one box, then they'll think about the dominance argument and switch to two boxing. Then they'll remember the statistics and switch back. This instability is a sign of the genuine paradox. If there were a simple resolution, a clear mistake in one argument, people wouldn't keep oscillating. The fact that both arguments continue to exert a pull, even after careful analysis, shows that each one is capturing something important about rational choice. There's also a pragmatic question. If you actually face this scenario in real life, what would you do? Setting aside all the philosophy and decision theory, faced with real boxes and real money, what choice would you make? Some people say they'd two box because the dominance argument is too compelling to resist in the moment. Others say they'd one box because they trust the statistics and want to maximise their expected winnings. And some people say they honestly don't know, that they'd feel paralysed by the conflicting arguments. The pragmatic question is interesting because it can diverge from the theoretical question. You might think, as a matter of pure decision theory, that two boxing is rational, but you might also think that one boxing is the better bet in practice, given the predictor's accuracy. Or vice versa. You might think one boxing is theoretically rational, but find yourself unable to resist the transparent box in the moment. The tension between theory and practice, between what you think you should do and what you think you'd actually do, is another layer of the paradox. This connects to a broader issue in decision theory and philosophy of mind, the gap between normative and descriptive theories. Normative decision theory tells you what you should do if you're rational. Descriptive decision theory, or psychology, tells you what people actually do. These can come apart. People often violate the axioms of rational choice as defined by standard theories. We're subject to biases, framing effects, emotional influences. Newcomb's paradox is interesting partly because it's not clear which answer is normatively correct, even before we get to the question of what people would actually do. Let's think about a few more variants and related scenarios to further illuminate the structure of the paradox. One variant is the transparent Newcomb problem. Both boxes are transparent, so you can see what's inside before you choose. If the predictor put the million in the opaque box, you can see it sitting there. If it left the box empty, you can see that too. What do you do? This variant seems to collapse the paradox for most people. If you can see the million, obviously, you should take both boxes, getting the million plus the 1,000. If you can see the opaque box is empty, you should still take both boxes to get at least 1,000. The contents are visible, there's no uncertainty, and taking both strictly dominates. But wait, if the predictor is very accurate, and you can see the million in the opaque box, that means the predictor predicted you'd one box. But now, you're about to two box. Does that mean the predictor was wrong? How can that be if it's nearly perfect? This variant seems to create a paradox of its own, a kind of self-defeating prediction. If the predictor puts the million in the opaque box because it predicts you'll one box, but making the boxes transparent causes you to two box, then the predictor made a mistake. But the predictor doesn't make mistakes, or makes them very rarely. So maybe the predictor knew the boxes would be transparent, and predicted accordingly. If it predicted you two box once you saw the contents, it would have left the opaque box empty. In that case, you see an empty box and you two box, getting just 1,000, and the predictor was right. If it predicted you'd somehow force yourself to one box, even seeing the million sitting there, it would have filled the box, you'd one box, and the predictor was right. But this feels strange. Why would you one box if you can literally see the million sitting there in the opaque box? Just take both boxes and walk away with the million plus the 1,000. The only reason not to would be if taking the transparent box somehow made the million disappear. But it can't. You can see it right there, and it's not going anywhere based on your choice. The transparent variant seems to break the symmetry that makes the original paradox work. When you can see the contents, the dominance argument becomes overwhelming, and the evidential argument loses its force. Another variant. Suppose the predictor tells you what it predicted. It says, I predicted you would one box, so I put the million in the opaque box, and then it leaves you with the boxes. What do you do now? You know the million is there. The predictor has told you so, and the predictor is very accurate, so you can trust its claim. Should you still one box, or should you two box now that you know the million is there? This creates a different kind of tension. If you two box, you're acting inconsistently with the prediction, which might seem to show the prediction was wrong, but the contents are already set based on the prediction, so your action doesn't change them. You can safely two box and get both amounts. On the other hand, if the predictor is nearly perfect, it would have anticipated that you might two box upon being told the prediction, and it would have predicted accordingly. If it predicted you'd two box after being told, why would it have told you? Or maybe it predicted you'd stick to your one boxing decision, even after being informed, in which case it filled the box and expects you to one box. This variant introduces issues of belief and knowledge into the scenario. In the original setup, you don't know what's in the opaque box, though you have strong probabilistic beliefs based on the predictor's accuracy. In this variant, you're given knowledge, or at least strong testimony. How that affects the decision depends on how you think knowledge interacts with decision-making, and whether learning the prediction should change your choice. There's also a version called the meta-Newcomb problem. Before the predictor fills the boxes, you're asked to commit to a decision strategy. You can commit to one boxing, commit to two boxing, or decline to commit. After you commit or decline, the predictor makes its prediction and fills the boxes, and then you make your actual choice. You're allowed to violate your commitment if you want, but the predictor knows you might do this and takes it into account. In this version, it seems clear you should commit to one boxing, because that makes it likely the predictor will fill the opaque box. Then, once the boxes are filled, should you stick to your commitment or violate it and two-box? If you violate it, you'll two-box and get both amounts, but the predictor probably anticipated you might do this. If the predictor is modelling you as someone who commits to one boxing, but then violates the commitment, it might have predicted two boxing and left the opaque box empty. On the other hand, if you're the kind of person who keeps commitments, even when it's tempting to break them, the predictor might have predicted you'd one box and filled the box accordingly. This variant highlights the role of commitment and consistency in decision-making. It also touches on issues of time inconsistency, cases where your preferences at one time conflict with your preferences at another time. Before the boxes are filled, you want to be the kind of person who will one box, because that gets the boxes filled favourably. After the boxes are filled, you're tempted to two box to get the extra amount. Managing this conflict requires either strong commitment mechanisms or a decision theory that evaluates policies across time rather than just actions at moments. Let's also consider what happens if there are multiple players. Suppose 100 people are all facing Newcomb's problem simultaneously, each with their own pair of boxes, each with a predictor that has studied them individually. Everyone makes their choice at the same time. What should you do? In this multiplayer version, your choice doesn't directly affect anyone else's boxes, so the basic structure of the problem is the same for you as an individual. But knowing that other people are facing the same choice might affect your reasoning. If you believe most people will two box, and the predictor knows this, then most opaque boxes will be empty. Does that tell you anything about your own box? Not directly. Your box's contents depend on the predictor's judgment of you specifically, but it might affect your confidence in the predictor's accuracy. If you see 99 people two boxing and finding empty boxes, that's strong confirmation that the predictor works. It might make you more confident you should one box. Alternatively, if you see people one boxing and getting rich, that confirms the predictor rewards one boxing, which might strengthen your resolve to one box. But if you see people one boxing and finding empty boxes, that suggests the predictor made mistakes, which might weaken your confidence in it. The multiplayer version introduces a social and evidential dimension. You're learning about the predictor's reliability from watching what happens to others. There's also an interesting question about whether you should coordinate with other players. If you could all agree to one box, you'd all likely get rich, but each individual has an incentive to defect from the agreement and two box once the boxes are filled. This is similar to a multiplayer prisoner's dilemma or a public goods game. The best collective outcome requires everyone to cooperate one box, but each individual might be tempted to defect. Two box. The predictor's accuracy adds a twist. If you defect, the predictor probably saw that about you and left your box empty. So even though defecting seems to be in your interest, it's actually a losing move. These variants and extensions show that Newcomb's problem is part of a broader family of decision scenarios where prediction, commitment, coordination, and time all interact in complex ways. The core paradox is cleanest in the simple two-box single-player version, but the same tensions appear in many related setups. This suggests the paradox is pointing at something fundamental about decision making, not just a quirk of one particular thought experiment. Thinking about Newcomb's paradox can also change how you think about other philosophical problems. For instance, the problem of evil in theology has some structural similarities. If God is omniscient, knowing all future choices, and if God set up the world in a particular way based on that knowledge, then the world's setup is correlated with our choices, even though the setup came first. This doesn't make Newcomb's paradox a solution to the problem of evil, but it shows that the interplay of prediction, choice, and temporal ordering appears in multiple contexts. Or consider debates about punishment and deterrence. If punishing a crime can't undo the crime, causally the crime already happened, why punish? One answer is deterrence. Punishing this crime makes future crimes less likely. But that's a forward-looking causal effect. Another answer is retribution. The person deserves punishment regardless of future effects. But there's also a Newcomb-like answer. Punishing is the right policy for a society to have, and being the kind of society that punishes is correlated with lower crime rates, even though the punishment of a particular crime doesn't cause that crime not to have happened. The structure is similar. An action that doesn't directly cause the outcome you want but is part of a policy or pattern that reliably produces good outcomes. Returning to the paradox itself, we might ask whether there's any way to definitively resolve it, to prove that one side is right and the other is wrong. The answer seems to be no, at least not without making substantive assumptions about what rationality means. If you assume rationality requires maximizing expected value based on all available evidence, then one boxing wins. If you assume rationality requires taking dominant actions based on causal effects, then two boxing wins. These are different conceptions of rationality, different values embedded in the decision procedure, and there's no neutral standpoint from which to judge between them. This might be unsatisfying. We want puzzles to have answers. We want to be able to say, here's the right choice, and here's why. But some puzzles are more like choices between frameworks than problems with solutions. Newcomb's paradox might be one of these. It asks you to decide what you value in a decision theory, what you want rationality to accomplish. Do you want it to follow certain structural principles, like dominance, even if that leads to systematically worse outcomes in some scenarios? Or do you want it to maximize expected value based on all correlations, even if that means treating your choice as evidence rather than just cause? Different people will answer this differently, and that's okay. The value of the paradox isn't in finding the one true answer. It's in understanding the question, in seeing the different ways we can think about choice and what trade-offs each approach involves. It's in recognizing that rational choice is not a simple, univocal concept, but something we have to define and refine based on what we care about. For someone trying to fall asleep, this might all seem abstract and cerebral, the kind of thing that would keep you awake rather than helping you drift off. But there's something oddly soothing about the paradox once you've sat with it. For a while, it's a clean, well-defined problem with a clear structure. There are no loose ends, no missing information, no ambiguities to resolve. The tension is real, but it's contained within the scenario. It doesn't threaten you in any practical way. You can think about it gently, turn it over in your mind, appreciate the symmetry of the two arguments without needing to force a resolution. The boxes sit there, one transparent and one opaque, waiting for a choice that is both free and predictable, both yours to make and already accounted for in the setup. The paradox asks you to think about what it means to choose well, to act rationally, to navigate a world where your decisions can be anticipated but are nonetheless real. It asks you to consider the relationship between cause and correlation, between the moment of choice and the pattern of outcomes over time, between following a principle and achieving a goal. And in the end, the paradox teaches a kind of humility about rationality. It shows that even in the simplest scenarios with just two boxes and a straightforward choice, The question of what you should do can be genuinely difficult, genuinely contested, genuinely open to multiple defensible answers. It reminds us that decision-making is not a mechanical process with obvious right answers, but a domain where our values, our principles, and our goals interact in complex ways, sometimes pulling in different directions, sometimes requiring us to make hard choices about what we care about most. The predictor has done its job, studied you carefully, made its forecast, filled the boxes. The setup is complete. The boxes sit before you, one box or two. The choice, as they say, is yours. And it is yours, genuinely and truly yours. Even if it was predicted, even if it was anticipated, even if the world was shaped in response to what you were going to do, the choice is yours. And in making it, you reveal not just what you decide in this moment, but something about how you think, how you reason, what you value when you choose. The predictor may know what you'll do, but you still have to do it. You still have to reach for one box or both, still have to commit to a way of thinking about decision and action and rationality. And in that reaching, in that commitment, you engage with questions as old as philosophy itself. What does it mean to choose? What does it mean to choose well? How should we act in a world that knows us better than we might like? A world that can predict us, anticipate us, shape itself around what we will do? These questions don't have final answers, but they have value in the asking. They make us think more carefully about decisions we face every day, about the relationship between our actions and our outcomes, about what we can control and what we can only influence through the kind of person we are. Newcomb's paradox is a gift in this way, a thought experiment that crystallizes these questions into a simple, elegant scenario, two boxes and a choice, and invites us to think deeply about what that choice reveals. As you lie there in the dark, perhaps drifting towards sleep, you can let the paradox settle into a comfortable shape in your mind. The two arguments, one boxing and two boxing, become familiar presences, each with its own logic, each pointing its own direction. You don't need to resolve them. You can let them coexist, two different ways of thinking about the same problem, two different values you might hold about decision-making. The tension between them is not a problem to be solved, but a feature of the landscape, a reminder that rationality is richer and more complex than any single principle can capture. The boxes remain transparent and opaque, seen and unseen, known and unknown, and the choice remains open, eternally poised between the dominance of more and the evidence of pattern, between the moment and the policy, between taking what's there and being what's rewarded. And in that openness, that eternal irresolution, there is a strange kind of peace. The peace of a question well posed, a problem clearly seen, a paradox that teaches without needing to be solved. The next story is about to begin. Please relax and enjoy. We spend much of our lives moving through the world with words that feel perfectly clear. When you say someone is tall, or that you waited a long time, or that there's a heap of laundry on the floor, the meaning seems obvious. These words let us communicate quickly, efficiently, trading descriptions back and forth without pausing to define every term. The convenience is remarkable when you think about it. How seldom we need to stop and ask, but what exactly do you mean by tall? We simply know, or we think we know, and the conversation continues. This smoothness depends on an assumption that lives quietly beneath our everyday language. The assumption that our words have boundaries, even if we never think about where those boundaries lie. Tall people exist on one side of some invisible line, and not tall people exist on the other. Heaps are heaps, and non-heaps are non-heaps. The categories feel stable because they work. You can look at a pile of sand and say, that's a heap, and someone else will probably agree with you. The agreement feels like confirmation that the word points to something real and definite in the world. But there's a moment, a particular kind of moment, when this comfortable certainty starts to wobble. It happens when you try to pin down exactly where one category ends and another begins. When does a person become tall? At what precise height does the shift occur? When does a pile of sand become a heap? After how many grains? These questions sound simple, almost silly, but they open a door to something genuinely puzzling, something that has fascinated philosophers for more than 2,000 years. The puzzle is called the Saurite's paradox, named after the Greek word sauros, which means heap. It's a paradox that doesn't require advanced mathematics or obscure knowledge. It emerges from the simplest observations about sand and piles and the words we use to describe them. And yet, once you see it clearly, it refuses to let go. The paradox begins with a statement that feels so obviously true that questioning it seems pointless. A single grain of sand is not a heap. If you placed one grain of sand on a table in front of you, you wouldn't look at it and think, there's a heap. The word heap implies volume, bulk, a collection of things gathered together in a noticeable way. One grain is just one grain, a tiny speck, barely visible if the lighting isn't right. There's no controversy here, no room for debate. Everyone agrees, one grain is not a heap. This starting point is important because the paradox depends on it. The argument needs a place to begin, a truth that seems unshakable, and this is it. One grain is not a heap. The simplicity is almost reassuring. It's the kind of statement that makes you feel like you're standing on solid ground, ready to reason clearly about whatever comes next. And what comes next is the step that makes the paradox possible. It's a step that also feels reasonable, perhaps even more reasonable than the first. The step is this: if you have something that is not a heap, and you add one grain of sand to it, it still isn't a heap. Think about that for a moment. If one grain isn't a heap, then surely two grains aren't a heap either. Adding one more grain to a single grain shouldn't be enough to transform a non-heap into a heap. The change is too small. One grain is so insignificant, so tiny in the grand scheme of things, that it can't possibly be the difference between two entirely different categories. This principle, that adding one grain can't turn a non-heap into a heap, feels intuitively correct because it matches our experience with small changes. In most areas of life, tiny increments don't flip switches. If you're poor and someone gives you a single penny, you don't suddenly become rich. If you're short and you grow 1 millimeter, you don't suddenly become tall. Small changes accumulate gradually, and categories seem to require more than just the smallest possible nudge. So the idea that one grain can't make the difference between a heap and a non-heap seems perfectly sensible. It's cautious, modest, and it respects the fact that one grain is genuinely very small. But here's where the paradox tightens its grip. If one grain is not a heap, and if adding one grain to a non-heap still leaves you with a non-heap, then you can keep going. You can add another grain. 2 grains plus 1 grain equals 3 grains, and 3 grains still aren't a heap. Add another, 4 grains, still not a heap. Add another, 5 grains, not a heap. Each step feels exactly like the previous step. Each time you add a grain, the change is minimal, barely perceptible. And if one grain never makes the difference, then no individual grain should ever make the difference. You can keep applying the same reasoning over and over, stepping forward one grain at a time, and the conclusion remains the same. Not a heap, not yet a heap, still not a heap. The process continues. 10 grains, 20 grains, 50 grains. None of them heaps apparently, because each one was reached by adding just 1 grain to something that wasn't a heap. 100 grains, 200 grains, 500 grains. At some point, you might start to feel uneasy. 500 grains of sand gathered together certainly starts to look like something. It has presence. It rises above the surface. You could scoop it up with your hand and feel its weight. But if the logic has been right all along, if one grain truly can't turn a non-heap into a heap, then even 500 grains shouldn't count as a heap. The reasoning that worked at the beginning should still work now. You keep going. 1,000 grains, 5,000 grains, 10,000 grains. Now the pile is visible from across the room. It has shape and volume. If someone asked you to describe what you are looking at, you might very naturally say, "It's a heap of sand." The word would come to you without effort. And yet, according to the logic you started with, this cannot be a heap, because you began with one grain, which was not a heap, and you added grains one at a time. And each time you added a grain, the result was still not a heap. If each step preserved the status of being a non-heap, then the final result, no matter how large, should also be a non-heap. This is the paradox. The premises seem true. One grain is not a heap, and adding one grain to a non-heap doesn't create a heap. The reasoning seems valid. If you apply a rule over and over, the conclusion should follow. But the final conclusion is absurd. Even 1,000,000 grains of sand piled together wouldn't be a heap. Yet heaps obviously exist. You can see them, touch them, shovel them. The logic seems to deny something that reality clearly affirms. You're left with a choice. Either reject one of the premises, reject the way the reasoning unfolds, or accept a conclusion that contradicts everyday experience. None of these options feels comfortable. What makes the Sorites paradox so enduring, so quietly unsettling, is that it doesn't point to a mistake in arithmetic or a flaw in some technical procedure. The paradox emerges from the way ordinary language works, or more precisely, from the way ordinary language meets the demands of strict logical reasoning. The real issue, the thing under pressure, isn't the sand, it's the word heap. And by extension, it's all the words like heap, words that describe the world without drawing exact lines. The word heap is what philosophers call a vague term. Vagueness here doesn't mean unclear or poorly defined in the sense of sloppy thinking. It means that the word functions perfectly well in normal conversation without requiring precise boundaries. You don't need to know the exact number of grains that constitutes a heap in order to use the word correctly. If someone says, "There's a heap of sand in the garage," you understand them. You picture something substantial, a noticeable pile, and that's enough. The vagueness is a feature, not a bug. It allows the word to be flexible, adaptable to different contexts and scales. But vagueness creates trouble when you try to apply classical logic, which assumes that every statement is either true or false, with no middle ground. Classical logic wants crisp boundaries. It wants to be able to say, "This is a heap," true. "This is not a heap," false. It doesn't have a comfortable way to handle sort of a heap, or more heap-like than not. The Sorites paradox reveals the friction between these two systems, the logic that demands precision and the language that thrives on flexibility. The paradox is essentially asking, where exactly does the boundary fall? And the word heap, by its very nature, refuses to answer. This tension isn't unique to heaps of sand. The same structure appears in countless everyday concepts. Consider baldness. If you have a full head of hair, say 100,000 hairs, you're clearly not bald, that much seems certain. Now suppose you lose one hair. Are you bald now? Of course not. Losing one hair doesn't make anyone bald. So we have a rule. If you're not bald and you lose one hair, you're still not bald. But if you keep applying that rule, you reach a conclusion that seems wrong. You could lose one hair at a time until you have no hair left, and at no point did you become bald, because one hair never makes the difference. Yet people with no hair are bald. The category exists, the paradox returns. Or think about the concept of being tall. If someone is 5 feet tall, most people wouldn't describe them as tall. If you add 1 millimeter to their height, they're still not tall. 1 millimeter is too small a change to shift the category. So if you keep adding 1 millimeter at a time, it seems like no one should ever become tall. But obviously, someone who is 7 feet tall is tall. The word applies. The category is real. But where did it begin? After which millimeter? The paradox suggests there's no good answer, or at least no answer that feels satisfying. The same pattern shows up with time. Imagine you're waiting for something. After 1 minute, you probably wouldn't say you've been waiting a long time. If another minute passes, it's still not a long time. One additional minute doesn't seem like it should tip the scales, but if you extend this reasoning, even after an hour, or 2 hours, or 3 hours, you shouldn't be able to say you've waited a long time, because no single minute ever made the difference. Yet clearly, waiting for 3 hours is a long time in most situations. The paradox appears again, asking where the boundary lies, and the concept of a long time doesn't provide a clear answer. These examples show that the Sawwright's paradox isn't a quirky puzzle about sand. It's a general pattern that emerges whenever gradual change meets a word that seems to divide the world into categories. Vague terms are everywhere in language: rich, poor, old, young, hot, cold, near, far, clean, dirty, expensive, cheap. All of these words work beautifully in conversation, and all of them resist the demand for exact cut-offs. The paradox is a window into how language functions, and it reveals something that might otherwise stay hidden: that usefulness and precision are not the same thing. Given the discomfort the paradox creates, it's natural to look for ways to resolve it, to find some response that restores clarity without giving up too much. Philosophers have offered many different solutions over the centuries, each with its own appeal and its own costs. None has achieved universal acceptance, which is part of what keeps the paradox alive. But examining these responses helps clarify what's at stake and what different people are willing to accept or reject. One common response is to insist that sharp boundaries do exist, even if we don't know where they are. According to this view, there is some specific number of grains, let's call it n, at which a collection stops being a non-heap and becomes a heap. Maybe it's 500 grains, maybe it's 1,000, maybe it's some other number entirely. The key claim is that the boundary is real and definite, even though we can't identify it with confidence. This approach is called epistemicism because it treats the problem as one of knowledge rather than one of language. The boundary exists, we just don't have access to it. This response has the advantage of preserving classical logic. If there is a precise cutoff, then every collection of grains is either a heap or not a heap, with no awkward middle ground. The statement, "this is a heap," is either true or false, just as classical logic requires. The paradox dissolves because the second premise, that adding one grain can't turn a non-heap into a heap, turns out to be false. There is some grain, the nth grain, that does make the difference. We may not be able to say which one it is, but it exists. The cost of this response is psychological and perhaps philosophical. It feels strange to believe that there's a fact of the matter about exactly when a heap begins, but that we have no way of knowing what that fact is and no principled way of ever discovering it. It's not like the boundary is hidden in some empirical detail we could measure more carefully. The word heap doesn't come with a built-in number, and there's no natural law that dictates where the line should fall, so the boundary, if it exists, seems arbitrary. Why would 500 grains be the cutoff rather than 501? And if the line is arbitrary, in what sense does it really exist? These questions leave some people unsatisfied, feeling that the solution saves logic at the expense of common sense about how language works. A different response suggests that the boundary isn't fixed at all. It shifts depending on context. According to this view, heap is a flexible term whose meaning adapts to the situation. A heap of sand on a kitchen table might require far fewer grains than a heap of sand at a construction site. A heap in a child's sandbox might be different from a heap in an industrial warehouse. The word doesn't point to a single universal standard. It points to a category that's defined relative to human purposes and expectations in a given setting. This contextualist approach has the appeal of matching how we actually use language. We do adjust our standards depending on the situation. What counts as expensive for a cup of coffee is different from what counts as expensive for a car. What counts as cold in summer is different from what counts as cold in winter. The same flexibility applies to heap. The paradox loses some of its force if we accept that there's no single answer to how many grains make a heap, because the answer depends on what you're doing and why you're asking. The cost here is admitting that some words don't have fixed meanings independent of context. They're tools we use, and tools can be adapted to different tasks. This might feel like a loss if you were hoping language would carve nature at its joints, revealing objective categories that exist regardless of human interests. But if you're comfortable with the idea that language is primarily for communication rather than metaphysics, this response might feel quite natural. It shifts the focus from finding the boundary to understanding the purposes that make different boundaries useful. A third response, more radical in some ways, suggests that we should abandon the idea that statements must be simply true or simply false. Instead, we could adopt a framework where statements can be true to varying degrees. In this framework, 1 grain is a heap is definitely false. Let's say it has a truth value of 0. 1 million grains is a heap is definitely true. Let's say it has a truth value of 1. But 500 grains is a heap might be somewhat true. Perhaps it has a truth value of 0.4, meaning it's more false than true, but not entirely false. This approach is called degree theory or fuzzy logic, and it's been developed in both philosophy and mathematics. Under this framework, the paradox fails because it assumes a binary switch. The paradox relies on the idea that if something is not a heap, adding 1 grain leaves it not a heap, with not a heap meaning completely false. But if truth comes in degrees, then adding 1 grain might shift the truth value slightly. 1 grain might move you from 0 to 0.01, from 0.01 to 0.02, and so on, with each grain nudging the truth value a little higher. There's no single moment when the statement flips from false to true, because the transition is gradual, not abrupt. The appeal of this response is that it respects the gradient nature of vagueness. Heaps don't snap into existence. They emerge gradually as you add grains. Degree theory captures that gradualness by allowing truth to be a matter of more or less rather than all or nothing. The cost, however, is that it requires revising what we mean by truth. In everyday conversation, when we say something is true, we usually don't mean it's 60% true or 80% true. We mean it's just true. Degree theory asks us to rethink that intuition, at least when dealing with vague predicates. Some people find this revision liberating, others find it counterintuitive and prefer to stick with classical logic if possible. A fourth response takes aim at the premise that seems most vulnerable, the idea that adding 1 grain can never turn a non-heap into a heap. This response suggests that the premise is actually false, even though it feels plausible. The claim isn't that we can identify which grain makes the difference. Epistemicism already made that move. Rather, the claim is that our intuition about 1 grain being insignificant is misleading when applied iteratively. While it's true that 1 grain doesn't feel decisive, and while it's true that we can't point to a specific grain and say, that one did it, it's also true that somewhere in the process, 1 grain does complete the transition. The shift is real, even if it's imperceptible. This response is sometimes called the rejection of the tolerance principle. The tolerance principle is the idea that if a predicate applies to something, it must also apply to something minimally different from it. In the case of heaps, the principle says, if n grains aren't a heap, then n plus 1 grains aren't a heap either. The response here is to deny that principle. Yes, 1 grain is a small change. Yes, it's hard to see how it could matter. But when repeated many times, small changes accumulate into large changes, and at some point, the category shifts. Our inability to perceive the shift doesn't mean it didn't happen. This response preserves the everyday meaning of heap and avoids committing to hidden boundaries or degrees of truth. It simply insists that gradual change can eventually produce a qualitative difference, even if we can't pinpoint the moment. The cost is that it requires us to accept a kind of uncertainty about boundaries that might feel unsatisfying. We're left saying, yes, there's a boundary, and yes, one grain crosses it, but no, we can't say which one. It's a humble position perhaps, but humility about the limits of our concepts might be appropriate when dealing with vague language. Each of these responses offers a way to live with the paradox, or to dissolve it, or to explain it away. None is obviously correct and none is obviously wrong. The choice between them often comes down to what you're willing to accept and what you're trying to preserve. Whether it's classical logic, the flexibility of language, the gradual nature of change, or the idea that words should reflect reality in some stable way. The fact that smart people have disagreed about this for thousands of years suggests that the paradox touches on something deep about how we think and communicate. But beyond the technical responses, there's a broader lesson the paradox offers, one that's less about solving the puzzle and more about understanding what it reveals. The Sorites paradox teaches humility about language and categories. It shows that the words we use every day, words that feel transparent and obvious, are often more complicated than they seem. They work not because they're precise, but because they're good enough for the purposes we have. Heap is a useful word. It lets us communicate about piles of things without needing to count every grain or establish strict thresholds. The vagueness isn't a defect, it's what makes the word practical. At the same time, the paradox reminds us that usefulness and logical rigour can pull in different directions. When we demand that language meet the standards of a formal logic, when we insist on exact boundaries and binary truth, values, we're asking it to do something it wasn't designed to do. Language evolved to help humans coordinate, share information, express feelings, and navigate the world together. It wasn't built to satisfy the requirements of classical logic, even though logic is a powerful tool for reasoning clearly. The friction between these two systems is real, and the paradox brings it into view. There's something almost comforting in this realization. It means that the difficulty you feel when you encounter the paradox isn't a sign that you're missing something, or that there's an answer you just haven't found yet. The difficulty is built into the situation. Vague language and strict logic don't fit together seamlessly, and that's okay. You don't need to resolve the tension completely in order to use words like heap effectively, or to reason carefully about the world. You can live with a little fuzziness at the edges. In fact, the fuzziness is often where meaning lives. Think about how limiting it would be if every word required an exact definition before you could use it. Conversation would slow to a crawl. You'd spend all your time negotiating terms, specifying boundaries, arguing about edge cases. Instead, we accept that words like tall, old, rich, and heap have flexible boundaries, and we trust that context and common sense will guide us through most situations. When precision is needed, in legal contracts, scientific measurements, technical specifications, we introduce it deliberately, often by stipulating exact thresholds or using quantitative terms. But for everyday life, vagueness is not only acceptable, it's essential. The paradox also invites reflection on how we think about categories more generally. We often act as if the world comes pre-divided into natural kinds, with clear lines separating one thing from another. But many categories are human constructs, shaped by our needs, our perceptions, and our purposes. The boundary between a heap and a non-heap isn't written into the fabric of reality. It's something we impose loosely and flexibly because it helps us talk about the world. Recognizing this doesn't mean categories are arbitrary or useless. It means they're pragmatic. They serve us rather than the other way around. This perspective can extend beyond heaps and baldness to more consequential examples. When does a collection of cells become a person? When does a child become an adult? When does a relationship become serious? When does a habit become an addiction? These questions have the same structure as the Sorites paradox. They involve gradual change, vague boundaries, and categories that matter deeply, but resist precise definition. The paradox doesn't tell us how to answer these questions, but it does tell us something about the nature of the questions themselves. They're hard not because we're ignorant of some hidden fact, but because the concepts involved are genuinely vague. They don't have sharp edges, and demanding sharp edges might distort the concepts rather than clarify them. There's a kind of gentleness in accepting this. Instead of insisting that there must be a right answer, a definitive point where one category ends and another begins, you can acknowledge that some transitions are gradual and that language accommodates gradualness by staying flexible. You can hold two thoughts at once, that heaps are real and that there's no exact number of grains that makes a heap. Both thoughts are true, even though they create a paradox when you push them together under the rules of classical logic. This doesn't mean giving up on clarity or precision when they're needed. It means recognizing that different contexts call for different levels of exactness and that vague language is appropriate for many, perhaps most of the situations we encounter. The Sawright's paradox is a reminder that reality can be continuous. Grains accumulating one by one, hair falling out strand by strand, height increasing millimetre by millimetre, while our labels remain approximate. The approximation is not a failure. It's a feature that makes language usable, adaptable, and deeply human. So where does this leave us with the paradox itself? It leaves us in a place where we can appreciate the puzzle without needing to banish it. The paradox is real. It shows a genuine tension, but the tension isn't a catastrophe. It's a natural consequence of the tools we use to navigate the world. Words like heap don't fail just because they don't have sharp boundaries. They succeed precisely because they don't. They give us the flexibility to describe the world without getting bogged down in endless specification. At the same time, the paradox serves as a useful check on our thinking. It warns us not to assume that every word maps neatly onto a well-defined category. It encourages us to be careful when we reason about vague concepts, to recognize that applying strict logic to flexible language can produce strange conclusions. It's a reminder to ask, is this the right tool for the job? Sometimes the answer is yes, logic is exactly what we need. Sometimes the answer is no, we need something more forgiving, more attuned to the messiness of ordinary experience. In the end, the Sawright's paradox is less a problem to be solved and more an insight to be absorbed. It teaches that categories can be real without being rigid, that language can be meaningful without being precise, and that ambiguity isn't always an enemy. Sometimes it's an ally, allowing us to communicate efficiently and flexibly in a world that doesn't always come with clear lines. Heaps exist. The word heap is useful, and the boundary between heap and non-heap is blurry. All of these things can be true at once, and recognizing that is a form of wisdom. As you lie here thinking about grains of sand one by one, piling up slowly, it's worth noticing how the paradox mirrors other experiences of gradual change. The way day turns into night without a single moment when you can say, now it's night. The way a person ages without a precise instant when they become old. The way a relationship deepens without a clear boundary between friendship and something more. Life is full of these transitions, these slow accumulations where categories shift without announcing themselves. The Sawright's paradox captures this quality of lived experience, this sense that change happens in increments too small to notice individually, but large enough, collectively, to transform everything. And maybe that's why the paradox has endured for so long, why it continues to fascinate philosophers and puzzle students and intrigue anyone who takes the time to think it through. It's not just an abstract logical problem, it's a reflection of something true about the world and about how we move through it. We use words to organize our experience, to make sense of complexity, to share our thoughts with others. Those words are powerful, but they're also limited. They carve up the world in ways that are useful rather than exact. The Sawright's paradox reminds us of that limitation, and in doing so, It deepens our understanding of what language is and what it can do. There's a certain peacefulness in this understanding. You don't need to worry that the paradox undermines meaning or makes communication impossible. It doesn't. People have been talking about heaps and bald heads and tall buildings and long waits for thousands of years, and they've understood each other just fine. The paradox doesn't break language. It reveals how language works, not by drawing perfect lines, but by offering flexible, context-sensitive, pragmatic tools that are good enough for the job. And most of the time, good enough is exactly what we need. So the paradox stands as a kind of monument to the complexity and ingenuity of human language. It shows that even the simplest words, even something as mundane as heap, can give rise to profound questions about truth, boundaries, and how we categorize the world. It shows that logic, for all its power, doesn't have all the answers, because some questions aren't about logic. They're about the nature of the concepts we're using. And it shows that living with a little uncertainty, a little vagueness, a little fuzziness at the edges, is not only possible, but necessary. It's how we manage to talk about a messy, continuous, ever-changing world with a finite set of words. As you consider the heap of sand, grain by grain, you might imagine the pile growing slowly in front of you. One grain, then another, each one so small that it barely registers. Each addition so minor that it couldn't possibly matter on its own. And yet together, over time, they build something real. The grains don't announce when they've crossed a threshold. They don't signal the moment of transformation. They just accumulate, quietly, steadily, until at some point, some blurry, indefinite point, you look at the pile and think, yes, that's a heap. There's no contradiction in this, not really. There's just the ordinary miracle of language doing what it's designed to do, helping you make sense of the world without demanding more precision than the world offers. The heap is real, even though the boundary is not. The word works, even though the definition is loose. And the paradox, rather than undermining this, simply makes it visible. It holds up a mirror to the way we think and talk, and it asks, gently but insistently, do you see how this works? Do you see the flexibility built into your words? If you do see it, the paradox becomes less troubling and more illuminating. It's not a trap, it's a window. It lets you glimpse the structure beneath everyday language, the give and play that makes communication possible. It shows you that certainty isn't always necessary, that ambiguity can coexist with understanding, and that some questions don't have answers, not because we're missing information, but because the questions themselves are built on concepts that don't support the weight of absolute precision. This is the gift of the Sorite's paradox. It teaches you to be at peace with vagueness. It shows you that you can live in a world where grains pile up without a magic number, where hair falls out without a sharp line of demarcation, where time passes without a precise moment, when a little while becomes a long time. You can navigate this world successfully, communicating clearly, reasoning carefully, making decisions wisely, all without needing every category to have crisp edges. The edges can be soft, they can blur, they can shift with context and purpose. And that's okay. In fact, it's more than okay, it's essential. Because the world itself doesn't come with labels. We bring the labels to it, and we use them in ways that serve our needs. A heap of sand doesn't care whether it's a heap. The classification matters to us because it helps us talk about what we see, plan what we'll do with it, coordinate with others. The word is a tool, and like any tool, its value lies in its usefulness, not in its perfection. So when you encounter the paradox, whether you're thinking about sand or hair or height or time or any of the countless other vague concepts that fill our language, you can meet it with curiosity rather than frustration. You can ask what it reveals rather than how to defeat it. You can appreciate the way it exposes the flexibility of language, the pragmatism of categorization, the human ingenuity involved in creating words that work even when they don't define. And as you drift closer to sleep, the paradox becomes almost soothing. Grain by grain the pile grows. Step by step the reasoning unfolds. The conclusion feels wrong, yet the premises feel right, and the tension between them creates a kind of rhythm, a back and forth that doesn't demand resolution. You can hold the paradox gently, turning it over in your mind, noticing its contours without needing to fix it or solve it or make it go away. It's a puzzle that's comfortable to live with, a question that's interesting precisely because it doesn't have a neat answer. The sand continues to pile, one grain at a time. Somewhere in that process, without fanfare, without a clear signal, the pile becomes a heap. You can't say exactly when, and you don't need to. The heap is there. The word applies, the meaning holds. And the paradox, far from undermining any of this, simply reminds you that language is a beautiful, flexible, imperfect tool. One that lets you describe a world full of gradual change, fuzzy boundaries, and ambiguous categories with a remarkable grace and efficiency. This is what the Sorites paradox offers, in the end. Not a problem to solve, but a perspective to inhabit. It invites you to see language not as a rigid system of definitions, but as a living, breathing, adaptive practice, one that works because it bends, because it accommodates, because it doesn't demand more certainty than the world provides, and in that flexibility, there's a kind of wisdom, a recognition that not everything needs to be pinned down, that some things are allowed to be vague, that the boundaries we draw are often provisional and context-dependent and good enough. The grains keep piling, the heap keeps growing, and you, watching this slow accumulation, can rest in the knowledge that heaps exist, that vagueness is real, and that the paradox is a teacher rather than a threat. It's a reminder that thinking clearly doesn't always mean thinking rigidly, that understanding deeply doesn't require defining precisely, and that some of the most interesting questions are the ones that don't have simple answers. The Sorites paradox is one of those questions, and it's been with us for thousands of years, and it will likely be with us for thousands more, quietly asking us to reflect on how we use words, how we carve up the world, and how we would make meaning in a reality that refuses to be neatly categorized. So let the paradox be. Let it sit there, unresolved and fascinating, a testament to the complexity of language and the subtlety of thought. Let the grains pile up, one by one, without worrying about the exact moments when the collection becomes a heap. Trust that the word works, that communication happens, that understanding is possible, even in the absence of perfect precision. And as you settle into that trust, as you accept the gentle blur at the edges of meaning, you might find a certain comfort, a recognition that the world is richer, more nuanced, more forgiving than strict logic would suggest, and that your language, for all its imperfections, is beautifully suited to the task of navigating that world. The next story is about to begin. Please relax and enjoy. We begin with something so familiar, it barely registers as an assumption. Everything has a beginning. The chair you sit in was assembled in a factory. The words you speak were learned from others who learned them before. The thoughts forming in your mind right now arise from memories, experiences, and neural patterns that developed over time. This intuition runs deep. When we encounter anything, an object, an idea, a melody, we naturally ask where it came from. We trace causes backward, link by link, confident that somewhere at the end of that chain lies an origin point, a moment of creation, an act of invention, a first cause that started everything else rolling forward. The bootstrap paradox asks us to imagine something different. It describes a situation where this comfortable chain of cause and effect forms not a line but a circle, where the thing we're trying to explain exists without ever having been created, where every step leads logically to the next but the loop, as a whole, has no beginning. The paradox gets its name from the old expression about pulling oneself up by one's bootstraps, an impossible feat of self-generation. And like that image, the bootstrap paradox presents something that seems to generate itself from nothing, not through magic or violation of logic, but through the strange geometry of circular time. At first glance, the paradox might sound like a mere curiosity, a puzzle for philosophers or science fiction writers to play with during idle hours, but it touches something deeper than entertainment. It challenges one of our most basic cognitive tools, the assumption that explanation means tracing backward to something earlier, something prior, something that came first. The bootstrap paradox suggests that in a universe where time travel is possible, some things might be fully explained without ever having a first moment. They exist, they're consistent. Every part of their existence makes sense in relation to the other parts, but they have no origin outside themselves. The core structure of the paradox is remarkably simple. Imagine an object or piece of information that travels backward through time. Once in the past, it participates in events that eventually lead to its own future existence. Then at the appointed moment, it travels backward again, closing the loop. The future depends on the past because the object must exist in the past to cause the future. But the past depends on the future because the object arrives from the future. Neither comes first. Neither is the foundation upon which the other rests. They form a circle, a loop that is internally consistent, each event following causally from the previous one, yet missing the external point of origin we instinctively expect. To make this less abstract, consider a concrete example, one gentle enough to ease us into the paradox's strange territory. Picture a time traveller who arrives in the past carrying a book, not just any book, but a collection of mathematical proofs, elegant solutions to problems that have puzzled scholars for years. The time traveller approaches a mathematician working in obscurity, someone talented but struggling, and hands over the book. "Study this," the time traveller says. "These proofs will change everything." The mathematician opens the book. The proofs inside are beautiful, clear, correct. They solve problems the mathematician has been wrestling with for months. Over the following years, the mathematician studies these proofs, absorbs them completely, and eventually publishes them under their own name. The publication is celebrated. The proofs become famous, studied by students, reproduced in textbooks, preserved in libraries. Decades pass. The book containing these proofs becomes a standard reference, printed and reprinted, passed from generation to generation. Eventually, a copy of this book finds its way into the hands of someone who will one day become a time traveller. They study it fascinated. They memorise its contents, and when they finally gain access to time travel technology, they choose to bring this particular book back to the past, to the mathematician at that crucial moment of struggle. They become the time traveller in our story, completing the loop. Now ask the central question, who created those mathematical proofs? The mathematician? No, the mathematician received them from the time traveller and merely studied and published what was already complete. The time traveller? No, the time traveller learned the proofs from the published book and carried them backward, unchanged. The proofs exist in a closed causal loop. Every step in their journey can be explained by reference to earlier steps in the sequence. The time traveller brings them because they learned them from the book. The book exists because the mathematician published it. The mathematician published it because the time traveller brought it. Each link in the chain is perfectly accounted for. Yet there is no moment of creation, no spark of original authorship. The information simply exists, circulating through time like blood through a closed system, never entering from outside. This is the essence of the bootstrap paradox. Something exists, and its existence is fully explained by a chain of causes, but that chain forms a loop rather than terminating in an origin. The information in the book was not created at any point in the timeline. It has no author in the usual sense. It is, in a real and troubling way, self-caused. Let's shift from information to physical objects, because the paradox works just as well, and perhaps feels even stranger, when applied to something you could hold in your hands. Imagine a pocket watch, old-fashioned and intricate, with delicate gears and a beautifully engraved case. Someone discovers this watch, perhaps in an antique shop, or inherited from a relative. They cherish it, care for it, have it repaired when necessary using its own design as a guide. Years pass. Eventually, this person gains access to time travel. For reasons sentimental or practical, they decide to send the watch backward in time, perhaps to their younger self, or to an ancestor, or simply to a point where it will be found and appreciated. The watch arrives in the past. Someone finds it. Maybe the same person at a younger age. Maybe someone else entirely. That person cherishes it, cares for it, eventually passes it on, or finds a way to send it backward in time. The watch loops. It is found, preserved, and sent back. Found, preserved, and sent back. Each cycle proceeds logically. Each person who possesses the watch has a clear explanation for where it came from. They found it, or received it, or inherited it. Each person who sends it back has a clear motive and method. The watch's journey through time forms a consistent history. But when was it made? When did a craftsperson sit at a workbench, shaping metal and glass into this particular configuration? The answer, according to the loop, is never. The watch was not manufactured. It was not assembled from raw materials at any point in the timeline. It simply exists, cycling through the same span of years over and over, neither created nor destroyed, only moved. Every moment of its existence can be explained. It's here now because it was there then, and it was there then because it will be here now. But the explanation is circular. The watch is self-sustaining. This reveals something important about the bootstrap paradox. It doesn't violate causality in the sense of having effects without causes. Every event has a cause. The mathematician publishes the proofs because the time traveller brought them. The time traveller brings them because the mathematician published them. The watch exists here because it was sent from there. It was sent from there because it exists here. Causality is preserved. What's violated, or at least deeply challenged, is our expectation that causal chains must have a beginning, a foundation, a first cause that wasn't itself caused by something later. Why does this feel so wrong? Why does the paradox generate such cognitive discomfort? To understand the discomfort, we need to examine our intuitions about causality and what we might call the accounting of existence. In ordinary experience, the universe operates on a kind of bookkeeping system. If you want a book to exist, someone must write it. If you want a watch to exist, someone must make it. Information must be generated, objects must be assembled, energy must be expended. The universe keeps accounts. Nothing appears without being paid for in the currency of prior causes, prior events, prior expenditures of energy and effort. We might not always know what those prior causes were, but we're confident they existed. The universe doesn't run a deficit. It doesn't give out books or watches or ideas for free. The bootstrap paradox appears to violate this accounting principle. The mathematical proofs exist and circulate through time, but nobody ever did the work of creating them. The watch exists and passes from hand to hand, but nobody ever expended the energy and skill to craft it from raw materials. The paradox seems to generate something from nothing, not in a single magical moment, but through a structure that avoids the need for generation entirely. It's as if the universe has found a loophole in its own bookkeeping. If time can loop, then causes can form circles. And if causes can form circles, then things can exist without needing to be paid for by a prior act of creation. This isn't quite getting something for nothing, because the object or information does exist and does participate in causal processes. It's more like having an account that always shows a balance, but never had an initial deposit. The books balance at every moment. The watch is here because it was there because it will be here. But the system as a whole seems to have skipped the step where value entered the system in the first place. Our discomfort with this situation reveals something about how deeply we rely on directional causality. We're accustomed to thinking of time as having a forward flow, and of cause and effect as respecting that flow. Causes precede effects, origins come before consequences, foundations are laid before structures are built on them. The bootstrap paradox preserves the local structure of causality. Each event is caused by a prior event, but breaks the global structure by forming a loop, and our intuitions, tuned to linear causal chains, rebel against the loop even when we can't point to a specific logical error. It's worth pausing here to distinguish the bootstrap paradox from another famous time travel puzzle, the grandfather paradox. The grandfather paradox asks what happens if you travel back in time and prevent your own existence, perhaps by interfering with your grandparents' meeting. The paradox is that you could only travel back in time if you existed, but if you succeeded in preventing your existence, you couldn't have travelled back to prevent it. This is a contradiction in the logical sense. It implies you both existed and didn't exist, which is impossible. The bootstrap paradox is different. It doesn't create a logical contradiction. There's no statement of the form A and not A. Instead, it creates a causal structure that is internally consistent but lacks an external origin. The mathematical proofs exist and have a complete history. The watch exists and has a complete history. Nothing in the timeline contradicts anything else. Every event flows logically into the next. The paradox is not one of logical impossibility, but of conceptual strangeness. A complete, coherent history that nevertheless seems to be missing something we instinctively think should be there. This distinction matters because it affects how we might respond to the paradox. The grandfather paradox suggests that certain time travel scenarios simply cannot occur. They lead to contradiction and therefore must be prevented by the structure of reality itself, perhaps through quantum effects or the nature of time. The bootstrap paradox doesn't obviously require that kind of prohibition. It's logically coherent. The question is whether the universe permits logically coherent but originless causal loops, or whether there's some deeper principle that rules them out even though they don't generate formal contradictions. Let's explore some common responses to the bootstrap paradox, approaches that different thinkers have taken to make sense of these strange loops without insisting they're simply impossible. The first response is to embrace self-consistency as a fundamental principle of time travel. According to this view, if time travel is possible, then the universe must be arranged such that only consistent histories can occur. You cannot kill your grandfather because that would be inconsistent with your existence. Similarly, if a bootstrap loop is consistent, if the watch really does loop without creating any contradictions, then the loop is permitted, even if it lacks an external origin. This approach has been developed most carefully in physics by researchers thinking about closed time-like curves, which are solutions to Einstein's equations of general relativity that allow for time loops. In general relativity, time and space are woven together into a four-dimensional fabric called space-time. Normally, as you move through this fabric, you move forward in time, but certain configurations of mass and energy, rotating black holes for instance, or certain theoretical constructions involving exotic matter, can curve space-time so severely that world lines, the paths objects follow through space-time, can loop back on themselves. An object following such a path would travel forward in its own experience, moment by moment, but eventually return to an earlier moment in external time, creating a closed loop. If such loops are possible, then the universe must somehow ensure that what happens in the loop is consistent with itself. The physicist Igor Novikov and others have proposed what's sometimes called the Novikov self-consistency principle. The universe will arrange events such that any action taken by a time traveller was always part of the timeline. You can't change the past because your attempt to change it was always part of the past. Any causal loop that forms must be self-consistent. Under this principle, bootstrap loops are not errors or impossibilities, but permitted structures. If a book of mathematical proofs loops through time, then that's simply what happens in that particular region of space-time. The proofs exist without an external author because the structure of space-time allows a closed loop, and the contents of the loop are self-consistent. There's no contradiction, no violation of physics, only a violation of our expectation that everything must have an origin outside itself. The cost of this view is conceptual rather than logical. You must accept that some things in the universe simply are, without having been created. They participate in causal processes, they cause effects and are caused by earlier events, but they exist within a loop rather than at the end of a chain. Origins, in these cases, are replaced by cycles. The question, where did it come from, has no answer in the usual sense, only a description of how it moves through the loop. This might feel unsatisfying, but it's not obviously unreasonable. After all, physicists have long grappled with the question of origins in other contexts. What caused the Big Bang? Some models suggest the Big Bang was the beginning of time itself, in which case asking what came before is like asking what's north of the North Pole, a category error. Other models propose eternal inflation or cyclical cosmologies, where the universe has no single beginning. The point is that physics has already encountered situations where our intuitive demand for an ultimate origin may not apply. The bootstrap paradox simply extends this conceptual challenge to localized loops within spacetime rather than to the cosmos as a whole. A second response to the bootstrap paradox involves the idea of branching timelines or parallel universes. According to this view, time travel doesn't occur within a single fixed timeline, but instead involves movement between different branches of reality. When something travels backward in time, it might not arrive in the same timeline it left from, but rather in a different, parallel version of history. Applied to the bootstrap paradox, this approach suggests that the watch or the book of proofs doesn't truly create itself within a single timeline. Instead, it travels from one branch to another. In timeline A, someone creates the watch through ordinary means. A craftsperson makes it. It's purchased. It eventually falls into the hands of a time traveller who sends it backward to timeline B. In timeline B, the watch appears from nowhere, as far as the inhabitants of that timeline can tell, but it has an origin in timeline A. The loop we observe in timeline B is not genuinely originless. It's just that the origin lies in a different branch of the multiverse. This approach has the advantage of preserving our intuition that everything must have an origin somewhere. The cost is accepting a vast, perhaps infinite, proliferation of parallel timelines. Every time travel event splits reality into branches or connects to already existing branches, creating a structure far more complex than a single linear history. The universe's bookkeeping is preserved. Every watch was made somewhere, every proof was thought up by someone, but the accounts are spread across multiple parallel realities. This branching model draws support from certain interpretations of quantum mechanics, particularly the many worlds interpretation proposed by Hugh Everett. According to this interpretation, every quantum measurement causes the universe to branch into multiple parallel versions, each representing a different possible outcome. If time travel involves quantum processes, and most realistic mechanisms for time travel, such as traversable wormholes, would involve quantum physics at some level, then perhaps it naturally connects to different branches of the quantum multiverse, rather than looping within a single timeline. Under this view, the bootstrap paradox isn't really a paradox at all. What appears to be a closed loop from the perspective of timeline B is actually a connection between two different timelines. The watch has a history, it's just not entirely contained within the timeline where we're observing it. The strangeness is softened, replaced by the different strangeness of a branching tree-like structure of parallel realities. The third major response to the bootstrap paradox is skepticism about whether such loops can actually occur in nature. This view holds that while bootstrap loops may be logically consistent, and while certain solutions to Einstein's equations technically allow closed time-like curves, The conditions necessary to create such loops might be impossible to achieve in practice, or might be forbidden by laws of physics we don't yet fully understand. There are several reasons to be skeptical. One involves the conservation of energy and information. In ordinary physics, energy is conserved. It can change forms, but cannot be created or destroyed. Information, similarly, has a kind of conservation property in quantum mechanics. But a bootstrap loop seems to create information or energy in a strange way. The watch exists at multiple times without being created or destroyed. Does this violate conservation laws? The answer is not entirely clear, and this ambiguity suggests that bootstrap loops might trigger physical instabilities or be prevented by mechanisms we haven't fully identified. Another concern involves quantum mechanics. Stephen Hawking and others have argued that quantum effects might prevent the formation of closed time-like curves. When space-time is curved severely enough to allow time loops, quantum fluctuations might become so intense that they destroy the structure before it can close. Hawking called this the chronology protection conjecture. The laws of physics conspire to prevent time travel and thereby protect the consistency of history. If chronology is protected, then bootstrap loops cannot form, not because they're logically impossible, but because the physical conditions that would permit them are ruled out by quantum processes. There's also the issue of entropy. The second law of thermodynamics tells us that entropy, roughly speaking disorder or randomness, tends to increase over time. But in a perfectly repeating loop, entropy would have to be the same each time around. The watch returns to the same state cycle after cycle. How can this be reconciled with the tendency of disorder to increase? Some physicists argue that true closed loops might be incompatible with the thermodynamic arrow of time, the direction defined by increasing entropy. If so, bootstrap loops might be forbidden, not by logic, but by thermodynamics. These physical objections don't definitively rule out bootstrap loops, but they suggest caution. Even if closed time-like curves are solutions to Einstein's equations, even if they're logically consistent, they might represent configurations of spacetime that cannot actually occur in nature, either because quantum effects prevent them, or because they violate thermodynamic principles in subtle ways. The bootstrap paradox might be telling us something important. If a model of physics predicts origin-less causal loops too easily, without sufficient barriers or constraints, then that model might be missing important features of reality. This skeptical stance has the advantage of preserving our intuitions about origins and causality without requiring us to prohibit time travel entirely. It allows that time travel might be possible in some limited forms, perhaps travel to the future through time dilation, or perhaps very constrained forms of backward time travel, without permitting the full-blown paradoxes that arise from unrestricted, closed time-like curves. It's a middle ground. Time travel might exist, but the universe has guardrails that prevent the strangest outcomes. So where does all this leave us? We've explored the bootstrap paradox from multiple angles: the core structure of the loop, examples involving information and physical objects, comparisons with other paradoxes, and various responses ranging from acceptance to skepticism. What can we learn from this journey? The deepest lesson of the bootstrap paradox is that cause and origin are not the same thing. We tend to conflate them in everyday thinking because, in normal circumstances, they align. The cause of the book is the author writing it, and the author is also the origin, the source from which the book came into existence. But the bootstrap paradox forces us to separate these concepts. In a causal loop, every event has a cause. The loop is not random or arbitrary. Each step follows necessarily from the previous step. Causality is preserved. What's missing is the origin, the external point from which the loop emerged. This separation might seem like philosophical hair-splitting, but it's actually quite profound. It suggests that our demand for origins is not the same as our demand for causal explanations. You can have a complete causal story every event explained by reference to earlier events, without having an origin story. The bootstrap paradox shows us a scenario where causality is local and circular, while origins, in the traditional sense, simply don't exist. This has implications beyond time travel puzzles. In cosmology, for instance, some models of the universe suggest eternal inflation or cyclical cosmologies where there is no single beginning, no first moment from which everything else emerged. The universe in these models is like a bootstrap loop writ large, self-sustaining, internally consistent, but lacking an ultimate origin point. The bootstrap paradox helps us understand how this could be coherent, even if it violates our intuitions. Similarly, in thinking about consciousness and self-reference, we encounter circular structures. Your sense of self is constructed from memories and experiences, but those memories and experiences are themselves shaped by your sense of self. The observer and the observed, the thinker and the thought form loops rather than clean hierarchies. The bootstrap paradox, by making us comfortable with circular causation, might help us think more clearly about these other domains where loops and self-reference appear. The paradox also teaches us something about explanation itself. We often assume that a good explanation traces back to something more fundamental, something prior, something that grounds everything else. This works well in many contexts. We explain the behaviour of matter by reference to atoms, atoms by reference to particles and forces and so on, drilling down to deeper levels. But the bootstrap paradox suggests that some explanations might be horizontal rather than vertical, circular rather than foundational. The explanation for why the watch is here is not that something more fundamental caused it, but that it's part of a self-consistent loop. The explanation is complete, but it doesn't ground out in anything external to the loop itself. This might make us uncomfortable, and that discomfort is worth examining. Why do we feel that explanations must terminate in foundations? Part of it is practical. In everyday life, causal chains do terminate. You trace the source of a river to a spring, the origin of a rumour to a person, the cause of a disease to a pathogen. Stopping at "it's a loop" would be unsatisfying in these contexts because it would mean giving up on finding a real external explanation. But the bootstrap paradox exists in contexts where time itself behaves differently, where the usual rules about before and after can be bent. In such contexts, perhaps our insistence on foundations is misplaced. There's also something aesthetically pleasing about foundations. We like the idea of building up from simple principles, of grounding complexity and simplicity, of tracing the intricate back to the elemental. Bootstrap loops, by contrast, are neither simple nor complex. They just are, existing as self-contained structures. They don't offer the satisfaction of reduction or the clarity of a base case. They're strange middle entities, too structured to be fundamental, too self-sustaining to need grounding in something else. The paradox doesn't demand that we accept bootstrap loops as real features of our universe. As we've seen, there are good physical reasons to be skeptical about whether closed time-like curves can actually form, and even better reasons to think that they would be extremely rare or limited if they did exist. But whether or not bootstrap loops are physically real, the paradox has value as a thought experiment. It shows us the logical structure of a certain kind of circular causation, and it challenges us to think clearly about what we mean by explanation, origin, and cause. In that sense, the bootstrap paradox is educational in the best way. It takes a concept we thought we understood, causality, and shows us that our understanding was incomplete. It reveals hidden assumptions we didn't know we were making. It forces us to distinguish between different aspects of causation that we normally lump together. And it does all this not by presenting us with a logical contradiction to solve, but by presenting us with a coherent scenario that nevertheless feels wrong, forcing us to interrogate why it feels wrong and whether that feeling is justified. Let's think a bit more carefully about what it would mean for a bootstrap loop to exist in practice, because there are subtleties we haven't fully explored yet. Suppose the loop is real. The watch genuinely cycles through time. The proofs genuinely circulate without an author. One question that arises is about the stability of the loop. Does the watch wear out as it cycles? Do small errors accumulate in the transmission of the proofs? In an idealized version of the paradox, we might imagine the loop as perfectly repeating, with each cycle identical to the last. The watch returns to exactly the same state each time. The proofs are transmitted without alteration or degradation. This perfect repetition would be necessary to maintain the loop indefinitely. If the watch degraded with each cycle, eventually it would deteriorate to the point where it couldn't function, and the loop would break. If errors crept into the proofs with each transmission, eventually they would become corrupted beyond recognition. But perfect repetition is difficult to achieve in the real world. Physical objects wear out, information degrades, entropy increases. So if a bootstrap loop is to be stable over many cycles, it would require either perfect preservation mechanisms, perhaps the loop passes through environments that restore the object to its original state, or the loop would have to be relatively short, covering only a span of time during which degradation is negligible. There's another subtlety involving the specificity of the loop. In our examples, we've talked about a particular watch or a particular set of proofs. But why those specific contents and not others? If the loop is self-contained, what determines what's in the loop? In ordinary causation, the specific outcome is determined by prior conditions and laws of nature. If you drop a ball, gravity determines how it falls. But in a bootstrap loop, there are no prior conditions external to the loop. The loop just is. So what picks out this particular watch, this particular set of proofs, rather than some other configuration? One response is that the loop must be self-consistent, and not all configurations would be. If the watch's design is too complex, it might not be possible for someone in the loop to preserve and transmit it accurately. If the proofs are wrong or incoherent, they wouldn't be publishable or credible. The requirement of self-consistency might constrain what loops are possible, ruling out many potential configurations and leaving only those that can sustain themselves. But this still leaves room for many possible loops, and it's not clear what would select among them. Perhaps if bootstrap loops are permitted by physics, there are many of them scattered through space-time, each containing different objects or information. Or perhaps the formation of a loop requires such specific conditions that only certain configurations are achievable in practice, with the specifics determined by the details of how the loop forms, the exact curvature of space-time, the precise arrangement of matter and energy, and so on. This question of specificity connects to a deeper issue about the nature of physical law. We're accustomed to thinking of laws of nature as rules that, given initial conditions, determine how things evolve. The laws tell you what happens next given what's happening now, but in a bootstrap loop, there are no initial conditions external to the loop. The loop has no beginning where you could specify starting values. Does this mean the laws of nature are incomplete, unable to fully determine what happens in a universe with closed time-like curves? Or does it mean we need a different way of thinking about physical law, one that treats self-consistency as a constraint rather than evolution from initial conditions as the primary mode of determination? These are open questions, and they take us to the frontiers of theoretical physics and philosophy. Some researchers working on quantum gravity and the nature of time have proposed that the universe might be best described not by evolution from an initial state, but by a kind of global self-consistency condition. The universe is the way it is because that's a self-consistent configuration, and other configurations would contradict themselves in various ways. This view is speculative, but it gains some motivation from the bootstrap paradox and related puzzles about time and causation. Another aspect worth considering is the subjective experience of someone inside a bootstrap loop. Imagine you are the time traveler who brings the book of proofs back to the mathematician. From your perspective, you study the proofs, learn them, decide to bring them back. Your actions are motivated by your knowledge and desires. You feel like you're making free choices, but the entire sequence of your actions is part of a loop that has no external cause. Were your choices really free, or were they determined by the structure of the loop itself? This is a version of the free will problem, but with an extra twist. In ordinary determinism, your actions are determined by prior states of the universe, which in turn were determined by earlier states, possibly tracing back to initial conditions at the Big Bang or some other starting point. You might not have libertarian free will, the ability to have done otherwise, but at least there's a sense in which the chain of causation grounds out in something external to you. In a bootstrap loop, the chain of causation includes you and loops back through you. You are part of what determines yourself. This is a strange kind of self-determination, but it's not clear whether it counts as freedom or simply a more elaborate form of constraint. Some philosophers find this appealing, actually. If you're part of a self-consistent loop, then in a sense you participate in determining your own actions, not by stepping outside the causal order, but by being an essential part of the causal structure. Your choices contribute to the overall consistency of the loop. Of course, this participation is not the same as having the power to do otherwise. If the loop is self-consistent, then it must unfold the way it does, but it blurs the line between determined and self-determined in interesting ways. Others find this deeply unsettling, because it seems to collapse the distinction between agent and mechanism. If your actions are part of a predetermined loop, then in what sense are they yours? You're not choosing based on reasons external to the loop. You're simply a component in a causal structure that includes you. Your sense of deliberation and decision-making might be a kind of illusion, or at least a local phenomenon that doesn't reflect the global structure of the loop. These questions about free will and agency in bootstrap loops connect to broader debates about determinism and responsibility, but they have a unique flavour because of the circular structure. They're not just about whether your actions are determined by prior states, but about whether your actions are part of a self-contained causal circuit that includes you as one of the relays. Let's return to the question of physical plausibility. We've mentioned that quantum effects might prevent the formation of closed time-like curves, but let's dig a bit deeper into why this might be the case. The concern is that, as space-time curves more and more severely approaching the configuration needed for a time loop, quantum fluctuations of the fields pervading space would become increasingly intense. Normally, these fluctuations are tiny and average out to near zero, but in highly curved space-time, they can be amplified. In particular, near the point where a time loop would close, you might expect a phenomenon called a quantum vacuum fluctuation to blow up. Virtual particles, which normally pop in and out of existence on tiny scales, might be produced in such numbers that they create a huge back reaction, warping space-time in the opposite direction and preventing the loop from forming. This is the basis of the chronology protection conjecture. Quantum effects act as a kind of immune response, attacking any configuration of space-time that threatens to allow travel to the past. The mathematics of this is complex and not fully understood. Calculating quantum effects in curved space-time is one of the hardest problems in theoretical physics, and we don't yet have a complete theory of quantum gravity that would let us answer definitively what happens near closed time-like curves. But the heuristic argument that quantum fluctuations would destabilize the loop is taken seriously by many physicists as a reason to think that time travel to the past, and therefore bootstrap loops, might be impossible in practice, even if they're not forbidden by classical general relativity. On the other hand, some researchers have explored whether there might be exotic forms of matter or energy that could stabilize a time loop against quantum disruption. These would be materials with strange properties like negative energy density or violations of energy conditions that normally hold. Such exotic matter has not been observed in nature, and it's not clear whether it can exist, but it's not definitively ruled out either. If it does exist, it might make closed time-like curves more stable, potentially allowing bootstrap loops to form. The hunt for exotic matter and the study of quantum effects in curved spacetime are both active areas of research, motivated in part by the puzzles raised by time travel scenarios like the bootstrap paradox. Even if we conclude that bootstrap loops are impossible in our universe, understanding why they're impossible would teach us something important about the deep structure of physics. There's also a question about what kinds of time loops might be possible, even if full-fledged closed time-like curves are not. For instance, quantum mechanics allows for a phenomenon called retrocausality, where the outcome of a measurement can be influenced by events in its future. This doesn't permit classical time travel. You can't send a watch or a book backward, but it does involve causal influence flowing in both temporal directions. Some interpretations of quantum mechanics embrace retrocausality as a fundamental feature, while others reject it in favour of purely forward-moving causation. If retrocausality is real at the quantum level, then in some sense causal loops already exist in nature, just not at the macroscopic scale where we could exploit them for time travel. A measurement here and now might be causally connected to a choice made in the future, forming a small, localized loop in the web of causation. These quantum loops wouldn't allow you to send information backward in time in a controlled way, but they would mean that the universe already contains structures reminiscent of the bootstrap paradox. This is speculative, and many physicists are skeptical of retrocausal interpretations of quantum mechanics. But the point is that the bootstrap paradox, while often discussed in the context of macroscopic time travel, connects to deeper questions about the nature of causation and time that appear in fundamental physics. The paradox is not just a curiosity about time machines, it's a probe into the structure of causality itself. Let's consider one more variation of the paradox, one that brings out a slightly different flavour of the puzzle. Suppose instead of a watch or a book, we're talking about a piece of genetic information. Imagine a time traveller who carries a DNA sample backward in time. This sample is incorporated into a genome, perhaps through advanced genetic engineering, and the organism that develops from this genome eventually gives rise to descendants, one of whom becomes the time traveller who carries the DNA sample backward. Now the question is, where did that specific sequence of DNA come from? It's not the result of evolution in the usual sense, because evolution involves variation and selection over many generations, and those processes would generate new sequences. But in the loop, the sequence is transmitted unchanged, from future to past and back. It exists without having been generated by evolutionary processes. It's a genetic bootstrap. This variation highlights something interesting. Information, whether in the form of mathematical proofs, DNA sequences, or any other encoding, seems particularly suited to bootstrap loops because it can be copied with high fidelity. A physical object might degrade over time, but information, if properly copied, can remain unchanged. Of course, in reality, copying is never perfect. There are always small errors, mutations, transcription mistakes. But in principle, information is the kind of thing that can circulate through a loop without degradation. This raises the question of whether bootstrap loops are more plausible for information than for physical objects. If so, then maybe the bootstrap paradox is primarily a problem about the origin of information rather than the origin of matter. Information can exist in a loop, while matter, subject to wear and entropy, cannot sustain perfect loops. Of course, information is always encoded in matter, whether in ink on paper, neurons in a brain, or bases in a DNA strand. But perhaps the relevant feature is the information itself, not the physical substrate. This connects to debates in philosophy of mind and information theory about whether information is a fundamental feature of reality or merely a useful abstraction? If information is fundamental, then maybe bootstrap loops of information are not just logically possible, but physically permissible. If information is merely a way of describing physical states, then the constraints on physical loops would also constrain informational loops. We should also consider the narrative and dramatic uses of the bootstrap paradox, because while our focus is on the science and philosophy, the paradox has captured the imagination of storytellers for good reason. It's a device that allows for elegant, self-contained plots, where every element is explained, but the overall structure has a kind of mysterious completeness. A character receives a message from the future, acts on it, and in doing so causes the message to be sent. Everything makes sense, but nothing had to start. In fiction, this can create a sense of fate or inevitability. The characters are playing out roles in a script that has no author, following a pattern that exists simply because it's self-consistent. This can be thrilling or eerie, depending on how it's framed. But it's worth noting that the narrative appeal of the bootstrap paradox is not separate from its philosophical interest. Both stem from the same source, the tension between our desire for origins and the coherence of the loop. Science fiction has explored many variations. In some stories, the loop is tight and simple, a single object or piece of information cycling through time. In others, the loop is vast and complex, involving entire civilizations or histories that curve back on themselves. Some stories treat the loop as stable and eternal. Others explore what happens if the loop is disrupted or decays over time. These narrative explorations can serve as intuition pumps, helping us think through the implications and variations of the paradox in ways that pure abstraction might not. But we should be careful not to let the narrative convenience of bootstrap loops in fiction make us overestimate their plausibility in reality. Fiction operates under different constraints than physics. A story needs to be coherent and satisfying. A physical theory needs to be consistent with observation and experiment. The bootstrap paradox is a wonderful narrative device, but that doesn't make it a feature of our universe. At the same time, fiction can sometimes point toward conceptual possibilities that are worth taking seriously. Many concepts in modern physics, higher dimensions, parallel universes, black holes, were once purely speculative or appeared first in fiction before being developed rigorously by scientists. The bootstrap paradox might be similar, a thought experiment that clarifies the logical structure of time and causation, even if it never describes an actual event. As we near the end of this exploration, it's worth stepping back and asking what we've gained from all this. The bootstrap paradox doesn't have a clean resolution. It's not like a math problem where you can turn to the back of the book and check the answer. Different responses, self-consistency, branching timelines, physical prohibition, all have their merits and drawbacks. The paradox remains genuinely puzzling, and that's part of its value. What we've gained is a richer understanding of causation. We've learned to distinguish between local and global causal structure, between having causes for individual events and having an origin for a system as a whole. We've seen that circular causation is logically coherent, even if it's strange and unfamiliar. We've explored how physics might or might not permit such structures, and we've thought about what it would mean for explanation and understanding if they did occur. The bootstrap paradox also serves as a reminder of how much we assume when we think about the world. We assume that time flows in one direction. That causes precede effects, that everything has a beginning. These assumptions are so basic that we rarely notice them. But they're not self-evident truths. They're features of the world as we experience it. And in principle, a world with different features, a world with closed time-like curves, might be possible. The paradox helps us see our assumptions by showing us what a world without them would look like. There's also a kind of humility that comes from engaging with the bootstrap paradox. It reminds us that even basic concepts like cause and origin, which seem so clear and straightforward, can become slippery and complex when we push them into unusual contexts. This doesn't mean those concepts are useless or that we should abandon them. It means they have limits, boundaries beyond which they stop giving us reliable guidance. Recognizing those limits is part of thinking clearly. In the end, the bootstrap paradox is a puzzle about existence and explanation. It asks whether something can exist without being created, whether a chain of causes can form a circle, whether explanations must always ground out in foundations or can sometimes be self-supporting loops. These are deep questions, and the paradox doesn't answer them so much as make them vivid and concrete. Perhaps the best way to think about the bootstrap paradox is as a kind of lens. It doesn't change the world, but it changes how we see the world. It brings into focus the structure of causation, the nature of time, the meaning of explanation, and by showing us a scenario where all these familiar concepts behave in unfamiliar ways, it helps us understand them better. We started with the assumption that everything has a beginning, and we've journeyed through a landscape where that assumption breaks down. We've seen how an object or piece of information could exist without ever being created, how a loop could be self-sustaining and complete yet strangely unfinished. We've explored responses, considered physical possibilities, and thought about what it all means. The bootstrap paradox doesn't demand a final answer. It's not a puzzle to be solved and discarded. It's a conceptual tool, a thought experiment that helps us explore the edges of what we understand about time and causation. Whether or not bootstrap loops are real, whether or not time travel is possible, the paradox has done its work. It's challenged us to think more carefully, to question our assumptions, and to appreciate the subtlety of concepts we normally take for granted. As we let these ideas settle, we can appreciate the paradox for what it is, a window into the strange possibilities that open up when time is treated not as a simple, one-directional flow, but as a dimension that might, under the right conditions, curve back on itself. It's a reminder that the universe, even in its logical structure, holds mysteries and surprises. And it's an invitation to keep thinking, keep questioning, and keep exploring the boundaries of what we know and what we can imagine. The bootstrap paradox shows us that cause and origin can come apart, that something can be fully explained step by step and still lack a first step, that loops can be complete and coherent and still leave us searching for a beginning that isn't there. It's a gentle paradox, not a contradiction, but an oddity, a structure that fits together perfectly, while missing the piece we most want to find. And in that peculiar completeness, that origin-less existence, we find something to ponder as we drift towards sleep. A puzzle that asks not for an answer, but for contemplation, a loop of thought that circles back on itself, complete and self-contained, just like the paradox it describes. The next story is about to begin. Please relax and enjoy. The world we move through, from morning to night, runs on a rhythm so familiar that we rarely notice it. One thing leads to another. Earlier moments shape later ones, and the past sits fixed behind us, while the future remains open ahead. When you flip a light switch, the bulb glows. When you drop a cup, it falls. Cause flows into effect with a steadiness that feels almost like a physical law, and in a sense, it is. This chain of causality gives structure to our days, our decisions, and our understanding of how events connect. We live in a universe where time moves forward, where what has already happened cannot be undone, and where the sequence of events follows a logic that makes sense. But then comes a question, simple on the surface, that threatens to unravel that entire structure. What if you could travel backward in time and change something that made your journey possible in the first place? Not a grand change, not the reshaping of empires or the prevention of disasters, but something deeply personal, something that reaches into your own origin and pulls it apart. The grandfather paradox is built on exactly this question. It doesn't ask you to imagine complex machinery or exotic physics. It only asks you to consider one trip backward, one act and one consequence. The paradox gets its name from the simplest version of the problem. A traveller goes back in time to a moment before their grandparents ever meet and prevents that meeting from happening. If the grandparents never meet, they never have children. If they never have children, the traveller is never born. And if the traveller is never born, they cannot make the trip back to prevent the meeting. The circle closes on itself, and the logic collapses into contradiction. This is not a story about adventure or tragedy. It is a thought experiment, a tool for examining the deepest assumptions we make about time, causality, and the structure of events. The grandfather paradox asks whether the universe can allow backward time travel without breaking the rules that keep history coherent. And in asking that question, it forces us to think carefully about what we mean when we say the past is fixed, what we mean when we imagine changing it, and whether the idea of changing your own origin even makes sense in a world governed by consistent cause and effect. The paradox is clean, sharp, and unsettling, not because it involves dramatic consequences, but because it reveals a quiet, fundamental tension in the logic of time. Let's begin by setting up the scenario with care, because the paradox depends on understanding exactly what is being proposed. Imagine a person who exists in the present day, someone with a history, a lineage, a chain of ancestors stretching backward through time. Among those ancestors are two people, the traveller's grandparents, who at some point in the past met, formed a relationship, and eventually had a child who became the traveller's parent. This meeting, unremarkable in itself, was a necessary link in the chain that led to the traveller's existence. Without that meeting, the traveller's parent would not exist. Without the parent, the traveller would not exist. The meeting is a causal dependency, a moment on which later moments depend. Now imagine that this traveller gains access to some mechanism for travelling backward in time. The details of that mechanism are not important for the paradox. It could be a machine, a natural phenomenon, a fold in space-time, or simply a hypothetical granted for the sake of argument. The key point is that the traveller moves from the present to a time in the past, specifically to a time before their grandparents have met. Once there, the traveller has the opportunity to act. And in the scenario that defines the paradox, the traveller chooses to act in a way that prevents the meeting from happening. Perhaps the traveller warns one grandparent away from a location, or introduces a distraction, or simply ensures that the two never cross paths. The method is not important. What matters is the outcome. The meeting does not occur. If the meeting does not occur, then the chain of events that led to the traveller's birth is broken. The traveller's parent is never born, and therefore the traveller is never born. At this point, the paradox begins to assert itself. The traveller's existence depended on the meeting. If the meeting is prevented, the traveller cannot exist. But if the traveller does not exist, they cannot have travelled back in time to prevent the meeting. And if they did not prevent the meeting, then the meeting happens, the traveller's parent is born, and the traveller is born, which means they can travel back and prevent the meeting. The loop is complete, and it contains a contradiction that refuses to resolve. This is not a question of probability or chance. It is not a matter of saying, well, maybe the traveller would fail, or perhaps something would stop them. The paradox is built on the assumption that the traveller succeeds, that the prevention is real, and that the causal chain is broken. And yet that success requires the traveller to exist, which requires the chain to remain unbroken. The paradox is a direct logical collision, a situation where two incompatible histories seem to be demanded by the same sequence of events. Either the meeting happens, or it doesn't. Either the traveller exists, or they don't. But the scenario seems to require both outcomes at once, depending on which moment in the timeline you examine. This is why the grandfather paradox is so much more than a quirky story problem. It exposes a structural tension in the idea of backward time travel. When we imagine travelling forward in time, we are simply imagining skipping ahead, moving through the future faster than normal. There is no contradiction in that. The future has not happened yet, so there is no fixed sequence of events to violate. But when we imagine travelling backward, we are entering a domain that has already happened, a stretch of history that is settled and complete. And if we imagine changing that history, we are proposing to alter events that led to the present moment, including, potentially, the events that led to our own existence. The paradox asks whether that kind of change is even possible in a universe governed by consistent cause and effect. Let's slow down and examine the contradiction in more detail, because the paradox is subtle and it deserves careful attention. The traveller exists in the present. That existence is a fact, a result of a long chain of causes stretching back through time. Among those causes is the meeting of the traveller's grandparents. The meeting is not optional, it is a necessary condition for the traveller's existence. If the meeting did not happen, the traveller would not exist. This is straightforward causality, the kind we rely on every day. Now the traveller goes back in time. At the moment of travel, they exist. They have a body, a mind, a history. They step into the past and they are there, physically present, able to act. They find the time and place where the grandparents are about to meet, and they intervene. The intervention succeeds. The grandparents do not meet. At this point, the chain of causality that led to the traveller's existence is broken at its source. The traveller's parent is never born. The traveller is never born. But here is the problem. If the traveller is never born, they cannot be standing in the past, intervening. The action that broke the chain depends on the traveller existing, which depends on the chain remaining unbroken. This is not a matter of the traveller fading away like a character in a science fiction story. The paradox is not about what happens to the traveller's body or their memory. It is about the logical structure of events. If the traveller exists, then the chain must be intact, which means the meeting happened, which means the intervention did not succeed. But if the intervention did not succeed, then the traveller can travel back and try again. And if they try again, they might succeed, which means the chain is broken, which means they do not exist, which means they cannot intervene. The timeline seems to demand two histories at once, one in which the meeting happens and the traveller exists, and one in which the meeting does not happen and the traveller does not exist. But a single, consistent timeline cannot contain both histories. This is the heart of the paradox. It is not a puzzle to be solved by cleverness or imagination. It is a logical impossibility, a situation where the conditions of the scenario contradict each other. The paradox reveals that backward time travel, if it allows for changes to the past, threatens the consistency of history. And consistency is not a small matter. Consistency is what allows us to make sense of events, to trace causes to effects, to understand why things happen. If history can be both one way and another way at the same time, then causality breaks down, and with it, our ability to reason about the world. So the grandfather paradox is not just a fun thought experiment. It is a test, a challenge to any theory or idea that permits backward time travel. The test is simple. Can your theory allow travel to the past while preserving a coherent, consistent timeline? If it cannot, then something must give. Either time travel must be restricted in some way, or the idea of a single, consistent history must be abandoned, or time travel must be ruled out entirely. These are the three main responses to the paradox, and each response has profound implications for how we understand time causality and the nature of the universe. The first response is to insist that the past is fixed, that history is self-consistent, and that any attempt to create a contradiction will fail. This is sometimes called the self-consistency principle, and it has a long history in discussions of time travel. The core idea is simple. If time travel is possible, then the past already includes all the actions of time travelers, and those actions must be consistent with the history that led to the traveller's existence. In other words, you cannot change the past because the past already happened, and it happened in a way that allowed you to exist and to travel back. Any attempt to prevent your grandparents from meeting would fail, not by chance, but because a consistent timeline has no room for a successful contradiction. Under this view, the grandfather paradox is not a paradox at all. It is simply a demonstration that certain actions are impossible. You might go back in time with the intention of preventing the meeting, but something would always stop you. Perhaps you would arrive too late, or be delayed by unforeseen circumstances, or find that the grandparents met in a different way than you expected. Perhaps you would change your mind, or be unable to act, or discover that your intervention was part of the reason they met in the first place. The universe, in effect, protects its own consistency. It does not allow events to unfold in a way that would create contradictions. This might sound like fate or predestination, but it is not quite that. It is not that your actions are forced or that you lack free will. It is that the space of possible actions is constrained by the requirement of consistency. You cannot perform an action that would erase your own existence because such an action would be logically impossible. It is similar to saying you cannot draw a square circle or create a married bachelor. The impossibility is not physical, it is logical, and in a universe governed by consistent cause and effect, logical impossibilities do not happen. This approach has a certain elegance. It allows time travel to exist while preserving the coherence of history. But it also raises questions. If the past is fixed, then what does it mean to travel back in time and act? Are you truly free to choose your actions, or are you simply playing out a role that history has already assigned to you? And if every action you take in the past was already part of history, then in what sense are you changing anything? You are not changing the past, you are simply being part of it. The past already included your visit, your actions, your presence. Nothing new is happening. You are just experiencing events that, from the perspective of the timeline, already occurred. Some people find this satisfying, others find it troubling. It seems to reduce time travel to a kind of observation, where the traveller is a participant in history, but not an agent who can alter it. The past is a script that has already been written, and the traveller is an actor who must follow the lines. There is no room for improvisation, no possibility of deviation. The timeline is a single, fixed structure, and time travel is simply a way of moving within that structure, not a way of changing it. But there is another response to the paradox, one that takes a very different approach. Instead of insisting that the past is fixed, this response suggests that travelling back in time does not take you to your past, but rather to a different timeline, a branching history that diverges from the one you came from. Under this view, when the traveller goes back and prevents the grandparents from meeting, they are not erasing their own history. They are creating or entering a new history, a branch where the meeting does not occur, where the traveller's parent is never born, and where the traveller never exists in that branch. But the traveller themselves does not vanish, because they originated from the original timeline, not the new one. They are a visitor from a different branch of history, and their existence is grounded in that original branch, not in the altered one. This is the branching timelines approach, sometimes called the many worlds interpretation of time travel. It dissolves the paradox by separating the traveller's origin history from the history they alter. There is no contradiction because there are two distinct histories, and they do not interfere with each other. In the original timeline, the grandparents meet, the traveller is born, and the traveller eventually travels back. In the new branch, the grandparents do not meet, and the traveller's counterpart is never born. The traveller stands in the new branch as a remnant of the original, a being whose existence makes sense only in the context of a different history. This approach has its own appeal. It allows for genuine changes to the past, or at least to a version of the past, without creating contradictions. The traveller is free to act, to intervene, to alter events, because those alterations do not erase the traveller's own origin. The timeline does not loop back on itself. It forks, creating a new path that diverges from the old. And because the two paths are separate, there is no logical collision, no demand for two incompatible histories within a single timeline. But the branching approach comes with its own costs. It requires accepting the existence of multiple timelines, multiple versions of history that coexist in some way. This raises questions about the nature of reality, the relationship between these branches, and the meaning of identity. If the traveller prevents the meeting in one branch, are they saving the people in that branch from some future consequence? Or are they simply creating a new world where those consequences do not occur? And what about the original timeline? Does it still exist, unchanged, with the grandparents meeting and the traveller eventually being born, while the new branch unfolds in parallel? If so, then the traveller has not changed their own past. They have simply created a different past for a different world. Some people find this satisfying because it allows for agency and change without contradiction. Others find it unsatisfying because it seems to dilute the significance of time. Travel. If you cannot change your own past, only create new branches, then time travel is not really about revisiting and altering your history. It is about generating alternate histories, parallel worlds that diverge from your origin. The traveller becomes a kind of immigrant, moving from one world to another, but never able to return to the exact moment and place they came from, at least not in a way that would allow them to change it. And then there is the third response, the hardest and the simplest. Perhaps backward time travel is simply impossible. Perhaps the universe does not allow it, not because of technological limitations or practical difficulties, but because the very idea contains a logical flaw that cannot be resolved. The grandfather paradox, under this view, is not a puzzle to be solved. It is evidence, a demonstration that any physical theory permitting backward time travel in a single, consistent timeline must be wrong or incomplete. The paradox functions as a paradox. Warning sign. If your theory leads to this kind of contradiction, something in the theory must be adjusted or rejected. This view is sometimes called the causality protection conjecture, or more informally, the idea that the universe protects its own consistency by forbidding processes that would violate it. If time travel to the past were possible, and if it allowed for changes that could erase their own causes, then the universe would be vulnerable to contradictions. And since contradictions cannot occur in a consistent physical reality, the universe must prevent the conditions that would create them. Backward time travel, at least of the kind that allows causal loops and self-negating actions, is ruled out by the structure of space-time itself. This is a conservative response, but it has a certain appeal. It preserves the integrity of causality without requiring multiple timelines or self-consistency constraints that feel like fate. It simply says, the universe is the way it is, and part of being the way it is involves not allowing backward travel that would create paradoxes. Time is directional, flowing from past to future, and that flow is a fundamental feature of reality, not something that can be reversed or circumvented. Of course, this response does not answer the question of why time is directional, or what physical mechanism enforces the prohibition on backward travel. It is more of a boundary condition, a statement of what is possible rather than an explanation of what prevents the impossible. But it has the virtue of simplicity. It does not require exotic structures or ontologies. It simply says, time travel to the past is not part of the universe we live in, and the grandfather paradox is one reason we can be confident of that. So we have three responses, three ways of addressing the paradox. The self-consistency approach says the past is fixed and time travel cannot create contradictions, so any attempt to prevent the meeting would fail. The branching approach says time travel creates new timelines, so the contradiction dissolves because the traveller's origin is separate from the altered history. And the impossibility approach says backward time travel cannot happen, so the paradox is a reductio ad absurdum, a proof by contradiction that the scenario is not physically realizable. Each response preserves logical consistency, but each does so in a different way, and each has different implications for how we understand time, causality, and the nature of reality. But the grandfather paradox is not just about resolving contradictions or defending theories. It also teaches us something deeper, something about identity, agency, and the meaning of could have. When we imagine time travel, we often imagine a kind of freedom, the ability to go back and fix mistakes, to undo regrets, to change the course of events. The paradox forces us to confront the limits of that freedom. If changing the past means erasing the reason you went back, then the very idea of that change becomes logically incoherent. You cannot exercise agency in a way that deletes the conditions of your own existence, because such an exercise would be self-negating. This is a profound limit, and it touches on questions that go beyond physics. What does it mean to say, I could have done otherwise, if doing otherwise would eliminate the I who did it? In ordinary life, we assume a kind of continuity. I am the same person who made a choice yesterday, and I can reflect on that choice, regret it, wish I had chosen differently. But time travel breaks that continuity in a unique way. If I go back and change the choice, I do not simply create a different present for myself. I potentially erase the entire chain of events that made me the person who is capable of going back. The paradox reveals that causality and identity are intertwined, that I am a product of a history, and that history must remain consistent for I to exist. This is not to say that we lack free will, or that our choices are not real. It is to say that free will operates within a framework of causality, and that framework has constraints. You can make choices, and those choices have consequences, but you cannot make a choice that eliminates the conditions under which you're able to make choices. The grandfather paradox is an extreme illustration of this point. It asks what happens when you try to exercise agency in a way that undermines the basis of your own agency, and the answer is logical contradiction. The universe does not allow it, either because the action would fail, or because the action would create a new branch, or because the action is impossible from the start. There is also a kind of emotional intuition at work when we think about time travel, a feeling that if we could just go back, we could fix things, make them right, undo the harm. The grandfather paradox challenges that intuition by showing that the logic of causality does not bend to our desires. The past is not a rough draft that can be revised. It is a foundation on which the present stands, and pulling out a foundational stone means the whole structure collapses, including the person doing the pulling. This is not a pessimistic conclusion. It is simply a recognition of how cause and effect work. The past shapes us, and we cannot unshape ourselves by changing that past, because the change would eliminate the shaped person who made it. In this way, the paradox teaches a kind of humility. It reminds us that we are embedded in time, that our existence is contingent on a vast web of prior events, and that we cannot step outside that web without losing the ground beneath our feet. Time travel stories often imagine a hero who stands outside time, who can manipulate it freely, who is immune to the consequences of changing history. But the grandfather paradox says, no, you cannot stand outside. You are part of the timeline. Your existence depends on it. And if you try to change it in a way that erases you, the change itself becomes impossible. This is a lesson not just about time travel, but about the structure of reality. Causality is not just a rule, it is the fabric that holds events together, that gives meaning to before and after, that allows us to say, this happened because that happened. When we think about time, we often think of it as a river, flowing from past to future, carrying events along with it. The grandfather paradox asks, what happens if you try to swim upstream and cut off the source? The answer is that you cannot, because you're made of the water that flows from that source. Remove the source, and you remove yourself, and the removal undoes itself. The river flows on, unchanged, because it cannot be interrupted by something that depends on it for existence. Let's return to the core question one more time, because it is worth holding in mind. If you could alter the past, could you ever alter it in a way that deletes the reason you went back? The paradox says no, not in a single consistent timeline. Either the alteration fails, or it creates a new branch, or it never happens at all. And this is not a failure of imagination or a limit of storytelling. It is a fundamental constraint imposed by the logic of causality. The past and the present are linked, not by sentiment or memory, but by the unyielding requirement that effects must follow from causes, and that a cause cannot be undone by its own effect. The grandfather paradox is a simple thought experiment, but it carries a deep purpose. It shows how fragile causality becomes when you allow effects to reach backward into their own causes. It reveals the tension between our intuitive sense of what time travel should allow and the logical requirements of a consistent universe. And it forces anyone who thinks seriously about time travel to answer, not with drama or speculation, but with clear rules. How the timeline stays coherent when the past can be visited. In the Wachi end, the paradox is less about time machines or adventures through history and more about the nature of time itself. It asks whether time is a dimension that can be navigated freely, like space, or whether it has a unique structure, a directionality, a resistance to being undone. And it suggests that whatever the answer must respect the fact that we are beings embedded in time, shaped by it, and unable to escape the logic that connects our existence to the events that came before. The paradox does not have a single resolution that everyone agrees on. Different thinkers, different theories, different philosophical perspectives offer different answers. But the question remains, and it remains because it touches on something fundamental about how the universe works, or at least how it seems to work from our perspective as creatures who move through time in one direction, from birth to death, from cause to effect, from past to future. The grandfather paradox is a reminder that time is not just a stage on which events unfold, it is part of the structure of those events, and changing it is not as simple as turning a dial or stepping through a door. And so we return to the calm takeaway, the gentle landing after all this thinking. The grandfather paradox is not a crisis, it is not a horror, it is a tool, a way of clarifying what we mean when we talk about time, causality, and change. It shows us that the past is not infinitely malleable, that our existence is tied to a history that cannot be casually erased, and that any serious idea of time travel must grapple with the logic of consistency. The paradox asks a question, and the question is worth asking, because it leads us to think more carefully about the world we live in, the time we move through, and the causes and effects that connect one moment to the next. Time flows, the past recedes, the future approaches, and we move along with it, unable to turn back, unable to erase what has been. The grandfather paradox is a thought experiment that reminds us of that fact, not with sadness or regret, but with a quiet recognition of the structure that holds everything together. Causality is real, time is directional, and the logic that binds them is not negotiable. And in that non-negotiable logic, there is a kind of stability, a foundation we can rely on, even if it means we cannot undo the past. The universe, it seems, has its rules, and one of those rules, whether enforced by self-consistency, by branching timelines, or by the impossibility of backward travel, is that you cannot erase yourself by changing the events that led to your existence. The paradox is a demonstration of that rule, a sharp, clear illustration of what happens when you try. And the answer is always the same. The timeline stays coherent, one way or another, because coherence is not optional. It is the very basis of a world where events make sense, where history is knowable and where we can trace the thread of cause and effect from one moment to the next. The grandfather paradox stands as a quiet sentinel at the boundary between logic and imagination, between what we can dream of and what the structure of reality permits. It does not close the door on time travel entirely, but it does insist that any door that opens must lead to a hallway that does not loop back into itself in a way that erases the person walking through it. The hallway must be consistent, must follow rules, must preserve the connection between the walker and the walk. And in that insistence, there is a kind of comfort. The universe is not arbitrary. It does not allow contradictions. It holds itself together with a logic that is stern but fair, unyielding but comprehensible. The grandfather paradox is a test of that logic, and the logic passes every time by refusing to permit the impossible. Time travel, if it exists, must bow to consistency. And if it cannot, then it does not exist, and we remain here in the present, shaped by the past moving toward the future, one moment at a time, in a timeline that makes sense. This is the lesson of the paradox, the quiet, steady conclusion that emerges from all the thought and all the questions. The past is what it is. The present follows from it. The future will follow from the present. And you, the person thinking about all this, are a link in that chain, a being whose existence testifies to the fact that the chain has held, that the causes and effects have lined up, that history has unfolded in a way that brought you here. The paradox asks whether you could break that chain by travelling back and interfering with it. And the answer is no, not in a way that makes you disappear, because your disappearance would erase the interference and the chain would remain unbroken. There is a beauty in that answer, a kind of integrity. The universe protects its own consistency, not by force or by accident, but by the very structure of causality. And we, as beings who live within that structure, can trust it, can rely on it, can know that the past is fixed in a way that gives meaning to the present. The grandfather paradox is a thought experiment that reveals that trust, that reliance, that meaning. It shows us that time is not just a dimension to be navigated, but a framework to be respected, a logic to be honoured, and a foundation on which everything else is built. And so, as you think about the paradox, as you turn it over in your mind, as you consider the traveller and the grandparents, and the meeting that must or must not happen, you are also thinking about yourself, your own history, your own place in the chain of cause and effect. You are realising that you're not separate from time, not an observer standing outside it, but a participant, a product, a result. Your existence is proof that the timeline is consistent, that the cause is lined up, that the effects followed. And that proof is all around you, in every memory, every choice, every moment that led to this one. The grandfather paradox is not a threat, it is a clarification. It is a way of seeing the structure of time more clearly, of understanding the limits and the possibilities, of recognizing that some things are not negotiable, not because they are forbidden by fiat, but because they are incoherent by definition. You cannot erase yourself by changing the past because the change depends on you, and you depend on the past. The circle is closed, the logic is complete, and the timeline stands consistent and whole. And in that wholeness, there is peace. The past is behind you, fixed and complete. The future is ahead, open and uncertain. And you are here in the present, the product of one and the creator of the other, moving through time in the only way that makes sense, forward, steadily, one moment at a time, in a universe that holds itself together with a logic that cannot be broken, no matter how much we might imagine otherwise. The grandfather paradox is a reminder of that logic, a gentle, insistent reminder that causality is real, that time has a direction, and that the structure of the universe is such that you cannot step outside it without ceasing to be. And in that reminder, there is a kind of reassurance, a knowledge that the world makes sense, that the past is stable, that the present is grounded, and that the future, whatever it holds, will follow from the same chain of cause and effect that brought you here. So the paradox, in the end, is not about impossibility or frustration or limitation. It is about understanding. It is about seeing the world as it is, with its rules and its logic and its quiet, unyielding structure. And it is about accepting that we are part of that world, bound by its rules, shaped by its logic, and held in place by its structure. The grandfather paradox is a window into that understanding, a thought experiment that teaches us, with patience and clarity, how the universe works, how time flows, and how causality binds everything together into a coherent, consistent whole. And as you drift towards sleep, as the thoughts settle and the questions fade, you can rest in that understanding, knowing that the world is stable, that the past is fixed, that the present is real, and that the future will unfold in a way that makes sense, one moment leading to the next, in a chain that cannot be broken, in a timeline that holds. The grandfather paradox asks a question, and the answer is the same as the answer to so many questions about the universe. Consistency, coherence, logic. The universe holds itself together, and in that holding, there is order, there is meaning, and there is a foundation we can trust. The paradox is a thought experiment, but it is also a kind of meditation, a way of thinking about time that brings clarity and calm. It shows us that the world is not chaotic, not arbitrary, not vulnerable to contradictions. It shows us that causality is real, that time is directional, and that the structure of events is such that the past supports the present, and the present will support the future, in a chain that cannot be undone, in a logic that cannot be violated, in a universe that makes sense. And so, with that calm understanding, we let the paradox settle, let the questions rest, and let the quiet logic of causality carry us forward, into sleep, into dreams, into the next moment, knowing that the timeline is consistent, the universe is coherent, and the past, whatever it was, is fixed in a way that allows the present to be what it is, and the future to unfold as it will. The grandfather paradox is a reminder, a teacher, a guide, and in its simplicity, it reveals the deep, steady structure of time itself, the structure that holds everything together, the structure that makes sense, the structure that allows us to move through the world with confidence, knowing that cause leads to effect, that before leads to after, and that the universe, in its quiet way, holds itself together, moment by moment, in a chain that cannot be broken. Before we descend into the darkness, I want to ask a favour. If you enjoy this story, please use your hype points on this video. It helps the channel more than you possibly know. If you're listening on Spotify, leaving a review makes a massive difference. And if you'd like, comment what time it is and where in the world you're listening from. We absolutely love seeing where everyone is tuning in. And of course, if you enjoy the content, consider subscribing. Now let's begin. There is something quietly comfortable about the assumption that things stay themselves. The ship docked at the harbour this morning is the same ship that was there yesterday. The chair in the corner of the room is the same chair it was last week. We live surrounded by objects that seem to maintain their identities despite the passage of time, despite minor wear and tear, despite small repairs and adjustments. This sense of stable identity feels so natural that we rarely question it. A ship might get a fresh coat of paint, a new sail, a replaced board or two, and we still call it by the same name, still think of it as the same vessel. The continuity seems obvious, unproblematic, woven into the basic fabric of how we navigate the world. But there is an ancient thought experiment that takes this everyday comfort and stretches it until something strange begins to show through. It does not do this through dramatic transformation or sudden change. Instead, it simply follows the normal process of maintenance and repair to its logical conclusion, and in doing so, reveals a quiet puzzle about what we mean when we say something is the same thing over time. This is the paradox known as the ship of Theseus, and it has occupied philosophers for more than 2,000 years precisely because it does not feel like a trick question. It feels like it should have a straightforward answer, and yet the more carefully you think about it, the more that answer seems to slip away. The scenario itself is remarkably simple. Imagine a ship, an ordinary wooden sailing vessel, perhaps one that has served faithfully for many years. Like all ships made of organic materials, it requires regular maintenance. Wood rots when exposed to seawater. Planks crack under strain. Masts weaken over time. So the ship's caretakers do what any responsible owner would do. They replace the damaged parts. A rotting plank on the hull is removed, and a fresh one is fitted in its place. A few months later, another plank needs replacing. Then a section of the mast, then some of the rigging. Each repair is minor, sensible, the kind of thing that happens to ships all the time. The key detail is that this process continues. Year after year, the ship is kept in service through careful, gradual replacement. Each time a piece begins to fail, it is swapped out for a new one. The ship never stops being used. It never goes into dry dock for a complete overhaul. It never sits idle while being reconstructed from scratch. Instead, it remains continuously operational, always the same ship in appearance and function, always bearing the same name, always recognised by sailors and port authorities as the vessel it has always been. The replacements happen one at a time, spread out over months or years, so that at no single moment does the ship undergo a dramatic transformation. And yet, if you follow this process long enough, something unsettling emerges. Suppose the maintenance continues for decades. Every plank in the hull is eventually replaced, every timber in the frame, every piece of the mast and rigging, every nail, every fastening, every component that makes up the physical structure of the ship is at some point removed and substituted with a new part. The process is so gradual that there is never a moment when you could point and say, here is where the ship became something else. At every stage, it looked like the same ship. It sailed the same routes. It was commanded by the same captain, or at least by captains in an unbroken succession. It bore the same name painted on its hull. And yet, by the end of this long process of maintenance, not a single molecule of the original ship remains. Every physical piece that made up the ship when it was first built has been discarded and replaced. So here is the question that creates the paradox. Is it still the same ship? The immediate, intuitive answer for many people is yes, of course, it is the same ship. Nothing dramatic happened. There was no moment of destruction and recreation. The ship never ceased to exist, never stopped being used, never lost its continuity. From the perspective of anyone watching the ship over those years, it simply continued being itself, undergoing normal repairs the way any long-lived object does. If you walked down to the harbour to see the ship of Theseus, you would see a ship that looks right, functions correctly, and has a continuous documented history stretching back to its origin. In every practical sense, it seems to be the same ship. But another part of our thinking rebels against this conclusion. If literally nothing of the original ship remains, if every single piece has been replaced, then what exactly makes it the same ship? It is not the same physical matter. The wood that made up the original hull is gone. The metal fittings are different. Every atom that was present at the ship's construction has been removed. What we are calling the ship of Theseus now is made of entirely different stuff than what we called by that name originally. So in what sense is it the same? The name is the same, yes. The shape is the same, presumably. The function is the same. But is the ship itself the same? This is where the paradox begins to show its teeth, because it reveals that the word same might mean different things, and those different meanings can come into conflict. When we say two things are the same, we might mean they are made of the same material, the same physical substance, or we might mean they have the same form, the same structure and arrangement, or we might mean they have the same function, the same role and purpose, or we might mean They have the same history, the same continuous existence through time. These different criteria usually align. A chair is usually made of the same wood it was made of yesterday, still has the same shape, still serves the same purpose, and has existed continuously. But the ship of Theseus is a scenario where these criteria pull apart, and suddenly we have to decide which one actually defines identity. If identity is fundamentally about material composition, about the stuff something is made of, then the fully replaced ship is not the same ship. It is a different collection of matter that has been arranged to look and function like the original. Under this view, when you replace a plank, you're removing a piece of the ship and adding a piece of something else. Do this enough times and you have gradually subtracted the entire original ship and added an entirely new one. The fact that the subtraction and addition happens slowly, piece by piece, does not change the fundamental fact that the original matter is gone. A ship under this definition is its planks and masts and rigging, and when those are gone, the ship is gone, even if something very similar has taken its place. But if identity is fundamentally about form and function, about the shape and purpose of something, then the fully replaced ship is absolutely the same ship. After all, it has the same design, it performs the same role. If you showed someone a detailed blueprint of the original ship and asked them to identify which ship in the harbour matches that blueprint, they would point to the maintained vessel. The form has been preserved even as the matter has changed. Under this view, a ship is defined by its configuration, its structure, the way its parts are arranged to enable sailing. As long as that configuration is maintained, the ship remains itself, regardless of whether the individual components are original or replacements. And if identity is fundamentally about continuity through time, about an unbroken chain of existence, then again the maintained ship is the same ship. This is perhaps the most intuitive view for many people. The ship never stopped existing. It was never destroyed and rebuilt. At every moment in its history, there was a ship that everyone acknowledged as the ship of Theseus, and that chain of acknowledgement has never broken. The ship tomorrow is the same as the ship today, which is the same as the ship yesterday, which is the same as the ship the day before that. And if you trace that chain all the way back, it leads to the original ship. The fact that the material has gradually changed does not break the continuity. After all, rivers replace their water constantly, but we still speak of the Thames or the Nile as the same river over centuries. Each of these perspectives feels reasonable. Each captures something important about what we mean by identity, and yet they can lead to different conclusions about the ship. And that is precisely what makes this a paradox. It is not that there is a hidden correct answer we are failing to find. It is that our concept of sameness is itself more complicated than it first appears. And the ship of Theseus is a scenario that exposes that complexity by pushing the concept to a situation where its different aspects no longer align, but the paradox has a classic intensification, a twist that makes the problem even sharper. Suppose that as the ship is being maintained and its old parts are being replaced, those discarded original pieces are not destroyed. Instead, they are carefully preserved. Perhaps they are stored in a warehouse, or perhaps someone with a sense of history collects them. The rotting planks are set aside. The old mast is kept. Every original component is saved. And then, after the maintenance process is complete and the sailing ship has been entirely replaced with new parts, someone takes all those original components and reassembles them into a ship. Now there are two ships. One is the ship that has been continuously maintained, that never stopped sailing, that bears the name of Theseus, that has an unbroken operational history, but it is made entirely of new parts. The other is the ship that has been reconstructed from the original components, every plank and mast and fitting that was present when the ship was first built. But it has not been in continuous use. It sat disassembled for years while its parts were replaced one by one in the other vessel, and then it was put back together, all at once. Which one is the real ship of Theseus? The question becomes much more pointed now, because we have two candidates, and presumably only one of them can be the true continuation of the original ship. Unless, of course, we are willing to accept that both are the ship of Theseus, or that neither is, or that the question does not have a determinate answer. But those options themselves require justification. The continuously maintained ship has a strong claim based on continuity and function. It never stopped being the ship of Theseus. At no point in its history was there a gap in its identity. Every day it was recognised and treated as the same ship it had been the day before. It has the operational history, the legal status, the social recognition. If there are records of the ship's voyages, those records document the history of the continuously maintained vessel. If someone owns the ship of Theseus, they own the ship that kept sailing, not the pile of old planks in the warehouse. From a practical standpoint, from the standpoint of how identity works in the world of human institutions and agreements, the maintained ship seems to have the better claim. But the reassembled ship has its own powerful argument based on material identity. It is made of the original stuff. Every piece of wood, every metal fitting that was present when the ship was first constructed, is now part of the reassembled vessel. If you believe that a thing is fundamentally the matter it is made of, then this reassembled ship is the real ship of Theseus, and the maintained ship is an imposter, a replica that happens to have a good backstory. The reassembled ship might not have the continuity of use, but it has the continuity of substance. It is the original ship in the most literal, physical sense, so we seem to have a conflict. Continuity of form and function points in one direction, continuity of matter points in another. And the paradox asks us to choose, or at least to explain why both answers might be acceptable, or why the question itself might be confused. This intensified version of the puzzle reveals something important. The ship of Theseus is not just about change over time. It is about what we think identity fundamentally consists of. What makes something the thing it is rather than something else? One tempting response is to say that identity is somehow a matter of both material and continuity, and that the paradox arises because these have been artificially separated. In normal circumstances, they go together. A ship maintains its identity by being made of the same stuff and by existing continuously. The paradox forces us to consider a scenario where these come apart, and perhaps in such a scenario, our concept of identity simply breaks down or becomes indeterminate. Maybe there is no fact of the matter about which ship is the real ship of Theseus. Maybe both are, and neither is. Maybe identity is a concept that works well in typical cases, but fails to give clear answers in unusual cases like this. But there is another perspective worth considering, one that shifts the focus away from trying to find the inherent metaphysical truth about which ship is really the same, and toward thinking about identity as something that humans assign based on purpose, context, and agreement. Under this view, identity is not purely a matter of objective fact waiting to be discovered. It is partly a matter of human practice, of the rules and conventions we use to classify and track objects over time. Think about how identity actually works in the world. Objects have names, but those names are given by people. Objects have ownership, but ownership is a social and legal construct. Records are kept, histories are documented, but those are human activities. When we say this is the ship of Theseus, we are not just reporting a metaphysical fact about identity. We are making a claim that fits into a network of social practices, legal frameworks, cultural understandings, and different practices might give different answers to the identity question depending on what they care about. From a legal perspective, the continuously maintained ship is likely to be considered the ship of Theseus. It has the unbroken chain of ownership. It has been registered and recognised continuously. The replacement of parts during normal maintenance does not change legal identity. Ships are repaired all the time, and we do not treat every repaired ship as a legally distinct entity. So if there is a dispute about ownership or rights, the law would almost certainly side with the maintained vessel. From a historical or archaeological perspective, the reassembled ship might have the stronger claim. If the goal is to preserve the actual original object, the actual physical artifact from the past, then the ship made of original components is the authentic one. Museums care about preserving original materials. A museum would rather have the reassembled ship made of ancient wood than a continuously maintained ship made of modern replacements, even if the maintained ship has the better historical documentation. In this context, material authenticity matters more than continuity of use. From a functional perspective, if the question is which ship can actually sail and perform the role that the ship of Theseus performed, the answer is probably the maintained ship. It has been kept in working order. The reassembled ship, having sat in pieces for years or decades, might need extensive restoration before it could actually function. If the identity question is about continuing the ship's purpose and role, then the maintained ship succeeds, where the reassembled one might not. So we can start to see that which is the real ship of Theseus might not have a single answer that applies in all contexts. Different contexts care about different aspects of identity. Legal contexts care about continuity of recognition and ownership. Historical contexts care about material authenticity. Functional contexts care about operational continuity. These different concerns can legitimately give different answers, not because anyone is making a mistake, but because the same ship is being asked to do different work in different settings. This contextual view of identity does not mean that identity is arbitrary, or that we can just decide anything is the same as anything else. The context matters, but so do the facts about continuity, material composition, form, and function. The point is that there is not a single metaphysical fact about identity that determines the answer independent of why we are asking. Identity claims are made for purposes, and those purposes can affect which features of identity are most relevant. And this observation about objects, about ships and their parts and their histories, begins to suggest something about a different kind of identity question entirely. Because human beings also change over time. Human bodies replace their cells constantly. Skin cells slough off and are replaced in a matter of weeks. Red blood cells live for a few months before being recycled. Even neurons, once thought to be permanent, can be renewed in some parts of the brain. Over the course of years, the vast majority of the physical matter that makes up a human body is replaced. And yet we do not think of ourselves as becoming different people because our cells have changed. Memories change too. They are not perfect recordings, but reconstructions that can shift and alter with each recollection. Beliefs and values can evolve over a lifetime. Personality traits can shift. The person you are at age 50 might have very different opinions, different priorities, different habits than the person you were at age 15. And yet we still speak of personal identity as continuous. We say, I am the same person I was as a child, even though almost nothing about us, physically or mentally, has remained static. The ship of Theseus becomes a mirror for thinking about the self. If the ship with all its parts replaced can still be the same ship, then perhaps a person with all their cells replaced can still be the same person. But what makes that continuity? It is not the physical matter, because that changes. It is not the exact thoughts and memories, because those change too. So what is it? One answer is that personal identity is based on psychological continuity. As long as there is a continuous stream of consciousness, a chain of memories linking the present self to the past self, then identity is preserved. This is similar to the continuity argument for the ship. The person you are today remembers being the person you were yesterday, who remembered being the person the day before, and so on back through time. Even though the content of those memories and the beliefs you hold might change, the chain of psychological connection remains unbroken. Just as the ship never stopped being recognized as itself, You never stop being recognized as yourself by your own consciousness. But there are challenges here too. Memory is fallible. People forget things, sometimes forget entire periods of their lives. Are they no longer the same person if the chain of memory is broken? People with dementia or amnesia can lose vast stretches of their personal past, and yet we do not typically say they have become different people, only that they have lost access to their own history. So perhaps personal identity cannot be purely about psychological continuity in the sense of memory. Another approach focuses on the continuity of the body, but not the specific cells or atoms that make it up. Instead, the focus is on the continuous physical and biological process. Your body is not just a collection of parts, but an ongoing dynamic system. Cells are replaced, but the pattern of organization continues. You are not the same cells you were years ago, but you are the same biological process, the same continuous living organism. This is more like saying the ship is the same, because it maintains the same form and function, the same organized structure, even as the material substrate changes. But this too has complications. If someone loses a limb, they are still the same person. If they receive an organ transplant, they do not become someone else. So clearly, not all of the physical structure is essential to identity. And what about the brain? Many people have the intuition that the brain is more central to personal identity than other organs. If your brain were somehow transplanted into a different body, most people would say that you, the person, would go with the brain, not stay with the original body. But the brain is also made of matter that changes over time, so the same questions about material versus continuity still apply. There is also the question of what makes personal identity matter. We care about whether we will continue to exist in the future. We care about whether the person who will wake up tomorrow is the same person who goes to sleep tonight. This is not just an abstract philosophical question. It affects how we think about responsibility, about promises, about planning for the future. If the person you will be in 10 years is the same person you are now, then you have a reason to care about what happens to that future person, to make decisions that will benefit them. But if personal identity is vague or indeterminate in the way the ship of Theseus suggests, what does that mean for these practical concerns? One response is to say that personal identity is not all or nothing. Perhaps what matters is not strict identity, but a relation of connection or continuity. The person you will be in 10 years is connected to the person you are now through chains of psychological connection, physical continuity, and causal dependence. Those connections are strong enough to ground the kinds of care and concern we associate with personal identity, even if there is not some metaphysical essence that remains perfectly identical through time. This is sometimes called the relation that matters view. What matters for survival, for responsibility, for prudential concern is not strict identity, but the right kind of continuity. But returning to the ship itself, the paradox does not just ask us to pick between material and continuity. It reveals that there are multiple ways of understanding what identity claims actually mean, and these different understandings can be formalized in different philosophical frameworks. One approach is called essentialism. This is the view that things have essences, core properties or features that make them what they are. For the ship of Theseus, an essentialist might argue that there is some particular feature, whether material origin, original design, or something else, that is essential to the ship's identity. If that essence is preserved, the ship remains the same. If it is lost, the ship has become something else. The challenge for essentialism is identifying what that essence is and justifying why that particular feature is privileged over others. Why should original material be the essence rather than continuous function? Or vice versa? These choices seem somewhat arbitrary, unless there is a deeper principle to appeal to. Another approach is continuity theory, which focuses on identity as a relation across time rather than a property at a single moment. On this view, The ship of Theseus is not a single thing existing at different times, but a series of temporal stages connected by the right kind of continuity relations. The ship today is the same as the ship yesterday because it is connected to it by spatial continuity, causal continuity, and similarity. As long as these connections are strong, enough identity is preserved, even if the material changes. This approach handles gradual change well, because each small step maintains strong continuity with the previous step. But it might struggle with the reassembled ship case, because there the continuity is broken when the ship is disassembled, even though the material is preserved. A particularly interesting framework is called four-dimensionalism or perdurantism. This view treats objects as extended through time, in something like the way they are extended through space. Just as a ship has a front and a back, existing at different spatial locations, it also has a past and a future, existing at different temporal locations. On this view, the ship of Theseus is not something that exists entirely at a single moment, and then persists by being the same thing at later moments. Instead, it is a four-dimensional object, a space-time worm that has different temporal parts at different times. The ship at the beginning of the maintenance process is one temporal part. The ship in the middle of the process is a different temporal part. The ship at the end is yet another temporal part. These are all parts of the same larger four-dimensional object. This might sound strange at first, but it has some appealing features. It explains how change is possible without loss of identity. The ship of Theseus can have different properties at different times, including being made of different materials, because those properties belong to different temporal parts. The four-dimensional whole contains all these parts, and that whole is the ship. When we ask, is this the same ship, we are really asking whether two temporal slices are part of the same four-dimensional object, and they are as long as they are connected by the right kind of continuity. Four-dimensionalism also handles the reassembled ship case in an interesting way. On this view, there might actually be two four-dimensional objects. One is the object that includes all the temporal parts of the continuously maintained ship, stretching from the original construction through all the repairs and beyond. The other is the object that includes the original ship, then goes through a stage of being disassembled into separate parts, and then is reassembled. These are two different four-dimensional entities, even though they overlap at the beginning. The question, which is the ship of Theseus, becomes a question about which four-dimensional object the name refers to, which might depend on context or convention. Yet another approach is conventionalism, the view that identity is partly or entirely a matter of the conventions and rules we adopt for classifying and tracking objects. On this view, there is no deep metaphysical fact about which ship is the ship of Theseus independent of our practices and purposes. Instead, identity is determined by the criteria we choose to use, and different criteria are appropriate in different contexts. Legal conventions might identify the ship one way. Historical conventions might identify it another way. Neither is simply right or wrong. They are different conventions serving different purposes. Conventionalism does not mean anything goes. The conventions have to be coherent, useful, and applied consistently. But it does mean that when our conventions give conflicting answers, as they do in the ship of Theseus case, we should not necessarily expect there to be a single correct resolution. We might simply have to acknowledge that identity is context sensitive, and that different questions about the ship might legitimately get different answers. These different philosophical frameworks do not just offer different solutions to the ship of Theseus paradox. They represent different underlying views about what identity is and how it works. Essentialism says identity is about having the right properties. Continuity theory says it is about being connected in the right ways. Four-dimensionalism says it is about being parts of the same extended object. Conventionalism says it is about fitting the right criteria for the purposes at hand. Each framework has implications that extend far beyond ships and planks. They affect how we think about persons, about artifacts, about natural objects, about everything that persists through time. Consider a river. The water in the Thames today is not the water that was there yesterday. The molecules have flowed downstream, been replaced by water from upstream, and yet we say it is the same river. Why? Not because of material continuity, because the material is constantly changing. Possibly because of continuity of form, the river occupies the same channel and maintains the same general structure. Possibly because of continuity of process, the river is an ongoing flow of water through that channel. Different philosophical frameworks might emphasize different aspects of what makes the river the same river. Or consider a living cell. A cell maintains its identity while constantly exchanging matter with its environment. It takes in nutrients, expels waste, breaks down, and rebuilds its own components. The specific atoms that make up the cell are not the same from one moment to the next. What makes it the same cell is not material identity, but organizational identity. The cell maintains a boundary, a membrane that distinguishes inside from outside. It maintains a set of chemical processes that define its metabolism. It maintains information in its DNA that guides its structure and behavior. The identity of the cell is more about pattern than about parts. Or consider a more human creation, like a city. Is Paris the same city it was 500 years ago? The buildings are almost entirely different. The population is different. The political system is different. The language has evolved. What makes it the same city? Probably the continuity of location, the continuity of the name, the continuity of being recognized as Paris by its inhabitants and by the world. The identity of Paris is not about its physical components, which have changed completely, but about its continuity as a social and geographical entity. The ship of Theseus gives us a simple, clear case where we can see these issues in their purest form. No complications of consciousness, no debates about personhood, no messy biological processes, just a ship, some planks, and a question about what makes it the same ship. And yet that simple scenario opens up vast questions about the nature of identity itself. What emerges from thinking carefully about the paradox is that same is not a simple, unitary concept. When we say two things are the same, we might mean any of several different things. We might mean they are numerically identical, literally the exact same entity. We might mean they're qualitatively identical, having all the same properties, even if they are distinct entities. We might mean they are continuous, connected through time by the right kinds of relations. We might mean they fall under the same classification, they are the same kind of thing. The ship of Theseus is a case where some of these meanings pull apart. Numerical identity might point one way, material identity another way, continuity yet another way. And perhaps the deepest lesson is that our everyday concept of identity works well in ordinary circumstances, because these different aspects usually align. Things are usually made of the same stuff they were made of before. Things usually maintain their form while maintaining their material. Things usually persist continuously without breaking apart and being reassembled. So we do not have to distinguish between material identity, formal identity, and temporal continuity. They all point in the same direction, and we can just say, it is the same thing, without worrying about what exactly we mean by that. The ship of Theseus is valuable not because it has a single correct answer that philosophers have somehow failed to find for 2,000 years, but because it exposes the complexity hidden in that seemingly simple phrase, the same thing. It shows that identity is not a simple binary property that things either have or lack. It is a cluster of different relations and properties that usually coincide but can come apart in unusual cases. When they do come apart, we have to decide which aspects matter most for the question we are asking, and that decision might depend on context and purpose. There is something almost restful about this conclusion. The paradox does not need to be solved in the sense of finding the one correct answer that makes all the others wrong. Instead, it can be appreciated as a window into how our concepts work, how language and thought handle persistence and change. The ship of Theseus teaches us to be more careful and more aware when we talk about things staying the same over time. It teaches us that same can mean different things, that identity is more nuanced than it appears, that continuity comes in different forms. And this awareness is useful not just for abstract philosophy, but for navigating the real world. When we think about whether a restored historical building is the same building, or whether a river that has changed course is the same river, or whether we are the same people we were years ago, we are grappling with ship of Theseus questions. The paradox does not give us a formula that solves all these cases, but it gives us tools for thinking about them more clearly. It helps us distinguish between material continuity, formal continuity, and historical continuity. It helps us see that different questions might legitimately care about different aspects of identity. It helps us understand that vagueness and context sensitivity in identity claims are not failures of our concepts, but features of how those concepts actually work. The ship of Theseus sails on, in a sense, through the history of philosophy. It appears in discussions of personal identity, in debates about artifacts and natural kinds, in questions about the persistence of nations and cultures and languages. It is a simple thought experiment that keeps generating new insights because it touches on something fundamental about how we think about objects in time. The ship does not need to reach a final port, does not need a definitive answer to which version is truly the ship of Theseus. The journey itself, the process of thinking through the puzzle, is what reveals the complexity of identity. Consider how this connects to our intuitions about originality and authenticity. We value original works of art more than copies. A painting by Rembrandt is worth vastly more than a perfect reproduction, even if the reproduction is visually indistinguishable. Why? Because the original has a different history. It was created by Rembrandt's hand. It has a causal connection to the artist that the copy lacks. In this context, material and historical authenticity matter enormously. The specific canvas and paint that Rembrandt applied are part of what makes it valuable. If you replace those with new materials, even if you perfectly preserved the image, you would have diminished its value as an original. But we also value continuity and use. A musical instrument that has been played continuously for centuries might be considered more valuable than an identical instrument that was built at the same time but sat unused. The played instrument has a history of performance, of use, of being part of living music. Even if its parts have been repaired and replaced over the years, it maintains a connection to that history of use that the unused instrument lacks. In this context, continuity of function and tradition might matter more than material originality. Different domains care about different things. This is not inconsistency. It is recognition that identity serves different purposes in different contexts. When we ask if something is the same, we need to know why we are asking. Are we asking for legal purposes, for historical purposes, for functional purposes, for sentimental purposes? The answer might legitimately vary depending on what matters in that context, and this points to something important about how concepts work in general. Many of our concepts are what philosophers call cluster concepts. They do not have a single defining feature that something must have to fall under the concept. Instead, they have a cluster of typical features, and things can belong to the concept by having enough of those features, even if they do not have all of them. Identity might work this way. There is a cluster of features associated with being the same thing: material continuity, formal continuity, historical continuity, functional continuity, spatio-temporal continuity. Typical cases have all of these. The ship of Theseus is unusual because it has some but not others, and so our concept does not give a clear verdict. This is not a flaw in the concept. Concepts do not have to give clear verdicts in every possible case to be useful. Language and thought are tools that evolved to handle typical situations. When we push into unusual edge cases, it is not surprising that our tools sometimes fail to give precise answers. The ship of Theseus is an edge case for the concept of identity. It is a scenario that our concept was not really designed to handle because in ordinary life, ships do not get every part replaced while remaining in continuous use. Nor do we typically save all the old parts and reassemble them. The fact that the concept does not give a clear answer in this case does not mean the concept is broken. It means we have reached the boundaries of where the concept applies clearly. And that is actually useful information. It tells us something about how the concept works, about what features it tracks, about what happens when those features come apart. The paradox is not a problem to be eliminated, but a phenomenon to be understood. There is also something to be said about the role of gradualness in the paradox. If the ship were destroyed and rebuilt from entirely new materials all at once, we would probably not hesitate to say it is a different ship, a replica. But when the change happens slowly, one plank at a time, it feels different. Each individual step seems not to change the identity. Replacing one plank does not make it a different ship. So how can a series of steps, each of which does not change the identity, add up to a change in identity? This is a version of a puzzle called the Sorites paradox, or the paradox of the heap. One grain of sand is not a heap. Adding a single grain to something that is not a heap does not create a heap. And yet somehow, if you keep adding grains, you eventually do get a heap. How is that possible? The ship of Theseus has this same structure. The ship with one plank replaced is the same ship. Replacing one more plank does not change that. And yet somehow, after enough replacements, we might want to say it is no longer the same ship, or at least we are uncertain. The gradualness creates a puzzle, because it seems like identity should be transitive. If ship A at time 1 is the same as ship B at time 2, and ship B at time 2 is the same as ship C at time 3, then ship A should be the same as ship C. But if we follow that logic through a long chain of small changes, we end up concluding that the original ship is the same as the fully replaced ship, even though they share no parts. One response is to deny that identity is always transitive in these cases of gradual change. Perhaps same ship is a vague predicate, one that does not have sharp boundaries. There is a range of cases where it is clearly true that something is the same ship, a range where it is clearly false, and a range in the middle where it is indeterminate. The fully original ship is clearly the same as itself. The fully replaced ship made of entirely new materials might be clearly not the same as the original. But somewhere in the middle, when half the parts have been replaced, or 2/3 or some other proportion, the answer might just be indeterminate. It is neither clearly the same nor clearly different. This indeterminacy might seem uncomfortable. We want clear answers. But indeterminacy is a feature of many concepts we use successfully. Consider bald. How many hairs can someone have and still be bald? There is no precise answer. Someone with no hair is clearly bald. Someone with a full head of hair is clearly not bald. But in between, there is a range where the answer is vague. The concept still works fine for most purposes. We do not need a precise cutoff to use the word meaningfully. Similarly, the ship of Theseus might simply be a case where the identity claim becomes indeterminate after enough change. This does not mean we cannot use the concept of identity. It means we recognize that it has limits, and that those limits show up in unusual cases like this one. For practical purposes, we can still make identity judgments in typical cases without worrying about the edge cases that arise in philosophical thought experiments. But there is also a question about whether the indeterminacy is in the world or in our language. Is it indeterminate whether the ship is the same because there is no fact of the matter, no objective truth about identity waiting to be discovered? Or is it indeterminate because our language and concepts have not carved up the world finely enough to give a precise answer? In this case, different philosophical views will answer differently. A realist about identity might say there is a fact of the matter, even if we do not know what it is or our language does not capture it precisely. Either the ship is the same or it is not, regardless of what we think or say. The challenge for this view is explaining what that fact consists in. What makes it true that the ship is or is not the same independent of any features we can point to? An anti-realist or constructivist might say that identity is not a feature of the world independent of our concepts and practices. Things are the same or different relative to the ways we classify and track them, and if our practices do not give a clear answer in some case, then there simply is no answer. Identity is something we impose on the world through our concepts, not something we discover in it. Most people probably fall somewhere in between these extremes. There seem to be real facts about continuity, about material composition, about form and function. But how we weigh these facts, which ones we privilege in making identity judgments, does seem to involve choices and conventions. So perhaps identity is partially objective, grounded in real features of the world, and partially conventional, dependent on how we choose to classify and track things. The ship of Theseus does not force us to pick one of these meta-metaphysical positions, but it highlights the question. When we ask, is it the same ship? Are we asking about something that has a determinate answer independent of us? Or are we asking how we should apply our concept of sameness in an unusual case? The paradox can be seen either as revealing something about the nature of identity itself, or as revealing something about the limits of our concepts, or both. There is a certain comfort in recognizing that not every question needs a definitive answer. The ship of Theseus has puzzled people for millennia, and that is fine. It is working as intended. A good philosophical paradox is not one that gets solved and disappears. It is one that keeps revealing new layers, keeps prompting new ways of thinking, keeps showing connections to other problems and questions. The ship of Theseus does all of this. It connects to questions about personal identity, about the nature of artifacts, about how concepts work, about the relationship between parts and wholes, about the role of time in our ontology. Each of these connections opens up new avenues for thought, and in a way the paradox is also a demonstration of how philosophy itself works. Philosophy does not always provide final answers. Often it provides better questions, clearer ways of framing problems, distinctions that help us think more carefully. The ship of Theseus takes a simple question, is it the same ship? And reveals all the complexity hidden in that question. It shows us that we need to distinguish between material identity, formal identity, and temporal identity. It shows us that these can come apart. It shows us that context matters for how we evaluate identity claims. These insights do not solve the paradox in the sense of making it go away, but they help us understand what is going on, why the question is hard, what is at stake in different answers. Philosophy done well should make you see familiar things in new ways. The ship of Theseus does this. After thinking about it carefully, you might look at ordinary objects differently. You might notice the gradual changes they undergo. You might wonder about what makes them continue to be themselves. You might be more aware of the role that human practices and agreements play in maintaining identity. That enhanced awareness, that shift in perspective, is valuable even if it does not come with a tidy solution. And there is something almost meditative about sitting with a paradox like this. Not trying to force an answer, not rushing to judgment, but simply thinking through the different considerations, feeling the pull of different intuitions, noticing how they conflict and how they might be reconciled. This kind of careful, patient thinking is a skill worth developing. It helps in many areas of life, not just philosophy. Being able to hold multiple perspectives, to see the validity in different viewpoints, to recognize when a question does not have a simple answer, these are valuable cognitive abilities. The ship of Theseus invites this kind of thinking. It presents a scenario where multiple answers seem reasonable, where different frameworks give different verdicts, where intuition pulls in different directions. And instead of demanding that we pick one and dismiss the others, it allows us to explore why each answer has merit, what assumptions underlie each one, what would follow from accepting each one. This exploration is itself worthwhile, independent of where it leads. As a thought experiment, the ship of Theseus is remarkably durable. It has persisted through millennia, been discussed by countless philosophers, been adapted and modified in countless ways. And yet the basic structure remains compelling. A ship has its parts replaced gradually. Is it still the same ship? The question is simple enough that anyone can grasp it, yet deep enough that it continues to generate philosophical interest. This combination of accessibility and depth is rare and valuable. The paradox also demonstrates the power of thought experiments in philosophy. We do not need to actually build a ship and replace all its parts to learn from this scenario. We can explore it in imagination, considering different possibilities, tracing out implications, testing intuitions. This is philosophy as a kind of conceptual engineering, using imaginary cases to map the contours of our concepts, to see where they work well and where they break down. And the ship of Theseus has inspired numerous variations and extensions. There are versions involving people, where someone's brain is gradually replaced, neuron by neuron, with artificial components. There are versions involving nations, where a country's territory, population, and government all change over time. There are versions involving abstract objects like songs or stories, which can be performed or retold in different ways while arguably remaining the same song or story. Each variation tests our intuitions about identity in a different domain, and each can reveal new aspects of how we think about sameness and difference. The reassembled ship variation, sometimes attributed to the philosopher Thomas Hobbes, is particularly effective at sharpening the paradox. It creates a direct competition between two candidates for being the ship of Theseus, forcing us to choose or to explain why both might qualify or why neither does. This intensification moves the discussion from vague uncertainty to a more pointed dilemma, and it highlights the question of what identity claims are for, what work they do. If we say the continuously maintained ship is the ship of Theseus, we are privileging continuity and function. If we say the reassembled ship is the ship of Theseus, we are privileging material composition and origin. Each choice reflects something about what we think matters most for identity. In some ways, the reassembled ship case reveals that our intuitions about identity might be inconsistent. We might want to say that the maintained ship is the same ship, because it never stopped being used and recognized as such. But we might also want to say that the reassembled ship has a strong claim, because it is made of the original parts. Holding both intuitions simultaneously leads to contradiction, because both ships cannot be the one and only ship of Theseus if they are distinct entities. So we have to give something up, to revise our intuitions, or to accept that identity is more complex or context-dependent than we initially thought. This process of confronting conflicting intuitions and working through the implications is central to philosophical methodology. We start with intuitions, with pre-reflective judgments about cases. Then we test those intuitions against each other, against principles, against thought experiments. When conflicts arise, we have to decide what to keep and what to revise. The ship of Theseus is a case that generates such conflicts, and working through them helps refine our understanding of identity. It is worth noting that the paradox also has practical analogues in the real world. There are actual ships and buildings that have been maintained over long periods through gradual replacement of parts. The question of whether they are still the original is not just academic. It affects legal status, historical significance, cultural value. Museums face Ship of Theseus questions when deciding how to restore artifacts. How much can you replace before it is no longer the original artifact? Different institutions and different cultural contexts might answer differently, and those different answers reflect different values and priorities. Similarly, there are legal cases that involve identity questions similar to the Ship of Theseus. If a company gradually changes its ownership, its management, its business model, and its assets, is it still the same company for legal purposes? If a nation's borders, population, and government all change over time, is it still the same nation? These are not just abstract puzzles. They have real consequences for contracts, treaties, property rights, and international law. The philosophical analysis of the Ship of Theseus can actually inform thinking about these practical cases by clarifying what is at stake in different approaches to identity. In the end, the Ship of Theseus endures as a philosophical problem precisely because it resists easy resolution. It sits at the intersection of several important issues: the nature of identity and persistence, the relationship between parts and wholes, the role of matter versus form, the importance of continuity versus origin, the way our concepts handle vagueness and gradual change. Each of these issues is rich and complex in its own right, and the Ship of Theseus touches on all of them in a single elegant thought experiment. The beauty of the paradox is also in its simplicity. You do not need advanced training in philosophy to understand the basic question. You do not need technical knowledge or specialized vocabulary, just a ship, some planks, and the question of what makes something the same over time. And yet, from this simple starting point, vast territories of philosophical inquiry open up. This is philosophy at its best, taking ordinary questions and showing that they lead to extraordinary depths. For someone lying in bed thinking about the Ship of Theseus, there is a kind of peaceful fascination in letting the question unfold without forcing an answer. You can imagine the ship being repaired, plank by plank, over years and decades. You can think about the workers carefully removing old wood and fitting new pieces into place. You can picture the ship sailing between ports, always recognized as itself, even as its material composition slowly changes. You can imagine the discarded planks being collected and stored, waiting to be reassembled. And you can hold the question gently: what makes it the same ship? Not rushing to judgment, not insisting on a single answer, but simply exploring the different ways one might think about it. This kind of contemplative thinking, where you turn a question over in your mind without demanding immediate resolution, has value beyond philosophy. It cultivates patience, flexibility of thought, comfort with ambiguity. These are qualities that serve well in navigating a complex world where many questions do not have simple answers, where different perspectives can each capture part of the truth, where wise judgment often involves balancing competing considerations rather than applying a single rule. The Ship of Theseus, in this light, is not just a problem to be solved, but an invitation to think deeply about something fundamental to how we understand the world. Objects persist through time. They change. We track them, name them, care about whether they continue to be themselves. And yet, when we look closely at what that persistence and that identity consist in, we find surprising complexity. The ship is a vehicle, quite literally, for exploring that complexity. It carries us into philosophical waters where the familiar concepts of same and different begin to behave in unexpected ways, and we have to navigate carefully to make sense of what is happening. As you drift towards sleep thinking about these questions, the paradox might take on a different character, less urgent, less demanding of resolution. The ship sails on in your imagination, neither definitely the same nor definitely different from its original self, existing in a kind of conceptual twilight where our ordinary categories blur and soften. And that is fine. That is part of what the paradox teaches. Not everything needs to be definitively resolved. Some questions are valuable precisely because they remain open, because they keep inviting us to think again, to consider anew, to find yet another angle from which to view the problem. The ship of Theseus has been sailing through philosophical waters for more than 2,000 years now. It has been discussed by ancient Greeks, medieval scholars, early modern philosophers, and contemporary analytic metaphysicians. Each generation finds something new in it, some fresh insight or connection, and it will likely continue to engage thinking minds for millennia to come, because the questions it raises are not the kind that get permanently answered and filed away. They are perennial questions, questions that touch on fundamental features of how we think and how we talk about the world. In a sense, the ship of Theseus itself, as a thought experiment, has persisted through time in a way analogous to the ship it describes. The exact wording of the paradox has changed. The context in which it is discussed has changed. The philosophical frameworks brought to bear on it have changed. And yet we still recognize it as the same paradox, the same question about identity and persistence. Has it maintained its identity through all these transformations? By what criterion the paradox applies to itself in a delightfully recursive way. And so the ship sails on through calm philosophical waters and through stormy debates, never quite reaching a final destination, always inviting new passengers to board and grapple with the question of what makes it the same ship. The journey itself is the point, the thinking, the questioning, the careful consideration of different possibilities, the recognition that our concepts are tools that work beautifully in ordinary cases but can perplex us at the edges. All of this is valuable. All of this enriches understanding, even without a final answer. As sleep approaches and thoughts begin to blur, the ship of Theseus might merge with other images, other questions, other gentle puzzles about identity and change. The ship becomes all ships, all things that persist through time while changing, all the ways we struggle to understand what makes something itself. And in that soft, drowsy state, the paradox loses its sharpness, becomes simply a wondering, a quiet musing on the strange and subtle nature of sameness and difference, of continuity and change, of the many ways things can be and cease to be themselves. The ship sails on into the night, into sleep, into the vast ocean of questions that have no final answers but endless depths to explore. And that is enough. That is more than enough. That is everything the paradox asks of us. To think, to wonder, to see the complexity in simple questions, and to rest in the knowledge that not all questions need to be answered to be worthwhile. The next story is about to begin. Please relax and enjoy.